and we have to show there's a number between. Well, the obvious thing is to take the mean. Let's just take x plus y over 2, and if that's rational, then we'll have proved the result. Well, here's the proof that it's rational. X plus y over 2 is equal to p over q plus r over s over 2, okay, which is p s plus q r over qs all over 2, which is ps plus qr over 2, what was it, qs, can't see underneath my hand here, which is rational because it's a quotient of two integers. But of course x is less than x plus y over 2 is less than y. And we're done. Okay, that's 1, 2 and 3 knocked off very, very quickly. Let's go on to do, I'll do number 7, the one about square root of 3. Well, just as we did with the square root of 2, we're going to prove it by contradiction. So I'm going to assume square root of 3 were rational. Okay. Then I could write root 3 is p over q, where p and q are natural numbers, and I can always assume that they have no common factors. Okay, because if you pick a pair of integers, a pair of natural numbers that do have a common factor, you can cancel it out. So you can always express a rational number in that form. Then if we square that, I get 3 is p squared over q squared. So I can multiply across by the q squared and get 3q squared equals p squared. So 3 divides p squared. But 3 is prime. And if a prime divides p squared, that means 3 divides p. If a prime divides a pair of numbers multiplied together, it divides one of the numbers. So 3 divides p. So that means p is of the form 3, let's call it 3r. Okay. So that means p squared equals 9r squared. So I can take p squared and substituting it back in here to get 3q squared equals p squared equals 9r squared. So if I'll forget the middle term now, 3q squared equals 9r squared. Let me factor the 3 out. I've got q squared equals 3r squared. So that means 3 divides q squared. But if 3 divides q squared, then just as before with p, that means that 3 divides q. And now I've got a contradiction. Since p and q have no common factors. And yet we've just shown that 3 is a common factor. So there's a contradiction, almost exactly the same as the one for square root of 2. So if we compare the two, CF, the proof for square root of 2, in the case of the square root of 2, we talked about numbers being even. But if we talk about something like p being even, that's just another way of saying 2 divides p. So really all I've done here is I've taken the previous proof, the one for root 2, and instead of talking about it in terms of even and odd, I could recast it in terms of whether it's divisible by 2 or not. And then the fact about 2 that we used there, we said if 2 divides p squared, then it divides p. It used the fact that 2 was prime. So I might just as well use 3. So it's exactly the same proof as before, except instead of talking about divisible by 2, I'm talking about being divisible by 3. I didn't express it that way before. I talked in terms of even and odd, but even just means it's a multiple of 2. Okay, well, we've moved on. Let me decide which one to do next. I think I'll do number 8. That shouldn't take too long. So we'll do number 8 next. Okay, so the converse of an implication, of a conditional, is the implication in the opposite direction, where you swap around the antecedent and the consequent, but everything remains more or less otherwise unchanged. So the converse of this is, if the yan rises, the dollar falls. We just swap them around. Same here. If negative y less than negative x, then x is less than y. And in the case of C, if 2 triangles have the same area, then they are congruent. Now, in terms of what we're doing, this is totally trivial. This is just swapping things around without doing anything. What I'm really trying to get at with this this exercise is in part to sort of contrast it with the contrapositive, and also to observe that truth and falsity can change. In this case, we start out with something that's true. This is a true implication. That's a true implication too. So sometimes the converse of a true implication is a true implication. Let's look at this one. If 2 triangles are congruent, they have the same area. That's true. But this one, if 2 triangles have the same area, they're congruent, that one's false. So sometimes the converse of a true statement is true, and sometimes the converse of a true statement is false. Now that's a different situation from what we find with the contrapositive. But when you swap round the order, you can sometimes get truth go into false, and you can sometimes preserve truth. Okay, well that's really all there is to that. It was just to sort of give an opportunity to reflect on these things and to recognise that truth and falsity plays its own game when you're dealing with converses. Okay, let's go and do number 11. Okay, that was that one about the irrational numbers. Well, we've already looked at some of these in the lecture where we've observed that some of them are rational. Let me see. We observed that this one can be rational. We observed that this one can be rational, and there's an issue about this one being rational. Okay, these were easy. We did those in the lecture. That was a later issue. That leaves 1, 2, and 5. They're the ones where they're irrational, and so we have to prove them this time. Okay, and so starting with number 1, say what we're trying to show is that it is irrational. So yes, it's irrational. Okay, and let's see. Suppose that r plus 3 were rational. Okay, that's a plus sign there. Then r plus 3 would be of the form p over q, where p and q are integers, where then r would equal p over q minus 3, which is p minus 3q over q, which is rational. And that's a contradiction. Because r is assumed to be irrational. And we've shown that if r plus 3 were rational, then r would have to be rational. And the others are similar. You simply assume the contrary, you express it in terms of p over q, and then you do a tiny little amount of manipulation, and you end up showing that the number r is rational here, and that square root of r is and that r is rational in the square root example. Okay, very straightforward. Nothing really more to be said about this one. Okay, the only one left now to do on assignment 7 is question 12. So let me just quickly go through question 12. Well, the key facts that you use in dealing with all of these are that if n is even, then, and actually if and only if, then n is 2k for some k, some integer k. Okay, and that n is odd if and only if n equals 2k plus 1 for some k. Okay, the even numbers are the ones that are multiples of 2, and the odd ones are the ones that are 1 more than a multiple of 2. Okay, they're in between the multiples of 2. So, for example, if we do part A, if m and n are even, then we would have m equals 2k, for example. We'd have n equals 2l. So m plus n would equal 2k plus 2l, which is 2 into k plus l, which means it's even. It's 2 times something else. Do I need to do one more? Well, let me just do one more anyway, just because I'm on a roll now. Let me do number D, part D. If one of them's even, it's 2k, and the other one's odd, it's 2l plus 1, then m plus n equals 2k plus 2l plus 1, which equals 2 into k plus l plus 1. Okay, so it's twice something plus 1, etc. for all the others. Okay, nothing terribly deep about these things, but in terms of writing out a proof, it's basically a case of just characterising evens and odds in this way and doing a tiny amount of algebra. Okay, that was a very easy assignment, I think. Well, it was meant to be an easy assignment. It's easy for me to say that, right? I've been doing this for years. If you haven't met this kind of thing before, then it probably isn't an easy assignment. I fell into the trap of mathematicians there of saying something's easy in the same way we talk about trivial. That's a sort of a term of art that we use in the game. So everything's easy when you know how to do it, right? Okay, but I was looking ahead to assignment 8, which was decidedly difficult for me and for you guys. Okay, assignment 8 coming next is difficult. Well, question 1 in problem set 5 asks us to judge whether this is a valid proof or not. Well, certainly the algebra looks correct, right? If m and n are odd, then by definition an odd number is simply one that's not even, and an even number is one that's a multiple of 2. So an odd number has to be of the form 2p plus 1, so that's okay for some p and for some q. So if they're odd integers such that, in which case multiplying them together, you get that, the algebra's correct, so mn is odd. Everything so far until this part, because it doesn't complete the proof. What we've shown is if. We've shown that mn is odd if m and n are odd. In other words, we've proved the implication that way. Okay, if m and n are odd, then mn is odd. So in this statement, we've proved the right-left implication, and we need to show the other part. We need to prove the only if part. In other words, the implication from left to right. It's if and only if. So we've proved the if part from right to left. We need to prove the only if part from left to right. i.e., we need to show let's write it out in full. If it's not the case that mn are odd, then mn is odd. Is not odd. Yeah, is not odd. Okay, there are various ways you can talk about this. Okay, i.e., well, if it's not the case that mn are odd, That should have been a comma there. Okay. If it's not the case that m and n are odd, then m times n is not odd. Okay. I got the tense correct, the plurality. That was are, and that is. Okay. If at least one of m and n is even, then m times n is even. Well, if m equals 2k, it doesn't matter which one we assume is going to be even, because multiplication is going to be commutative. If m equals 2k, then mn equals 2k times n, which is even. So this was hard. This is hardly going to set the world on fire, right? I mean, there's nothing terribly deep about this. It's extremely elementary. And it's not that you don't know this and understand it. The question is, can you write it down in a proof? And the point here is that we have to start with the definitions. And the definitions are n is even if and only if there is an integer k such that n equals 2k. And n is odd if it is not even. So starting from these two definitions, this is the proof we give. The first part that was actually given to us, that was fine from those definitions. We started with the definitions. Going the other direction, we took the definition. So the question is simply, all this really involves is reducing this to the definition. And then the argument itself is very simple. That was a slightly more complicated bit of algebra, but not much more. So it's not about the complexity of the algebraic manipulations. You've been able to do that for years, I know that. The question is, can you reduce the statement to something coming from the definitions? Because in many cases, you simply would, this would be so simple compared with most proofs in mathematics, you wouldn't go into these details. But the focus here isn't on at this stage, isn't on the complexity of the argument. The focus is on the structure of the argument. Are you able to get the logical structure right? And experience tells me that it takes most of us, and it certainly took me a long time to get the sense of what do I have to prove in order to prove something. That's not something that's not cookie cutter. You've got to build up experience in what constitutes a proof and being able to judge whether a proof is correct or not. Okay, let's go ahead and look at number 2 now. Let me jump first of all straight to the correct answer, and the correct answer is A. This says there are people and there are times at which you can fool those people. So you can fool some of the people some of the time. Remember, existence quantifiers are what we use in mathematics to capture the word some, or at least one. A little bit atypical in terms of what the word some means in everyday language. Okay, and here the way I've expressed it is there is a person and there is a time such that you cannot fool that person at that time. Okay, there's a person and a time such that you cannot fool that person at that time, which is actually equivalent to saying you can't fool all the people all the time. Formally, you could take that part and you could rewrite it as it's not the case that for all x and for all t, fxt. It's not the case that you can fool all the people all of the time. Okay, but I wrote it this way because we're only asking for the equivalence. I'm not saying which is the closest way of capturing it. I'm just saying which is one's equivalence. Okay, let's look at part B. What does this, well, there's the first part were the same in all of these three. So the distinction is in the second part. So let's see what this one says. Can we express that in English? Well, it's tricky to express in English because of these American Melanoma Foundation type issues. I mean, you could say something like, oh, let's say you can't fool everyone. Let's try something like this, at some time or other. Well, for everyone, it's the case that you can't fool them at some time or other. I mean, really what it's saying is it's not the case for every person. There's a time when you can fool them. Okay, so you can't fool everyone at some time or other. Yeah, that's sort of, I'm I can't think of a way of saying this that really makes that reads well in English, and yet which really captures this. But hopefully it's clear what the thing means. It's not the case that for every person there's a time when you can fool them. Okay. To me that says the same, but you may interpret that one different, because this is one of these things like American Melanoma Foundation, that it's ambiguous, as natural language so often is. Okay, let's see again in the case of this one, what does this one say? It's not the case that there is an X and there is a T, so you should fool. This one I think is easy to say in English. Okay, it basically says you can never fool anyone. Okay, it's not, you cannot find a single person and a single time such that you can fool that person at that time. You can never fool anyone. So this one I'm very happy with. Okay, that one really captures it. And the smiley doesn't indicate that I think that's true. It indicates that I think that's a really clean interpretation of what that one means. Well, and number 4 doesn't arise because we've already found something correct. Well, questions 3, 4 and 5 were just truth table arguments. That was essentially revision material, so I won't go through those here. Let's just take a look at question 6, which when you first meet it looks as though it might be terribly deep, especially since we've seen this now after we've looked at things like square root of root 2 and square root of root 3. But actually this one, when you step back and think about what it says, turns out to be very simple. We simply observe that whenever n is a perfect square, in other words, it's the square of some integer, any integer, and there are infinitely many integers, so there are infinitely many perfect squares, then of course the square root of n is just k, which is rational. And that's all there is to that one. I mean, not only is it rational, it's a whole number. The point is there are infinitely many numbers n for which the square root of n is a whole number and hence rational, namely all the perfect squares. Okay, that's all there is to that. You don't really need to say any more. That's it. That shows that it's true and it tells you why it's true. And that's the proof. Because you were only asked really to sort of say whether it's true or false, but it was this that I was interested in. Can you construct a proof of its negation? Of it or its negation. That was really what it's about. It's all about proving things here. Okay. Well, finally, question 7 is one of these fallacious proofs. There's a whole range of these things, quite amusing. Usually they depend upon dividing by 0 in some disguised form. This one's different. Okay, so let's follow it through, because normally the point is just to find the mistake. We're clear that there's going to be a mistake because 1 doesn't equal 2. And indeed, one of the things I asked you to do was to find the mistake. But the focus here isn't so much on finding the mistake, it's on how do you grade this as a proof. And remember, when we're grading proofs, logical correctness is certainly part of it, so there's going to be some losses of grade here. But also it's about communication. Okay, so let's go through this one and just see how we would grade the thing. Okay. Well, for example, is it clear? Well, it's absolutely clear, so we're going to have to give 4 marks for clarity. This is very clear. There's a good strong opening. We start with the identity. 1 minus 3 equals 4 minus 6. Okay, both sides are equal to 2, so full marks for giving the opening. The conclusion is stated, so it's 4 marks for stating the conclusion. And reasons given, yes, absolutely. Adding 9 plus 4, 9 over 4 to both sides. This is completing the square to give you a perfect squares. Then we're saying is it factors, which it does. That's why we added 9 over 4 to both sides. Taking square roots of both sides, absolutely. Reasons, reasons, reasons. So in terms of the structure, this is wonderful. Now overall, I'm going to have to give it 0, right? I mean, that's clear because the thing is plain false. The question is, what do I give for logical correctness? Well, first of all, we need to identify where the error's occurring, right? And the error's here. It's in this line, because when you take square roots, then of course there are positive and negative square roots to be had. And in fact, the correct solution is to say the minus on the left-hand side, the negative root on the left-hand side, minus 1 minus 3 over 2. And it's the positive root you take on the right-hand side when you take square roots. So that's what you should have. In other words, 3 over 2 minus 1 equals 2 minus 3 over 2. In other words, a half equals a half. Okay, so no big deal there. I mean, that's nice. The world still exists. A half does equal a half, even though 1 doesn't equal 2. So the issue here was when you're taking square roots, there are two possible signs, and the one that makes it valid is the negative on the left and the positive on the right. Okay, so this is where the mistake is. The only question is, do we give partial credit for the fact that there's logical correctness everywhere else? This is a judgment call. I would say that these steps are so simple, it's just very elementary algebra, arithmetic, that at this level I'm not going to give particular credit for getting these bits right. And I'm going to say this is a big mistake. This is huge. Okay, when you take square roots, you have to take a plus or a minus. That's a mathematical mistake. Realizing not recognizing that you need to worry about the signs when you take square roots. So that's a big error from a mathematical point of view. So this grading that I've given it, which means I'm actually giving 16, means I'm giving no points at all on the mathematical correctness. I'm giving lots of credit on everything else. Now, if this was a mathematics course, I wouldn't be using this rubric this way. I would take account of these, but they would have less weight. I mean, these have all got the same weight, a maximum of 4. And that's because the focus of this course is on proofs and reasoning and communication, and these are important parts of that. The assumption in this course is that you already can do some mathematics, and so I'm not really grading you on that. I'm grading you on mathematical thinking and mathematical communication. So there's 0 marks here on the mathematics, but there's 4 marks on everything else. And this is the reason why I did this one. This is where everything is well laid out, but the thing is plain wrong. So it distinguishes between mathematical correctness and the mathematical thinking and the communication and writing a proof out correctly. Having said that, in this case, it's blatantly obvious that something's gone wrong. But very often in mathematics, professional mathematicians make mistakes buried in proofs. And because they're professionals, they can usually write things correctly. We learn as part of becoming mathematicians, we learn how to write things out, we give reasons. So in fact, this, although it looks absurd here, you often find that because mathematicians know how to lay things out well, results get published even though they're absolutely wrong. And when a result gets published, basically what that means is that the referee of the journal where it's published has graded it and said this is correct, this is absolutely correct. So, this is not an unrealistic situation in principle. When false results get proved, and when false results get published, that is, because they're never really proved, the false results get published, when what's going on then is that the referee has gone through it and thought everything's okay. Okay. Here it's dramatic because the answer's absurd. It's patently false. But this is actually not an unrealistic scenario. And so giving a high grade isn't it's not a bad thing. I mean, I'm doing this to emphasize the distinction between the various things we're looking at here. And this one, I think, makes it clear that there are other issues involved other than logical correctness. But as I say, if this was a regular mathematics course, I wouldn't be giving 16 out of 24. In fact, I'm not even sure I'd give any marks for this if a student came up for this, because this is really a big mistake. Okay, but within the context of this course, this is the kind of thing we're looking for in looking at mathematical thinking and mathematical proofs and communication. Okay, there we go. Well, that's the end of the problem set questions. But let me leave you with one more tantalising little puzzle. Well, you're probably familiar with the story of Archimedes, lived in Greece about 250 BCE or thereabouts, who was asked by the king to determine whether a crown he'd been given was actually made of pure gold or not, and that involved calculating the density. And he knew how to calculate, to find out the mass of the weight of the crown. But the question was, how do you calculate its volume? Now, Archimedes knew lots of mathematics for calculating volumes. Indeed, he'd invented a lot of that mathematics. He was able to calculate areas of circles and volumes of spheres and various other shapes like boxes and rectangles and pyramids and so forth. He knew all of that stuff. So he had a lot of mathematics at his disposal that he could have applied. But it didn't seem to work for something irregular like a crown, or at least not easily. But then one day when he's taking a bath, this is sort of the story goes, when he's taking a bath, he has this amazing insight. He says to himself, if I immerse the crown in water, it will displace some water. In fact, the amount of water it will displace is exactly equal to the volume of the crown. So if I collect the water when it spills out of the bath, and when I put a crown inside it, into the water, then I'll be able to just measure the volume of the water in a standard way, and I'll know the volume of the crown. And as that story goes, he was so impressed and tickled by his solution that he jumped out of the bath and ran stark naked through the streets crying out, "Eureka, Eureka," which is Greek for "I found it, I found it." Now, I've known lots of mathematicians. I certainly haven't known Archimedes, but I doubt if even a mathematician deep in the throes of solving a problem would run naked through the streets. However, I can imagine him being extremely pleased with himself and having a great adrenaline rush when he had that insight, because that's a great example of thinking outside the box. He knew lots of techniques for calculating volumes. He invented many of them. But on this occasion, he thought outside the box and found a really elegant solution that was different. And the puzzle I'm going to give you is very much along those lines, and it actually is about taking a bath. And here it is. If it takes half an hour for the cold water faucet to fill your bathtub, and an hour for the hot water faucet to fill it, how long will it take to fill the tub if you run both faucets together? Now this looks like one of those frustrating little word problems you get in high school. Okay, where you end up, you sort of say, let the rate of flow of the cold water be F, and then the T, and you write down some equations and you figure something out. Okay, and I'm sure you know how to do that. You can apply a standard technique for doing this kind of thing involving rates of change, and you get the answer. But you don't need to do any of that. You don't need to do any calculations at all in order to solve this one. If you think outside the box, you can answer it without doing any of those calculations based on the rates of flow or anything like that. You simply have to think of the problem a different way. If it helps, if you're inspired by the Archimedes story, you might want to run a bath and get in the bath and see if you can come up with the idea then. I must admit from personal experience that a lot of my best ideas in solving mathematical problems and proving mathematical theorems throughout my career have actually been obtained when I've been sitting in a bath or shortly after taking a bath. There's something so relaxing about getting in a bath that it frees the mind to come up with these out-of-the-box solutions. So this isn't really about, do you know the standard methods? You probably do. This is about, can you think about this in a different way that allows you to solve it without really doing any arithmetic whatsoever. Okay, well, with that hint, I'll leave you to it. Enjoy. How did you get on with assignment 7? In this lecture, I'll say something about how to prove statements that involve quantifiers, which is true for almost all mathematical theorems. Universally quantified statements of the form, for all natural numbers n, some property an holds, where the quantification is over all natural numbers, are often proved by a method known as induction. I'll explain the method of induction with some examples from number theory. Number theory is one of the most important branches of mathematics. It studies the properties of the natural numbers, 1, 2, 3, etc. We'll look at some elementary parts of the subject in later lectures, but for now it provides good examples of induction proofs. But first, let's look at how we might prove an existence statement. We want to prove there exists x such that a of x. The obvious way is to find an object A for which A of A. For example, to show that there's an irrational number, just prove that square root of 2 is irrational. Which we did. Unfortunately, this doesn't always work. Sometimes we use indirect proofs. For example, I worked through that problem about the cubic equation, where we showed that there was a point on the x-axis where the curve crossed it, and hence that the cubic had a solution. We never found the solution, we just showed that one existed. Let me give you a really fascinating example of an indirect proof. I'm going to prove that there are irrationals, r and s, such that r to the power s is rational. That actually came up in assignment 7, if you remember, and I promised then that I would look at this later. Well, now is that later. The proof involves considering two cases. Case 1, if the square root of 2 raised to the power square root of 2 happens to be rational, we can take r and s both equal to square root of 2. Then, by the assumption that square root of 2 to the square root of 2 is rational, we've shown that there are numbers r and s which are irrational, with r to the power s rational. Well, if case 1 isn't the case, then we must be in case 2, which is where root 2 to the root 2 is irrational. In which case, take r equals square root of 2 to the square root of 2, and s equals square root of 2. And if we do that, then r to the power s is root 2 to the root 2 all to the root 2, which by the way that exponents work is root 2 to the power root 2 times root 2, which is root 2 squared, which is 2. And 2 is rational. So again, we've proved that there are irrationals, r and s, such that r to the power s is rational. Taken together, case 1 and case 2 prove the theorem. I really like this example. It's not just clever, but it's cute. And it's cute because of the way it works. We really don't know whether this number, root 2 to the root 2, is rational or irrational. It's probably irrational, actually, but the point is we don't need to answer that question. We just look at the two alternatives. If it does happen to be rational, seems weird, but if it does happen to be rational, then we can find irrationals r and s with r to the s rational this way. On the other hand, if root 2 to the root 2 is irrational, which probably is the case, but again, we don't need to know that, then we take r to be this number, s to be that number, and then r to the s is 2, which is rational. So we don't know, officially, which one of these is the case, and more to the point, we don't need to prove which one of these is the case. We simply look at the two alternatives, and depending on which alternative we're in, we take different irrationals r and s, with r to the s being rational. So the choices of r and s are different in the two cases, but because these two cases exhaust all possibilities, this number is after all either rational or irrational, then this proves the result. By the way, this is known as the method of proof by cases. And it's a method that's used a lot in advanced mathematics. Pretty neat, huh? Well, now let's take a look at how we might prove a statement involving a universal quantifier. Suppose we wanted to prove a statement for all x, a of x. One way is to take an arbitrary x and show that it satisfies a of x. For example, to prove that for all n there is an m bigger than n squared, where the variables m and n range over the natural numbers. Well, this is a pretty trivial example, but I want to focus on the method that you would use to handle the two quantifiers in a statement like this, where in particular the first quantifier is a universal quantifier. Let n be an arbitrary natural number. Set m equal to n squared plus 1. then m is bigger than n squared. And this proves the statement, there is an m bigger than n squared. And it follows that the statement, for all n there is an m bigger than n squared, is true. Okay, well, as I said, this is pretty trivial. Let's just see what's going on in terms of the logical reasoning. You want to prove a statement involving two quantifiers of the form, for all n there is an m bigger than n squared. What we're going to do is eliminate one quantifier by replacing it by an arbitrary natural number. Now, by arbitrary, I mean we make no assumptions at all other than the fact that it is a natural number. The argument will have to hold for any natural number whatsoever, because we're trying to show that this is true for all n. So we pick an arbitrary one. Then we carry out some reasoning to verify the rest of the formula. Okay, when we eliminate that for all n, we're trying to prove that there is an m bigger than n squared, which is this statement. Now, in this case, it's a trivial argument. We just square n, add 1, and let m be that number. So we explicitly find an m that satisfies this property. In practice, you're probably going to have to do a lot of work here. With a more significant example, there could be several lines or even pages of argument involved at this stage. But the point is, you eliminate the first quantifier by picking an arbitrary n, then you carry out some reasoning to prove the rest of the formula, which is this thing here. And when you've done that, because the argument works for an arbitrary natural number, it follows that you've proved it in this form. The for all n has been handled by reasoning with an arbitrary natural number. So we've taken away one of the quantifiers, carried out some reasoning, and proved the result. But let me stress that this works because the n that we pick is arbitrary. Well, another approach would be to use the method of contradiction. To prove for all x a of x, assume not for all x a of x. This is equivalent to exists x not a of x. Well, let C be an object such that not a of C. Notice that this isn't an arbitrary object. It's a specific object, admittedly an object whose identity we may not know, that is guaranteed to exist by this. The point is to prove this universal statement, we began by assuming its negation. Its negation gives us an existential statement, and that tells us that there will be some object, a specific object, for which not a of C. Now we've got a starting point to carry out a proof to derive a contradiction. Now reason with C, together with the fact that not a of C, to derive a contradiction. Now, the exact reasoning you use will depend upon what the statement A says. But the general pattern is this. You want to prove for all x a of x, and you're going to use contradiction. So you assume not for all x a of x. That's equivalent to exist x not a of x. And that tells you you can find an object, or at least you know that an object exists for which not a of C. And then, if you can, you reason with that object using the fact that not a of C to derive a contradiction. Okay, again, we'll see examples of this later on. I'm just giving you the general overview of the way these arguments work. So, as in the previous case, if this looks a little bit mysterious, it'll become clearer, I hope, when we look at some specific examples later. In fact, at this stage, you might want to look back at assignment 7 and see what was going on there in the light of what I've just said here. And before I let you go, let me give you a little quiz. Well, the correct answer is no. This is not a valid proof. The point is, picking a positive rational P arbitrarily is not the same as letting P be arbitrary. The choice of P may indeed be arbitrary, but once you've made it, you've got a specific P. And we've even said what it is. That's actually different from saying let P be arbitrary. An arbitrary choice of P leads to a specific P, which you may have chosen arbitrarily, but you might have been unfortunate in your choice. You might have chosen a P that just happens to make something happen without there being any specific reason. It's a subtle point, I know, but it's an important point, so you really need to sort this one out. Letting P be arbitrary is not the same as picking in an arbitrary fashion a specific P. The point is that P is specific. Its choice may have been arbitrary, but once you've made it, it's specific. In contrast, when you argue with an arbitrary P, you don't know anything about the P. You certainly wouldn't know that it was equal to 0.001 or whatever. You may need to think about that one a little bit longer, or talk it over with some of your colleagues. Now let's look at proof by induction. This is the special case where we're proving universal quantified statements where the quantifier ranges over the natural numbers. For example, suppose I want to prove that 1 plus 2 plus etc. 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 plus n equals a half n plus 1. So the sum of the first n natural numbers is a half times n plus 1. Well, if you're meeting this problem for the first time, a smart thing to do is to begin by checking the first few cases, just to see, first of all, to see if it's true for the first few cases, and to try and get a sense of what's going on. So, if n equals 1, what do we get? Well, then we've just got 1 here, and putting n equals 1 into the formula, we have a half times 1 times 1 plus 1, which is a half, times 1 times 2, which is 1, and indeed 1 equals 1. So it's true in the first case. In the second case, n equals 2, what do we have? We have 1 plus 2 is the left-hand side, equals, put n equals 2 here, we get a half times 2 times 2 plus 1, which is a half times 2 times 3, a half to, so we've got 3, and 1 plus 2 does equal 3. So the formula is correct for n equals 2. We might want to try n equals 3. What do we get then? We get 1 plus 2 plus 3 equals a half, 3 plus 1, which is a half, 3, 4, which is 6, which is correct. So the formula checks out for the first 3 cases, and we might want to do a couple more cases. But at least that gives us some sense of what's going on. By doing this, we understand what the formula, we understand what the equation's saying. Now, so far, this isn't a proof. This is just checking the first 3 cases. In fact, you've got to be very careful about jumping to conclusions based on the first 3 or 4 cases. So let me just stress that. This is not a proof. Okay, let me stress it again. Beware of jumping to conclusions. And to drive this point home, let me give you an example where if you jump to conclusions, you'll come to the wrong conclusion. Consider the formula Pn equals n squared plus n plus 41. If you start working out values for this formula, you'll find something rather interesting. You find that all values of Pn for n equals 1, 2, 3, etc. are prime numbers. Well, not quite. That's true until you reach n equals 41. And when you get to 41, you find that P of 41 works out at 1681, which is 41 squared. So the first series of values for n equals 1, 2, 3, etc., all the way up to 41, which is well beyond the number of cases most people would try out by hand, you find you've got a prime number. But if that leads you to believe that this formula generates primes for every n, then you're going to be wrong, because when you get to n equals 41, it's no longer prime. This example, by the way, is due to the famous Swiss mathematician Leonhard Euler in 1772. And it's a cautionary tale telling us not to jump to conclusions based on numerical evidence. Nevertheless, it's always a good idea, or it's often a good idea, to begin looking at a problem by working out a few cases. Not only do you get an understanding of what the formula is about, but you can sometimes, when you work out a few cases, you can find a pattern. In this case, there actually isn't much of a pattern to find. You work out the values and you just get numbers, and it turns out that the first 40 of them are primes. But in this case, if you look at what's going on, after, even if you did maybe a couple more, n equals 4, n equals 5, you'd begin to see a pattern of what's going on, how the two parts of the formula are combining, what's happening to the half. The half is dividing into the second one here, the first one here, the second one there. And after you've done a few cases, you can often find a way of capitalizing on the pattern that's there in order to produce the proof that I'll show in a minute. So induction proofs can often be derived by looking at the first few cases, seeing what the pattern is when you start plugging the numbers in, and then actually building a correct, rigorous proof. Okay, so the next step now is to begin with this numerical evidence and our understanding of how the formula works in order to come up with a rigorous proof of the fact that this formula holds for every n. The method of induction depends on a principle known as the principle of mathematical induction. Okay, and here's what it says. Suppose you want to prove a statement for all n, A of n. Establish the following two statements. 1, A of 1. That's known as the initial case, or the initial step. 2, prove the following statement. For all n, for all natural numbers n, if A of n is true, then A of n plus 1 is true. That's known as the induction step. Now, intuitively, this gives the statement for all n A of n as follows. By the initial step, step 1, A of 1. If we now apply the induction step in the special case where n equals 1, we have A of 1 by the initial step, and that yields A of n plus 1, which is A of 2. So by 2, or by step 2, A of 1 yields A of 2. So from A of 1, we can conclude A of 2. Okay, we begin by proving the initial step. So if we've proved A of 1, then we know that one's true. We can now apply the induction step in the special case where n equals 1. And having proved this, if we have A of 1, we can conclude A of 2. Then we can do the same thing again. Once we've got A of 2, we can put the 2 in here and conclude A of 3. So by A of 2, and the induction step. We can conclude A of 3, etc., all the way through the natural numbers. So it's a little bit like taking a row of dominoes and you knock the first one down, and providing the dominoes are close enough so that when one gets knocked down, the next one gets knocked down, then once you start to topple the row of dominoes, the first one goes down, then the first one knocks down the second one knocks down the third one knocks down the fourth one knocks down the fifth one, and so on and so on and so on, all through the natural numbers. So you get a row of dominoes falling down. So this basically says knock the first domino down and put the dominoes close enough together so that when one falls, the next one falls. Okay, that intuitive explanation is fine as far as it goes, but that's certainly not a rigorous demonstration of this method. The fact that proving these two together does yield that universally quantified statement, that's actually quite a deep result of mathematics. Okay. And let me just stress that. You need an axiom or a principle to make this work, called the principle of mathematical induction. The principle of mathematical induction is what tells you that steps 1 and 2 above, yield for all n A of n. Okay, now we have the method of induction laid out before us. I'll apply it in order to prove that identity that we looked at a moment ago about the sum of the first n natural numbers. So I'm going to prove a theorem now, that for any natural number n, 1 plus 2 plus 3 plus yada 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 plus n is a half n plus 1. I'm calling it a theorem because I'm going to give a rigorous proof. I'm going to use a method of mathematical induction. And since one of the purposes of a proof is to explain why something is true, it's usually good form to indicate to the reader the method you're going to use. It orientates the reader to what's going to come next. And I'm using a standard method here, namely mathematical induction, so it's good form to indicate that that's the method I'm going to use. Well, I have to do two things. I have to show that this is true when n equals 1, and then I have to show that if it's true at n, it follows at n plus 1. So the first step is to say that for n equals 1, the identity reduces to, well, n equals 1 on the left-hand side, I've just got 1. Put n equals 1 on the right-hand side, I've got a half times 1 times 1 plus 1, which is a half times 1 times 2. And indeed, the left-hand side does equal the right-hand side. So that's true. Since both sides equal 1. So we've proved the first step. Incidentally, you may have noticed that I referred to this not as an equation, but as an identity. And the reason is that an equation is something that you solve to find the value of a variable, either x in the case of a real number equation, or n in the case of a natural number equation. But this isn't an equation that you solve for n. This is an identity. It's something, it tells you that the two sides are always equal. And we use the word identity to refer to an expression like this that claims or that states that two things are equal for all values of n. So these two sides are identically equal. So the correct terms are an identity for something like this, an equation for something that you solve. Having said that, like many mathematicians, in practice I'm sometimes not particular in the words I use. If you caught me talking to my colleagues, you might find me using the word equation where I mean identity, possibly even using the word identity where I mean equation, although that one's less likely. But strictly speaking, an equation is something you solve. An identity is something that states that two things are always equal. Okay, let's move ahead. We've proved that the result is true at n equals 1. The next step is the induction step. So I'm going to assume the identity holds for n, i.e. I'm going to assume 1 plus 2 plus n equals a half n plus 1. And let me note now, and I'll put this in brackets, I want to deduce 1 plus 2 plus plus n plus 1 equals a half n plus 1 n plus 1 plus 1. Okay, that's just a note for myself to indicate the target I'm aiming for. And the challenge now is to start with what I know and deduce where I want to get. Well, how can I get this from this? Well, one way would be to add n plus 1 to both sides of that identity, which means that I'd get the left-hand side here, and then hope that when I work out the right-hand side, having added n plus 1, I end up with this expression. Okay, so let's add n plus 1 to both sides of, let me call it star. So star is the identity I'm assuming. Let me add n plus 1 to both sides of that. That gives me 1 plus 2 plus n plus 1 is a half n plus 1 plus n plus 1. So I've now got the left-hand side of what I want to prove. I need to show that the right-hand side is the right-hand side of the thing I want to prove. So I need to show that that is the same as that. Well, let's just see what happens. I can take the half out as a common factor. So I've got a half into n plus 1 plus 2 into n plus 1. And that equals a half n squared plus n plus 2n plus 2, which is a half n squared plus 3n plus 2. And this factors. This is a half n plus 1 n plus 2. But that's the same as that. I can write it explicitly, if you like, as a half n plus 1 n plus 1 plus 1. Which is the identity with n plus 1 in place of n. Hence, by the principle of mathematical induction, the identity holds for all n. And we're done. We've proved the initial step, a simple matter of observation, and we've proved the induction step by a fairly simple algebraic argument. And that's it. That's mathematical induction in practice. Where this screen came up about a quarter of an hour into the lecture, did you spot anything wrong with it at the time? Can you see anything wrong with it now? Well, the problem's in here. This isn't the polynomial I meant to write down. What I meant to write down here was the polynomial p of n equals n squared minus n plus 41. I got the sign wrong. And for this, it is the case that for all values of the polynomial for n equals 1, all the way up through n equals 40, it's prime. Okay, all the way up. And then p of 41, if you put that in, it's 41 squared minus 41 plus 41, which is 41 squared, which is this number here, 1681. Let me call that p sub minus to indicate that there's a minus sign here, because the polynomial I wrote down, I'll call p plus of n, was this one, plus n plus 41. That one is actually prime for n equals 1 through 39. And if I put 40 in there, let's put the minus in there to distinguish it. If I put 40 in there, I get what? I get 40. N squared plus n is n times n plus 1. So it's 40 times 40 plus 1 plus 41, which is 40 times 41 plus 41. So I've got 40 times 41 and then another 41. That means I've got 41 lots of 41, which again is 41 squared equals 1681. These are sort of the same polynomial when you look at it in terms of the behaviour here, if you just see what's going on. They were both actually due to, well, actually, well, I'm not sure historically whether Euler wrote them both down, but clearly once this had been discovered, you're just manipulating them. And what I did when I was giving the lecture, this is spontaneous. By the way, almost all of these lectures are spontaneous. They're not meant to be polished lectures. I mean, I'm familiar with the material, so it sometimes looks as though I'm just sort of reading it from a book. But if I am reading it from a book, it's a book in my head from having taught it for many years. Basically, what I'm recording is spontaneous, and I just pulled this off from my memory, and I confused two things. I knew that it didn't really matter what the sign was, but it does make a difference as to where it stops being prime. If you pick the negative sign, it's prime all the way up to 40. If you pick the positive sign, it's prime all the way up through to 39. So it was a technical error, but in principle it was correct. And it's certainly, whichever one you pick, gives a wonderful example of the fact that just because you have a repeating pattern, it doesn't mean to say something's true for all n. And remember that I introduced this as an illustration of caution when I was talking about induction proofs. Okay, well, what happened was the first time I gave this course, many students found the mistake, and I thought it was good to leave it in the second time I gave the course so that students would have a further chance of finding the mistake themselves. It's always fun to find mistakes. This time I decided to leave it in, but put in a quiz at the end just to prompt anyone that hadn't noticed the mistake that there was actually a mistake. Okay, so now you know what's going on here, and you've seen me make a wonderful mistake in public, which is something that all good mathematicians should do. Okay, well, that brings us to the end of 8.A, lecture 8.A. Let's move on to lecture 8.B now. Where the correct answers are this one, this one and this one. If you check back at the description I gave of the method of induction, you shouldn't have any difficulty realizing why this is the correct answer, why this is the correct answer, and why this is the correct answer. So if you got any of these wrong, you definitely need to go back and look at the lecture again and make sure you really understand induction. It's a very important technique in mathematics. Well, let me give you another example of an induction proof now, and this time I'll lay out the proof in a way that makes explicit the connection between the argument I give and the description of induction I gave a moment ago. And the example I want to give is the following theorem. Well, calling it a theorem is actually a bit of a stretch, but here's what I'm going to show, that if x is a positive real number, then for any natural number n, 1 plus x to the n plus 1 is bigger than 1 plus n plus 1 x. Okay, this result is not going to set the mathematical world on fire, but it is a good example to illustrate the way mathematical induction works, and in particular to connect the argument that I'm going to use to the earlier description I gave for mathematical induction. So here's the proof. Well, I'm going to begin by stating the method I'm going to use. It's mathematical induction. Since one of the purposes of proofs is to explain why something is true, it's always a good idea to begin by stating the method you use. That orientates a reader to the argument that's about to come. And to connect it to the description I gave of induction before, I'm going to let A of n be the statement 1 plus x to the n plus 1 bigger than 1 plus n plus 1x. So by induction, I'm going to prove for all n, A of n. Well, the first step is to prove A of 1. And A of 1 is the statement one plus x squared is bigger than 1 plus 2 of x, plus 2x. We put n equals 1 here, we'll get 1 plus x squared greater than 1 plus 2x. Is this true? Well, the answer is yes. It's true by the binomial theorem, which tells us that 1 plus x squared is equal to 1 plus 2x plus x squared, which is bigger than 1 plus 2x, because x squared is strictly positive. Notice that x is positive, so in particular x is non-zero, hence x squared is strictly positive, hence we have a strictly positive term here, hence that expression is strictly bigger than 1 plus 2x. So A of 1 is true. The induction step involves proving for all n, an implies a n plus 1. Well, how do we typically prove a statement like this? We pick an arbitrary n and prove an implies an plus 1. And how do we prove an implication like this? We assume the antecedent and deduce the consequent. Well, an is the statement 1 plus x to the n plus 1 greater than 1 plus n plus 1x. And an plus 1 is the statement 1 plus x to the n plus 2 is greater than 1 plus n plus 2x. So the induction step boils down to assuming this and deducing that from it. So I'm going to focus on this now, and I'm going to begin by looking at the first expression. 1 plus x to the n plus 2. In order to use the induction hypothesis, I'm going to pull out one of these terms and write that as 1 plus x times 1 plus x to the n plus 1. And by the induction hypothesis, 1 plus x to the n plus 1 is bigger than 1 plus n plus 1x. And that equals 1 plus n plus 1x plus x plus n plus 1x squared, which equals 1 plus I've got n plus 1x and another x, so altogether I've got n plus 2x plus n plus 1x squared. And this is positive, so that expression is strictly bigger than 1 plus n plus 2x. And that part of it, the part here connected with this, is this. In other words, this proves a n plus 1. And the theorem follows by induction. Okay, I've laid this out in gory detail here, but my purpose was to connect the kind of argument that you give when you do an induction proof with the description of induction that I gave a moment ago in terms of predicates an. Okay, so this is, so what I've been doing here is really emphasizing how my earlier description of induction connects to an actual proof. If you take out all of the pedagogic stuff that I've put in here, you've really got a 2 or 3 line argument. I mean, it really boils down to that step and then this step here. Those are the 2 key steps of the induction proof. Okay, well, there we are. Let me summarize how induction works. You want to prove that some statement an is valid for all natural numbers n. You first prove a1. That's usually a matter of simple observation. The next step is give an algebraic argument to establish the conditional a of n yields a of n plus 1. Usually you assume a of n and then you deduce a of n plus 1 from it. And typically you do that by looking at the form of a of n plus 1, manipulating it into such a form that you can apply a of n in order to carry out an argument. In other words, reduce a of n plus 1 to a form where you can use a of n. And conclusion, by the principle of mathematical induction, this proves for all n a of n. Occasionally, you might have to work pretty hard to establish the first case. Generally, this step is easy, and this one is where you have to put in the effort. But neither of these 2 steps on their own constitutes an induction proof. It's the whole package that constitutes induction. My illustration of induction as knocking over a row of dominoes, while it's intuitively helpful, obscures the fact that this principle of mathematical induction is actually a pretty deep principle of mathematics. The reason it's deep, by the way, is because this is talking about an infinite collection. It's talking about all of the natural numbers, and there are infinitely many of them. And the moment you start talking about infinity in mathematics, there are subtleties and complexities lurking on the wings. Incidentally, that's why we usually complete a proof by writing a sentence something like, by the principle of mathematical induction, the result follows. Because this is heavyweight. And it's usually good practice and a shrewd move to mention a heavyweight if there's a heavyweight in the room. Okay, well, that's induction. I'd better tell you about a fairly common variant of induction. We sometimes need to prove a statement of the form for all n greater than or equal to n0 a of n, where n0 is some fixed number, 5 or 10 or 20 or a million or something. In this case, the first step is to verify a of n0. A of 1 may not be true. In fact, it's usually the case that when we are trying to prove something of this form, the reason we have an n0 as the starting point is precisely because the result doesn't hold at the beginning. We have to go out some way through the natural numbers until the result starts to hold. General induction starts at 1. This variant starts at some point beyond 1. But other than that, the argument's essentially the same. In particular, the induction step is to prove for all n greater than or equal to n0, a of n implies a of n plus 1. In fact, the example of induction I want to give you next uses this variant of induction. And that example is part of a famous result of mathematics called the fundamental theorem of arithmetic. Before I do, let me give you a quiz. Is 1 a prime number? Okay, I know this isn't the focus of the course, but there's a lot of confusion about this, and if we don't clear it out of the way now, it's going to keep haunting us as we go through the material that's coming up. Now, you know, I could, of course, simply give you the answer, and in previous times when I've given this kind of course, both in a MOOC and elsewhere, I've given students the answer, but it's one of these things that people just don't sort of really pay attention to, and then it comes up again when there are homework exercises and discussions. So what I'm going to do is give you this as a quiz. So I want you to answer whether this is a prime number or not, whether 1 is a prime number or not. Okay? Well, the answer is 1 is not a prime number. And the reason is the definition. Here's the official definition of a prime number. It's a positive integer n greater than 1 whose only exact divisors are 1 and n. That's all there is to it. It's a definition. So from now on, please be very careful that you really know the definition of a prime number. 1 is not a prime number. Incidentally, whilst we're on the topic of getting definitions cleared out, let me make another remark. 0 is not a natural number. Again, this is by definition. 0 is an integer, but it's not a natural number. Historically, the natural numbers are the counting numbers, and people historically started counting at 1, 2, 3, etc. 0 was very much a Johnny-come-lately. Okay, so these come around all the time. They cause confusion. It's unnecessary confusion, so I thought I would get it out of the way now, and I would draw your attention to this definition by putting it in as a quiz. Okay, now let's go on to what I was planning to do. Here's the part of the fundamental theorem of arithmetic that I want to prove. And it's the following theorem. Every natural number greater than 1 is either prime or a product of primes. Now we have to use that variant of induction for this one because it's not true at n equals 1. The theorem only holds for n equal to 2 or more. In fact, 1 is the only number for which it doesn't hold. So we're only just in the variant. We just missed 1 point. But we have to start at n equals 2. In other words, the first step of the induction is going to involve looking at n equals 2, not n equals 1. But with that one change, it's going to be an induction proof. So proof will be by induction. Well, the induction statement an is, well, you might think it's going to be n is either prime or a product of primes. Okay, based on the examples we've seen so far, you might imagine that A of n, the induction statement, is that n is either prime or a product of primes. Well, that turns out not to be the case. That just doesn't work. We have to pick something else. And this is what we pick. For all m, if 2 is less than or equal to m is less than or equal to n, then m is either a prime or a product of primes. So the induction statement, A of n, talks about all the numbers between 2 and n being prime or products of primes. So it's a sort of cumulative statement, if you like. As we go up through the natural numbers, we iterate on the cumulative fact of things being primes or product of primes. And the induction proof establishes that an is true for all n bigger than 1. So we have to start with the first step, namely n equals 2. A of 2 says what? Well, if n equals 2, there only is one m between 2 and n. So the universal quantifier here is essentially vacuous. I mean, it's just a special case. It's a degenerate case. There is just n equals 2. So this statement, when n equals 2, simply says 2 is either prime or a product of primes, which is true. 2 is a prime. Now we're going to assume A of n and deduce A of n plus 1. Well, A of n plus 1 is going to talk about all numbers m between 2 and n plus 1. So let's look at one of those m's. Let m be a natural number, 2 less than or equal to m, less than or equal to n plus 1. Well, if m is less than or equal to n plus 1, m is either less than or equal to n, or m is equal to n plus 1. If m is less than or equal to n, then by A of n, m is either a prime or a product of primes. The only other possibility is that m equals n plus 1. Well, if n plus 1 is prime, then m is prime. So what happens if m equals n plus 1 and n plus 1 is not prime? Then there are natural numbers pq such that 1 less than pq less than n plus 1 and n plus 1 equals pq. If n plus 1 is not prime, then it can be obtained as a product of two smaller numbers. Not being prime means you can find two smaller numbers whose product equals the number. Two smaller numbers other than 1, that is. So this is just a definition of not being prime. Well, since 2 less than or equal to p and q less than or equal to n, by an, p and q are either primes or products of primes. These two numbers p and q are less than n plus 1, so they're less than or equal to n. That means these numbers are m's that fit into the induction hypothesis. They're less than or equal to n, so by A of n, each of these is either a prime or a product of primes. But n plus 1 is a product of them. So n plus 1 is a product of two numbers, each of which is either a prime or a product of primes. Hence n plus 1 is a product of primes. The theorem follows by induction. if you look back through this proof now, you'll see why we took our induction statement to be this somewhat more complicated looking statement. We wanted the induction statement to talk about all the numbers up to and including n being either prime or products of primes, so that when we went through the proof and we came down to a pair of numbers like this, we could immediately apply the induction hypothesis A of n in order to conclude that each of those two were either prime or products of primes, and therefore that the n plus 1 was either a prime or a product of primes. Incidentally, formulating induction statements that are cumulative in this fashion is quite common. It's often the case that in induction proofs you end up dropping down to some number or some pair or group of numbers smaller than the one you've got and needing to apply the induction hypothesis to those smaller numbers, as we did here with P and Q. Okay, how did you like that one? Okay, so now you know about induction. And with induction, we're starting to get into some serious university level mathematics. Though the general idea is simple enough, if you can always go one more step, then you will eventually reach every natural number. In practice, it can require a lot of effort and ingenuity to construct an induction proof. See how you get on with assignment 8. Well, assignment 8 was really quite difficult, I think. On the other hand, looking at the discussions on the forums, I think many people found it difficult because they hadn't yet made this transition to doing mathematical thinking. They were trying to do something that wasn't really required. This was very definitely the case with this one. Remember, the things I keep repeating are that one of the essences of mathematical thinking is that you first of all, you ask yourself, what is this asking me? What do I know? What does it tells me? What kind of objects is it talking about? And what do I need to do in terms of what's my target? So you have to stop, you pause, you reflect, you think about it. What you don't do, at least at the beginning, is say, does this remind me of a problem I've solved before that I can just instantly apply that previous technique? Because that can lead you in a completely the wrong direction. For example, there are various words here, and in high school, a good strategy was look for key words and try to map them into techniques. But it really isn't a good strategy in terms of advanced mathematics. Okay, there are many questions, many problems we have about perfect squares that are about the natural numbers. Okay, so what? This isn't about the natural numbers. This is about the integers. Completely different set of numbers. So, well, not a completely different set, it's a larger set of numbers. So this is about the integers. And the fact that some of the words are often used in discussions about the natural numbers, well, so be it. I mean, words get used for all sorts of contexts. Okay, so this is a question about the integers. And if it's about the integers, then why don't we just take m equals n equals 0. Then m squared plus mn plus n squared equals 0, which is 0 squared, and we are done. Folks, this is not a trick question. This is a question that gets at the heart of mathematical thinking. And the heart of mathematical thinking isn't knowing a ton of techniques from mathematics. The heart of mathematical thinking is, what do I know and what do I need to do with what I know? And what am I talking about? Stop, slow down, reflect, think. Mathematical thinking at this level is not a sprint. All of the techniques you taught in were taught in high school were very good for succeeding in high school, and they certainly leave you with a lot of valuable skills. But we've been there, done that. If we're beyond the high school, if we've mastered that, then we're trying to do something else. High school sort of teaches you how to lay bricks. What we're doing now is saying, how can I take all of those bricks, which are valuable things to have, and use them to build a house? We're now going from being bricklayers to architects. We certainly need all of those bricks. I am definitely not knocking high school, right? We use the stuff all the time, but that was providing us with the basic tools. Now we're learning how to make use of those tools. Okay, that's what mathematical thinking is about. And sometimes we need a lot of tools, and sometimes we can get by with something very simple because we just ask ourselves, what am I trying to do now? And we're not getting seduced into thinking that this is just another variant of something we've met before. think of every problem as a new problem. Then you'll find that things get much more doable because you'll be focusing on thinking, not applying techniques. Okay, that's the end of my sermon. Well, it's not really the end of my sermon because that's what the whole course is about. But let me just move on now to question 2. And in this case, you probably haven't seen anything quite like this before. So you have to start by asking yourself, how could it happen that the answer B was a perfect square? I mean, just how could that come about? What kind of thing must happen? Well, let's just write it this way. How can we have mn plus 1 equal to p squared for some p? Well, at this point, one of those bricks that I was taught in high school becomes really useful. Because if mn plus 1 equals p squared, that means mn equals p squared minus 1. And one of the bricks I had drilled into me in high school was that p squared minus 1 is p minus 1, p plus 1. So what we're about to do is take something that was drilled into us in high school and make clever use of it, okay? Because if mn is p minus 1, p plus 1, then we could have m equals p minus 1 and n equals p plus 1. In that case, p would be m plus 1. Remember, m is the number we're given. We're trying to find an n. And I'm just using this to say, what could that n be? What must that n look like? So given an m, we'd be able to take p equals m plus 1, and then from this one, n equals p plus 2. And now we found the n. Is m plus 2. Whoops, m plus 2. Okay? P plus 1. P is m plus 1, and n is p plus 1. So n is m plus 1. So given the m, we've already found the n. So given n, let's just summarize it now. Given m, take n equals m plus 2. Then mn plus 1 equals m plus 2 plus 1, which is m squared plus 2m plus 1, which is m plus 1 squared. So we've answered the question. We've said that given an m, take n equals m plus 2, then mn plus 1 is m plus 1 squared, which is a perfect square. Now, if I hadn't gone through this, it would have appeared that this was a rabbit out of a hat trick. And unfortunately, it's a consequence of the way that mathematicians often write their papers, that they don't include all of the reasoning, they just give you the conclusions. This would be a relatively simple example, but if I had simply said, given m, why don't we take n equals m plus 2, you would have said, how on earth did he come up with that? What made him think of that? You know, and I look as though I've got some kind of magical ability. No, I don't. I just went in and said, well, how could I possibly get to that answer? And then it was just something I learned in high school. Okay? So, you know, one of the techniques is just say, how could I possibly get the answer that I'm asked to find? Now, I'm couching this in terms of classroom questions, but the same issue arises when you're dealing with mathematical problems in the real world. Look at the problem. What does it tell you? What do you have to do? How can I get the answer that I'm going for? So this might be a simple classroomy type example, but it has many of the elements of good mathematical thinking. And in this case, it was, how can that answer possibly arise? And as soon as I sort of start to look at that, it just drops out. Okay? Recognizing that was the entire key to the thing. Once you've done that, straightforward. Okay, let's move on and look at the next one. Question 3. Well, question 2 is another one of these things that when you first meet it, you think, wow, this is asking me for something really deep. How could I possibly come up with a quadratic, all of whose values are composite? How could I guarantee that all of the values are composite? Sounds as though it's going to be really deep. But no, if you sort of just take a breath, sit back and say, how could it happen that numbers are composite? Well, if they're composite, they have to be the product of two other numbers. Okay, wait a minute. Why don't we just take, if that's going to always be the product of two whole numbers, let's make it the product of two whole numbers. And lo and behold, that is indeed of the form n squared plus bn plus c, where b and c are positive. That's all there is to it. We just wrote one down instantly. We didn't have to prove that one exists. We did prove it, but we did it by just writing one down. And all we had to say to ourselves is, no, this sounds complicated, but no, all it means is that the values are products. And quadratics are products of things. So we just write it. We explicitly make it a product of two things. The value will always be the product of two numbers, n plus 1 and n plus 2. And it's for all positive integers. So we'll have maybe 2 and 3 or whatever. So these are always greater than 1. So this thing is composite. N squared plus 3n plus 2 is always composite. That's it. Didn't involve any advanced machinery. Just thinking about what the problem asks us to do. Very similar with this one. You know, it sounds deep. Oh, it's about the Goldbach conjecture, a problem that's been around for hundreds of years, hasn't been solved. How on earth can we do anything with the Goldbach conjecture? Well, the answer is just look at what it tells us and ask us what we can do with it. And first of all, we observe that this is talking about numbers n bigger than 5 that are odd. Well, if n is an odd number bigger than 5, then n is of the form 2k plus 3, where k is bigger than 1. I mean, normally we think of odd numbers as being of the form 2k plus 1. But because I'm looking for prime numbers here, I'm going to write it as 2k plus 3. And I can do that because n is bigger than 5. So for numbers bigger than 5, any odd number bigger than 5 is of the form 2k plus 3, where k is bigger than 1. Well, in that case, since 2k is bigger than 2, because k is bigger than 1, 2k is an even number bigger than 2. So by Goldbach's conjecture, 2k equals p plus q, where p and q are primes. In which case, n, which is 2k plus 3, is p plus q plus 3. The sum of 3 primes. We're done. Actually, it wasn't difficult at all. Once we sort of thought about what it says, all of the complexity is in this unsolved problem, Goldbach's conjecture. If we assume Goldbach's conjecture, which we're allowed to because it says if that's true, then every even number bigger than 5 is the sum of 3 primes. One of which, in the case of our proof, is 3. That was it. Okay. Actually, it wasn't difficult at all. It just looked as though it might be when we first met it. So another lesson we can learn is don't get put off because something looks complicated. Until you think about it, you don't really know whether it's complicated or not. Okay. A couple more on this assignment sheet, and then we're done with it. Well, questions 5 and question 6, the last two questions, they're both induction proofs. So what I'm going to do is I'm going to do example 5, and then I'll leave you to do number 6. If you've already tried it and failed and you came here looking for an answer, you're not going to find it explicitly, but hopefully by watching me go through another example, namely number 5, you'll be able to go back and do number 6. Because these things are all very similar, at least the ones I'm giving you are all very similar. Not all induction proofs are similar, but these the ones I'm giving you from number theory are all very similar. Okay. Well, the first thing you have to do is express this as for some kind of an equation, with a formula in it, because otherwise we're going to deal with this expression, the sum of the first n odd numbers. So we're going to have to write down a formula for the sum of the first n odd numbers. So what it asks us to do is show that 1 plus 3 plus 5 plus, and then the nth one is 2n minus 1. And we have to show that equals n squared. Okay. Arguably the hardest part of this whole thing is figuring out what the last term is. Okay, so that's what we have to prove, and we're going to do it by induction. We're told to use by induction, so we have to begin by looking at the first case. For n equals 1, this becomes just 1 equals 1 squared, which is true. So it's true for n equals 1. Okay, So now let's assume the result. Let me call that star. So let me now assume star. And now I need to prove the corresponding result with an n plus 1 in place of n. So why don't I just add the next term to both sides? The next term would be 2n plus 1 to both sides of star, in which case I get 1 plus 3 plus 5 plus 2n minus 1 plus 2n plus 1. This is the first n plus 1. Okay, that's the first n plus 1 odd numbers. This is the next case in the induction. And now when I add 2n plus 1 to the right hand side, it becomes that. Wait a minute, I can now use another of those bricks that I learnt in high school. Thank you to my high school maths teachers, because now I can just get this one straight out. This was drilled into me. Boy, it's good to have these things at my fingertips. That's n plus 1 squared. We're done. It's the same formula with n plus 1 in place of n. Wasn't difficult at all. In fact, all of the machinery I needed to solve this one, I learnt in high school. The one thing I didn't learn in high school, at least not very well, was how to strategize about a novel problem. And that's what this course is about. This is how do you take all of that great stuff you learnt in high school and strategize and use it and get new results and think about new problems. But before you do that, you have to ask yourself, what is the problem I'm given? What do I know about it? And what am I having to prove? And if you misread a sentence, you're going to end up doing the wrong problem. You know, there were a lot of people writing on the forums where what they were really saying was, I demonstrated all my high school skills and great virtuosity and solved a problem that I wasn't asked to solve. Well, in this course, there's very little penalty for doing that, except you feel bad. If this wasn't a course, if you were working for a large corporation, you might be out of a job or demoted or moved to a less interesting job. So this is a low penalty experience for how to think mathematically, and which is why these MOOCs are great. Okay, well, as I say, I'm going to leave you to do question 6, and having seen another example, I hope you're not put off by the formulas and the complexity in question 6. It's really just logical thinking, okay, mathematical thinking. Okay, so much for assignment 8. Seemed hard at the time, actually was hard, but hopefully it doesn't seem quite so hard now. It's not hard if you become a good mathematical thinker, and that's achieving that is what the whole thing's about. Okay. Well, problem set 6 was all about whether we could recognise valid proofs or not. And by a proof being valid, we mean more than it's logically correct. Logical correctness is certainly an important part of being a proof, but the other part is its communicative aspect. Remember, proofs are about two things. They're about establishing the truth of something and about providing reasons for the truth. And to provide reasons, you have to lay it out in the proper way. Now, how you actually express it is not that important. I mean, high school teachers are very often follow this method that you, especially with proofs in geometry, that you write down statements in a left column and you write reasons in the right column. Well, that's fine. They probably do that because they want to emphasize that there are two parts to proofs. There is a sort of logical correctness, and they put that on the left side, and then there's the reasons, the rationales that make us understand on the right-hand side. But there's really no need for that. It's probably to do that for pedagogic reasons or for traditional reasons. Professional mathematicians almost never do that. What those of us in the business do is we actually tell a story, because that's what a proof is. It's a story. And like all stories, it has a beginning, it has a middle, and it has an end. And the bit in the middle has to lead from the beginning to the end. The beginning is usually a hypothesis or an assumption or a statement of the method. And the thing at the end is a conclusion when you sort of sign off and say, this is what we set out to prove, we're done. And providing it tells a logical story and makes it clear why the various steps have been taken, then it's a valid proof. Okay, so when we're looking at proofs, we have to look at them from two perspectives. Is the logic correct? And by the logic, I mean maybe the arithmetic or the algebra, whatever we're using. And is the structure correct? And how you lay it out is really up to you, so long as it's clear. So let's look at this one first of all from the point of view of telling a story. Does this tell a story? Does it have a good beginning? Does it have a good middle? The middle is usually the longest part. And does it have an end? A conclusion? And in fact the rubric actually has specific categories that cover these things. Okay, so let's just look at this one. Okay, so we begin very well. We state the method. It's a standard method, and if you're using a standard method, it really is important to begin by saying that. Because remember, if you're trying to communicate something to a reader, you need to help the reader. Tell them what you're going to do. Tell them why you're doing something. Tell them why you have done something. You shouldn't leave it up to the reader to try and figure out what you mean. That's not a good proof. That's actually a challenge. It's a problem. Someone should be able to read a proof and be convinced by what they read, not by what they have to do themselves to fill in the big gaps you've left. Okay, it's induction, so you begin by looking at the first case, and in most examples the first case is pretty trivial. It's an obvious truth, and so that's very rarely a problem. So the next step is, so let's tick them off as we go through. We stated the method. The method requires the first step, so we've done that. We'll check all the correctness later on, but we're just checking that everything's there that needs to be. Induction means you then assume the hypothesis, you assume the result for stage n, and then when you work through it, usually what you have to do is actually explicitly say what the hypothesis is. So we write down, this is what we're assuming now, within the course of the induction proof, so we've done that. Then we do some algebra. This is the middle part of the story, really, where we actually do some work. This is where you need some mathematical virtuosity. We're using the induction hypothesis. We'll check later that we're using it correctly. We state the reason for this last step. We state the fact that it's the induction hypothesis. That's a big deal. It's an induction proof. You need to state when you're using the hypothesis. I mean, there's only a couple of steps here, so it's fairly obvious when you're using it. But many induction proofs are pages long, so you need to sort of help the reader with that. A little bit more algebra. Then we've observed that the inequality has been established for n plus 1, so we say that. This establishes the inequality for n plus 1. So that's the end of the subplot. In a sense, there's a big plot that's by induction. Then the subplot of this story is you make an assumption and you reach a conclusion on the basis of that assumption. So in here, from here to there, there's a little subplot which has its own beginning, middle and end. This is a little proof within a proof. This is a proof that if you make that assumption, you can conclude the corresponding result for n plus 1 in place of n. So we've got a story within a story. And when we've completed the little story, then the big story gets completed, not automatically. It gets completed because we pull upon a very powerful property, a very powerful principle, an axiom in some cases, if you want to regard it as an axiom, called the principle or the axiom of mathematical induction. This is a powerful piece of mathematics that says if you can produce a little subplot like this, a little sub-story, then that follows. And the conclusion for the whole story, the one that began by saying we're trying to prove that, is that the inequality holds for all n. So we've ticked off the reason. This is also a reason. It depends upon that reason, but this is a separate reason. This is a reason for the whole story being correct. And then we tick off the conclusion. Okay? So this proof has all of the right structural aspects of telling a story that explains what's going on. Okay, now let's check if we've got it right. The tricky part is usually in here. This is where people very often go wrong. So let's just make sure we've got this part right. What are we doing? We're saying we're trying to prove an inequality of 2 to the n plus 1. We're trying to prove 2 to the n plus 1 is greater than 2 times n plus 1. We're going to take this inequality and replace n by n plus 1 in both sides and produce it. So we begin by the left-hand side of the thing we're trying to prove. We pull out one of the 2's. Why? Because we want to somehow use that fact there, because we've assumed it here. This is the induction hypothesis that we're going to use. And so we need to get the statement we're trying to prove in terms of n plus 1 in terms of that. So we do it this way. And then we can say the 2 gets carried over. The 2n is bigger than 2 times n by the induction hypothesis. Okay, so that's the key step there. Induction mathematics, we're given the reason. Now we do a little bit more algebra. 2 times 2n is 4n. 4n is 2n plus 2n. Why did we do that? Because we want to be able to get a 2 times n plus 1 out of it. That, of course, is bigger than or equal to 2n plus 2, because n itself is bigger than 1. So I might as well replace that by a 2 and make it possibly smaller. And then I can have a 2n plus 2. And then 2n plus 2 equals 2 times n plus 1. Okay, so all of this is correct. Okay, and it establishes that this guy is bigger than everything else, is either an equal sign or a greater than or equal to 2n plus 1. Unfortunately, this is one of those cases where what's usually trivially obvious isn't true. Okay, this actually is false. This is not a correct theorem, which means the proof is certainly not valid. So this guy is false. And the thing that went wrong wasn't the proof here. It was the first step, because it's not true for n equals 1. It's false for n equals 1. For n equals 1, this is false. In fact, it's also false for n equals 2. 2 to the 1 is not bigger than 2. It equals 2. 2 to the 2 is not bigger than 2 times 2. They both equal 4. However, 2 to the 3 is 8, which is bigger than 6, and from then onwards it remains valid. So this is actually false, not because the mathematics went wrong, but because we were careless and we didn't check the initial step. Okay, if you wanted to turn this into a valid theorem, you would have to insert here a clause n bigger than 2. You would have to say, for any natural number n bigger than 2, 2n is bigger than 2 to the n is bigger than 2n. Then the proof would be fine. The first step would be n equals 3, the first value for which the theorem is stated. So in principle it's a correct result, and in principle this can be turned into in practice this can be turned into a correct proof, but it doesn't hold for n equals 1 and n equals 2. So technically is a big deal, because we said it was true for all n and it's not. This guy is false and the proof is not valid. Even though the mathematical manipulation in the middle was perfectly okay. Obviously this is an easy example. You probably spotted that right away. I mean, I didn't bury this in a mass of symbols, so you overlooked it. It was right up there to be seen, and I'm sure many of you spotted that. But I want to make a point with this. This kind of mistake is actually pretty common. You'd be amazed, well maybe you wouldn't be amazed, but and I'm certainly not amazed, because I've been a mathematician for many years and I've seen this kind of mistake many times, and I've made it myself many times. You're trying to prove something by induction, and I say professional mathematicians do this all the time. You've been thinking about it for a long time. You come up with some really clever ideas to prove the induction step, and all your focus is on this, because this is the hard part. And in the course of doing that, you maybe simplify the theorem, you make some changes, and at some point you lose the fact that the first case is true. You know, you maybe began with a problem where it actually was true, and then you changed it, you generalized it, all sorts of things. But you're so focused on what you thought was the difficult part, and what had been the difficult part, that you forget the fact that the first case is no longer true. So it's actually, there's been a significant number of mathematicians, good mathematicians, professional mathematicians, who've produced induction proofs where the first step wasn't as obviously true as they thought. In fact, it was false. Not proofs as simple as this, admittedly. This was just an illustrative example. But the point I want to make is, do be careful about first steps, because professionals fall down on that all the time. You've just got so much to hold in your mind when you're proving theorems. When the proofs go on for several pages, you start to lose details. We all do. We're humans. We've got a limited finite mind, and we can only hold so much in our minds at the same time. So the answer to the question is the proof valid or not? It's a clear no. It's not valid. The best you can say is you can rephrase the statement and make the proof correct. But as it stands, it's not valid. So much for that one. Well, now let's take a look at this one. This is one from set theory. This may be a subject that many of you have not seen, at least not at an advanced level like this. Okay, but let's just follow it through, see what happens. if A is a non-empty finite set, X, that has n elements, then X has exactly 2 to the power n distinct subsets. Okay, and we'll do what we did in the previous one. We'll first of all check if the structure is correct, if this tells us a story and there's plenty of explanations. Is there a beginning, a middle and an end, and are the explanations there? Standard method, so we'll state what the method is, that's good. The case n plus 1 is true. We know now to be very careful to check that really is the case. We'll come back in a minute and do that. Since if X is a set with exactly one element, say X equals A, then X has the 2 subs. So here we've given reasons, explicit reasons. We'll come back and check the exactness in a minute, as I said. Okay, next step, assume, so that we've done the first step. We've said the method, we've done the first step. Next one, assume the theorem is true for n, induction hypothesis. Now we let X be a set with n plus 1 elements. We assume we've got a set with one more element. What are we going to do? Pick something in it. We'll come back later and see what all of this is about. Yada, 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 yada. Then here's the thing we're looking for next. So we're going to have to check the accuracy of all of that. But the next thing is establishing the theorem for n plus 1. Then, by the principle of induction, it's true for all n. So, yep, this is a good story. As a story, this looks fine. It's got the right structure, beginning, middle, end, and there seems to be the reasons in there. Okay, that's one part. The other part we have to check is whether it's logically correct. Okay, remember, validity means logically valid and communicatively valid, or communicatively effective, if you like. Okay, let's do. The case n equals 1 is true. Well, we are going to look at this carefully. Since if X is a set with exactly one element, say X equals singleton A, then there are just 2 subsets. There's the empty set, yep, and there's the set X itself, because there are no more elements to go into a subset. So in this case, not only do we have this here, but this is really correct. So that's, we'll put a little smiley here, because that's correct. Okay. Now we're going to have to check this bit. So we take a set with n plus 1 elements. We pick one element of the set, and we throw it away. So Y is the set X with A thrown away. Okay. So since we've thrown one element away, the set we're left with, Y, has only n elements. X had n plus 1 elements, we've thrown one away, so we're left with n elements. Now we can apply the induction hypothesis to Y, because a set with n elements has 2 to the n subsets. So we're going to list them as Y1 all the way up through Y to the 2n, 2 to the power n. So those are the subsets of Y. Now I ask ourselves, what are the possible subsets of X? Well, all of these are subsets of X, and for each one of them, if we throw A back into it, we get another subset of X. So we have the subsets of we have all of the subsets of Y, together with all of those subsets augmented by this element A that we originally threw out. And here I've made that explicit, and into each one. Well, how many sets do we have in this list? We've got 2 to the n in the first half, and another 2 to the n in the second half. The index here goes from 1 to 2 to the n, as it does there. So there are 2 lots of 2 to the n, which is 2 to the n plus 1 sets in this list. And that establishes a theorem for n plus 1. So the logic is absolutely fine. This line here is arguably overkill, because I've written it down here, and now I've put it in words. But this is essentially audience design. This is an introductory class, and so I'm assuming that many of you have never seen this kind of thing before. And for beginners at something, you spell things out in detail. If this was an advanced undergraduate class or students who'd completed a course in set theory, I wouldn't have bothered writing that part. I'd have just left that out as being superfluous. But since proofs are meant to communicate the reason for something being true, it's important to put in the reasons when you think they're going to be required for the reader. So there is a large element of audience design in writing a proof. That's just the way it is. In fact, quite frankly, a professional mathematician would write the theorem, and here's what the professional mathematician would say. Proof. Trivial by induction. That is probably all a mathematician would write. By the way, mathematicians very rarely write QED, but I admit that was when I was in the high school in my geometry class, and I thought it was kind of clever then, and I still kind of like it in a strange, bizarre sort of way. It's fine to sort of mark the end of a proof, but in any case, that's what a mathematician would say. Because when you've been doing this for many years, it is trivial. But that only works in the club of professional mathematicians. It's certainly not the case that an undergraduate taking a course could get away with that, because it doesn't convince the professor that the student knows that it's correct or not. But something like this is fine. Okay, and in an introductory class, this is about right, with or without that clause. Okay, I'm making heavy weather of this one just as I did in the previous one, because I am trying to establish what's involved in making good proofs and being able to understand proofs. Okie dokie. Right, let's go on to number 3. Well, I'm not going to do this one in full detail because we've essentially done it already. We've already, I mean, the answer is true. Okay, but that really wasn't what the issue was about. It was really about being able to prove this. Well, we've seen it proved, or we've proved it, one or the other, for p equals 2 and for p equals 3. When we first met it for p equals 2 in the lecture, I talked about even and odd. And then when we came to look at it later on for p equals 3, I observed that we could have cast the first proof in terms of divisible by 2 or not divisible by 2. And then if you take the proof for p equals 2 and replace even and odd by divisible by 2 and not divisible by 2, you can replace that phrase by divisible by 3 and not divisible by 3 and get the proof. So the proof here hinged upon divisible by 3. And that was a generalization from divisible by 2. But you can actually take it another step, and for an arbitrary prime p, you can replace divisible by 3 by divisible by p. It wasn't the fact that it was 2 that mattered, actually. It was the fact that 2 was a prime number. It wasn't the fact that it was 3 that mattered. It was the fact that 3 was a prime number. If you look through the proof, the fact that we use is that these guys, if they divide a product, divide one of the numbers in the product. And so if it only depended upon the fact that 2 was prime and that 3 was prime, then it really only depends on the fact that it is a prime. And so you can just replace the whole argument by divisible by p, and it all goes through. And so it's the same argument as before, except for a general prime. And I think that's really all I need to say for this one. This I think justifies. This actually, I mean, in terms of giving a proof, here's what I would say. The arguments. So here's how I would express it. You know, if someone insisted I write something down, the arguments used previously for p equals 2 and p equals 3 generalizes immediately. That means there's really no extra effort involved in doing it, to any prime p. That actually constitutes a proof. In this context, when we've done 2 and 3, that does constitute a proof, because it establishes the truth and it tells you why. That is perfectly good. Proofs don't have to have lots of algebra in them or lots of arithmetic. If it's a sound reason based upon previously established results, it's a proof. A proof has to be logically correct, and it has to convince the reader that it's true. That does. I mean, its logical correctness was already established in the previous ones, and we've referred back to that. Okay, now we're going to do number 4. Well, for question 4, we have to use the grading rubric. And as you'll see, this is going to involve some significant qualitative judgments. Even though we've separated out grading into these 6 different criteria, for each one of these we're going to have to exercise judgment. So you're going to find this challenging at first. In fact, you'll find it challenging even at the end of the course, although hopefully you'll have got more confidence in doing it, and in the process you'll have understood more about mathematical proofs. But let's just press ahead and see what we've got here. Okay, first of all we're going to look for logical correctness. This is an argument that involves some arithmetic and some algebra, so logical correctness is going to involve both the logic itself and the and issues of arithmetic and algebra. So all of those have to be correct. So let's take it step by step. The left-hand side for n equals 1 is, well, if n equals 1, there's just one term in this sum, and it's 1 over 1 times 2. And the right-hand side is 1 over 1 plus 1, which is 2. So indeed, this is correct. Left-hand side and the right-hand side are both a half. Okay. Assume the identity holds for n. Well, what's going on here? Well, we have to figure out what's going here, don't we? I mean, the author hasn't provided any explanation. So when it comes to looking for reasons, I'm going to be critical at this point. In fact, what is going on is that the author has taken the sum and separated out the final term. You've got a sum from 1 to n plus 1, so we take the first n and leave them there, and we pull out the final term and put it out here. Okay, so this is indeed correct. It's just taking a sum of n plus 1 terms and grouping it in terms of n terms and then the final terms. So it's absolutely correct. What's going on here? Well, again, because I've got lots of experience, I've seen hundreds of induction proofs in my life, I recognise at once that the author's simply using the induction hypothesis. Again, that's going to be an issue for reasons, but in terms of correctness, this guy does indeed equal this. And that's just carried forward. What's going on here? Let's see, so there's two terms. First of all, we're putting it over a common denominator. So we have to take this and multiply numerator and denominator by n plus 2, which gives us this part, and then we add that one onto it as well. So there's actually two steps concatenated into one here. There's expressing in terms of a common denominator, then combining them. Then we've just expanded that. And then we've used the binomial identity to get from here to here, and then we've cancelled n plus 1 to get from there to there. So all of these steps are correct. So the logic is correct. Okay. So we give full marks for that. What about clarity? Well, leaving aside reasons, I think this is perfectly clear. Everything is expressed well. Almost all the steps are in. Arguably, this was two steps in one in going from here to here. From this line to this line, there were two steps. It was expressing this one in terms of a common denominator and then combining them. But at this level of development, where we're looking at mathematical proofs in number theory, I think we're going to assume that a reader of a proof can follow this without any real problems. So I think in terms of clarity, we're going to have to give 4. This is perfectly clear. Absent reasons, we're going to look at reasons separately. But what about opening? Well, there's an opening. It's a standard method. It's using induction, and the author begins by saying induction, and then locally, in terms of doing the induction, there's a local opening here. So we're going to give full marks for the opening. And is there a conclusion? Yeah, well, there's actually two conclusions. There's a sub-conclusion in the induction proof. Assume it for n, conclude it for n plus 1. And then there's a final conclusion at the end. Okay, so we're going to have to give 4 marks for that one too. Now, this is pretty generous already for a proof that's quite a challenge, because we had to, when we looked at this, we really had to sort of figure out what was going on here. And let's just see what's really missing. This identity here, there's no reason given for that. It should have said something like separate out the final term. That would have been fine. Okay. What about this one? This identity here. Oh dear, this is a real problem. That should definitely have said by the induction hypothesis. This is an induction proof. You really should mention when you're using the induction hypothesis. So that's a real problem for me. It should be a problem for you too. This one, not so much of a problem. It would have been nice if the person had said something like express using the common denominator. That would have been nice. For this one in here, well, I mean, if you want to put a reason, you could say by elementary algebra. Because that really is elementary algebra. What about from here to here? Same thing. You could have just said by elementary algebra, and for this one here, you could say cancel n plus 1. Okay. I don't worry about this one. At this level, as I say, we're looking at we're looking at proofs in number theory now. So heavens above, we can assume that the reader can follow this kind of step. So this isn't a big deal. This isn't a big deal. This isn't a big deal. That's not a big deal. This is a huge deal. This is an induction proof. It's about proofs. It's about reasoning. And we're using one of the most powerful techniques in mathematics, certainly in number theory, which is induction. So these are big guns. We need to mention that we're using the heavy artillery here. And this is significant as well. This is the thing that sets it up. Yes, you could say that the reader could figure it out. In fact, we could assume the reader figures almost everything out given time. But a proof isn't meant to be a challenge in the sense of, can you see what I'm thinking? The proof is meant to be an explanation saying, here is what I'm thinking, here is what's going on. So in terms of a proof, this is pretty hopeless. There just are not reasons given. As I say, these are not important. These two really need to be in. This one's absolutely critical. And I would say that this one is really important. It's the key to the proof, really. Interestingly enough, up here, reasons were given. The left-hand side, I mean, this was very clear. I mean, we gave credit for the fact that this was easy to follow in terms of clarity. Okay, there were no explicit reasons, but it was so clear that you could follow the reasoning. In this case, we had to think for a minute, what's going on? Here, we had to think for a minute, what's going on? And you really shouldn't be doing it at that level. These, yeah, you have to think about it, but I think it's fairly transparent. So 0 for reasons. Okay, there are just no reasons given essentially, and 2 of them are critical reasons. If these reasons had been missing, but these 2 had been in, I wouldn't have worried. I'd have given 4 marks for reasons. If this one had been in, and maybe that one was missing, I think I would have given 3. So basically I'm saying there's 3 for that one and there's 1 for that one, and they're both missing. And these I don't care about. On the other hand, the overall picture of this is of complete lack of reasons. By the way, with these proofs, what I've done is I've taken proofs that I've obtained from students over the years, and I've condensed them so that they can fit onto a single slide. Normally this would have been taking a lot more space, but I condensed it and kept the highlights just to emphasize the various points. So this is a sort of composite of proofs that I've seen over the years from different students. So these are the kind of things that crop up all the time. Okay. What about overall evaluation? I'm going to give this 3. It's still a good proof. I mean, it's a good proof. I've given, I've penalised for the reasons. And I think justifiably, but overall, reasons aside, this is a good proof. The author just needs to be a little bit more helpful towards the reader, and that means I've got a total aggregate grade of 19, which I think is a fair grade. We've lost 5 marks. The students lost 5 marks, but I think justifiably, given the absence of the helping. It was nice that, and this you could say this is sort of generous. Well, this was very nicely done. In particular, the author not only set it up well, but concluded it well. When you've finished a proof, and proofs, remember, have beginnings, middles, and ends, and when you've got to the end, it's like a performance. You've told a story, and if you go to the theatre at the end of the performance, the cast comes to the front of the stage and takes a bow. Maybe the drums roll or something else. There's a clash of cymbals or something. You've got there. You've achieved something. Take your bow. So if you give a proof, sign off and say that you've done it, and take the bow and get the audience's applause. And okay, well, I hope you did well on that one. Well, how did you get on with question 5? Okay, this was a kind of cute little thing. It's in many ways it's very similar to question 2 that was explicitly set theoretical. But this is it's based on set theory, but it's expressed in sort of everyday terms. So let's just see. I mean, obviously it's false, right? So the question is, can you find out where the mistake is? So let's see. We're going to follow this through. Let Sn be the statement in any group of n Americans. That's just a statement. That's a definition. So there's nothing wrong with that. We're going to prove Sn by induction on n. Okay. Since everyone in a group of 1 American has the same age, S1 is true. That's true. That's okay. Assume Sn is true for some n, any n. Then prove Sn plus 1. So you pick an arbitrary group of n plus 1 Americans. Again, this is very similar to question 2. We show that everyone in G has the same age. Okay. And to show that everyone has the same age, it's enough to show that any 2 members picked at random have the same age. So you let 2 elements be in G. Okay. And let's see. That's fine. We've got n is at least 1. So G is a group of at least 2 Americans. So we can find 2 Americans in there. We can find 2 people in there. There definitely are 2 people in G. We remove 1 of the elements from G. And then we're left with a set of n elements. By the induction hypothesis, that's true. Ditto, we've taken B out. That allows us to use the induction hypothesis, which is true here. Dear me. Now let's see, be any person other than A and B. How do I know there's going to be another person? N is at least 2. N is at least 1, right? N is a natural number, so n is at least 1. So the set G has at least 2 members. But if n actually does equal 1, it only has 2 members. So this thing goes wrong right after the first step. It doesn't work when you've got n equals 2. In fact, that's where the problem is. So here it's gone wrong. There may not be a person other than A and B. Apart from that, everything's fine if you follow this through. But this thing goes wrong because once you've got more than 1 American involved, the thing is false, which intuitively, of course, is obvious. Because if you pick a group of 2 Americans, then the chances are that they don't have the same age. So just by common sense, even when you pick a pair of Americans at random, the chances are high that they don't have the same age. So intuitively, you might think that this has got to go wrong pretty quickly. It's got to go wrong once you've got more than 1 American. But of course here it's buried at stage 13 in a rather lengthy proof. So the answer is it's false. Of course we know it's false, but the answer to the question is it's false because this is the step that goes wrong. There may not be a person other than A and B. Other than that, this was fine. Okay, it's stating methods, all that kind of thing. So if we were grading this by the rubric, it would go wrong on a very, very important technicality. Okay, how did you do with that one? Well, this was really just sort of for fun, but the focus, of course, for all of this problem set was on can you recognize proofs as being valid or invalid, and can you assign a grade to a proof. Recognize them as invalid or valid is perhaps the easier of the two. Assigning grades is tricky, and that's why we're going to be spending more time looking at how to grade examples. Okay, well, there we go with problem set 6. How did you get on with assignment 8? Though the focus of this course is a particular kind of thinking, rather than any specific mathematics, the integers and the real numbers provide convenient mathematical domains to illustrate mathematical proofs. Those domains are number theory and elementary real analysis. The principal advantage as example domains is that everyone has some familiarity with both systems, yet very likely you won't have been exposed to their mathematical theories.
I'll take the integers first. Most people's experience with the whole numbers is by way of elementary arithmetic. Yet the mathematical study of the integers, looking beyond mere calculation to the abstract properties those numbers exhibit, goes back to the very beginnings of recognizable modern mathematics around 700 BCE. That study has grown into one of the most important branches of pure mathematics, number theory. Most college mathematics majors find that number theory is one of the most fascinating courses they take. Not only is the subject full of tantalizing problems that are easy to state but require great ingenuity to solve, if indeed they have been solved, and many haven't, but some of the results turn out to have applications crucial to modern life, internet security being arguably one of the most important. Unfortunately, we'll barely scratch the surface of number theory in this course, but if anything you see in this lecture arouses your curiosity, I would recommend that you look further. You're unlikely to be disappointed. The mathematical interest in the integers lies not in their use in counting, but in their arithmetical system. Given any two integers, you can add them, subtract one from the other, or multiply them together, and the result will always be another integer. Division's not so straightforward, and that's where things get particularly interesting. For some pairs of integers, say 5 and 15, division is possible. 15 divides by 5 to give the integer result 3. For other pairs, say 7 and 15, division is not possible unless you're prepared to allow fractional results, which takes you outside the integers. If you restrict arithmetic to the integers, division actually leads to two numbers, a quotient and a remainder. For example, if you divide 9 by 4, you get a quotient of 2 and a remainder of 1. 9 equals 4 times 2 plus 1. This is a special case of our first formal theorem concerning integers, the division theorem.
The division theorem says the following. Let a, b be integers with b greater than 0. Then there are unique integers q and r such that a equals qb plus r and 0 less than or equal to r less than b. Well, there are two parts to this theorem. There's an existence part, there are integers with this property, and there's a uniqueness part. Those integers are unique with this property. In proving the theorem, we're going to take those one at a time. I'll first prove existence, and then I'll prove uniqueness. So proof. As always, it's a good idea to begin a proof by stating the method you're going to adopt. In this case, what I'll say is I'm going to prove existence first, then uniqueness. I'm not using any standard method, so I'm not able to state that I'm using something like induction or whatever, but it will orientate the reader to say that the first part of the proof will deal with existence and the second part will deal with uniqueness. Okay, so we're going to handle existence. Well, look at all non-negative integers of the form a minus kb, where k is an integer, and show that one of them is less than b. What the theorem says is that among the integers a minus qb, namely the integers r, there is one with r between 0 and b. So I'm going to look at all possible candidates for a minus kb, or a minus qb if you like, and I'm going to show that among those candidates, one of them satisfies that condition. And the k for which it satisfies that condition will be the q that I'll take for the theorem. Well, first of all, I need to show that there are such integers. For example, take k equals negative absolute value of a. Then, since b is greater than or equal to 1, a minus kb equals a plus absolute value of a times b, which is greater than or equal to a plus absolute value of a, which in turn is greater than or equal to 0. Well, having shown that there are such integers by producing a k that gives me such an integer, I can choose the smallest one. Let r be the smallest such integer, and let q be the value of k for which it occurs, i.e. we'll have r equals a minus qb. So with r and q defined in this way, I will indeed have a equals qb plus r. If I can show that r lies between 0 and b in this fashion, then I'll have proved the existence. So, to complete the proof, we show that r is less than b. Well, suppose, on the contrary, that r is greater than or equal to b. In other words, I'm now going to use proof by contradiction to show that r is less than b. Well, if r is greater than or equal to b, then a minus q plus 1b equals a minus qb minus b, which equals r minus b, which is greater than or equal to 0 by virtue of this assumption. Thus, a minus q plus 1b is a non-negative integer of the form a minus kb. But r is the smallest such. And yet a minus q plus 1b is less than a minus qb, which is r. And that's a contradiction. If r is the smallest such, we can't find a smaller one. There's a contradiction. Hence r is less than b, because we obtain that contradiction on the assumption that r is greater than or equal to b. And that proves existence. If you haven't seen a proof like this before, it almost certainly looks very complicated. It's actually not complicated or deep, it's just intricate in its structure. The idea is to look at all of the possible candidates to make this true. Well, first of all, we have to show there is a possible candidate, and we actually do that by exhibiting one. And then, to get a candidate which satisfies this additional requirement, we pick the one where the r is the smallest, it's the minimal value of r that gives us one of these things. And then we use the fact that it's minimal in order to show that it has to satisfy this requirement. Each individual step is just elementary algebra. It's just somewhat intricate to push the argument through. There's a lot of arguments in mathematics like this. There is no deep mathematics involved. There's nothing more than elementary arithmetic and a little bit of algebra. But there's a bit of intricate structure to make the proof work. So if you haven't seen this kind of argument before, it'll probably take you several reads through. You need to look at it several times before it begins to make sense. Okay, well, that proves existence. Then we need to turn to uniqueness. To prove uniqueness, we show that if there are two representations of a equals qb plus r and a equals q prime b plus r prime, with 0 less than or equal to r and r prime less than b, then r equals r prime and q equals q prime. So the first part of the division theorem, the existence part that we've already proved, shows that there are representations of this form. What we're now doing is showing that if there are two such representations, then in fact they're identical. The R is the same and the Q is the same. Incidentally, you probably realise by now that the letter Q is going to denote quotient and the letter R is going to denote remainder. We haven't officially defined quotient and remainder yet, so I haven't written anything like that down, but I'm using the familiar notation. Because what we're doing is we're giving the mathematical underpinnings of the familiar knowledge that you probably have about arithmetic, dividing one integer by another. Okay, so we have an equation here. QB plus R equals Q prime B plus R prime. Let's rearrange it. Rearranging, I get R prime minus R equals B into Q minus Q prime. And I've labelled that equation 1 for later reference. Now I'm going to take absolute values in this equation. And when I do that, I get absolute value R prime minus R equals B times absolute value of Q minus Q prime, which I've labelled equation 2. B is positive, remember. So when you take absolute values, B remains the same. But negative B is less than negative R, which is less than or equal to 0, and 0 is less than or equal to R prime, which is less than B. So negative B is less than R prime minus R is less than B. Well, if R prime minus R is between negative B and plus B, that means that the absolute value of R prime minus R is less than B. So by 2, B times absolute value of Q minus Q prime is less than B. Well, I can divide by B now to give me absolute value of Q minus Q prime is less than 1. But everything here is an integer, and the only way you can have a pair of integers, the absolute value of the difference between them being less than 1, is if that absolute value is 0, which means Q has to equal Q prime. And then by equation 1, R has to equal R prime, and that proves uniqueness. And with it, we've proved the division theorem. Well, again, if you haven't seen arguments like this before, it's going to seem pretty daunting, but when you go through it step by step, this is really just very basic arithmetic arguments with inequalities. Take it step by step, and you should be able to follow the arguments through right to the end. Okay, good luck with that.
If this is the first full-blown, rigorous proof of a theorem like this that you've encountered, you'll probably need to spend some time going over it. The result itself isn't deep. It's something we're all familiar with. Our focus here is on the method we use to prove conclusively that the division property is true for all pairs of integers. Time spent now making sure you understand how this proof works, why every step was critical, will pay dividends later on when you encounter more difficult proofs. By gaining experience with mathematical proofs of simpler results like this one, which is obvious, mathematicians become confident in the method of proof and can accept results that are not at all obvious. For an example of a result that's not obvious, in the late 19th century, the famous German mathematician David Hilbert described a hypothetical hotel that has a strange property. Hilbert's hotel, as it's become known, is the ultimate hotel in that it has infinitely many rooms. As in most hotels, the rooms are numbered using the natural numbers, 1, 2, 3, etc. One night, all rooms are occupied when an additional guest turns up. "I'm sorry," says the desk clerk, "all our rooms are occupied. You'll have to go somewhere else." The guest, a mathematician, thinks for a while before saying, "There is a way you can give me a room without having to eject any of your existing guests." Before I proceed with this story, you might like to stop the video for a moment and see if you can see the solution the mathematician guest has seen. The clerk is sceptical, but he asks the mathematician to explain how he can free up a room without ejecting anybody already in the hotel. Well, it's simple, the mathematician begins. You move everybody into the next room. So the occupant of room 1 moves into room 2, the occupant of room 2 moves into room 3, and so on throughout the hotel. In general, the occupant of room n moves into room n+1. When you have done that, room 1 is empty. You put me in that room. The clerk thinks about it for a moment and then has to agree that the method will work. It is indeed possible to accommodate an additional guest in a completely full hotel without having to eject anyone. The mathematician's reasoning is totally sound, and so the mathematician gets a room for the night. The key to the Hilbert Hotel argument is that the hotel has infinitely many rooms. Indeed, Hilbert formulated the story to illustrate one of the several surprising properties of infinity. You should think about the above argument for a while. You won't learn anything new about real-world hotels, but you will come to understand infinity a bit better. And the significance of understanding infinity is that it's the key to calculus, the bedrock of modern science and engineering. And when you're satisfied you understand Hilbert's solution, try the following variants. First variant. The Hilbert Hotel scenario is as before, but this time 2 guests arrive at the already full hotel. How can they be accommodated? In separate rooms, I should add, without anyone having to be ejected. Second variant. This time, the desk clerk faces an even worse headache. The hotel is full, but an infinite tour group arrives. Each group member wearing a badge that says, "Hello, I'm N," for each of the natural numbers n equals 1, 2, 3, etc. Can the clerk find a way to give all the new guests a room to themselves without having to eject any of the existing guests? And if so, how? Examples like the Hilbert Hotel demonstrate the importance of rigorous proofs in mathematics. When used to verify obvious results, like the division theorem, they may seem frivolous. But when the same method is applied to issues we are not familiar with, such as questions that involve infinity, rigorous proofs are the only thing we can rely on. Now back to the division theorem.
Well, the way I've stated the division theorem, it only applies to division by a positive integer b. There's a more general version that I'll give you now. So, theorem, general division theorem, let a, b be integers with b non-zero. Then there are unique integers q and r such that a equals q times b plus r and 0 less than or equal to r less than absolute value of b. So the general division theorem is almost exactly the same as the previous division theorem we proved, except that instead of demanding that b is strictly positive, we're saying that b is non-zero. And then here we have the absolute value of b. And the proof follows fairly straightforwardly from the previous result. Then, since the absolute value of b is greater than 0, the previous theorem tells us there are unique integers q prime and r prime such that a equals q prime times the absolute value of b plus r prime and 0 less than or equal to r prime less than absolute value of b. Well, now we simply let q equal negative q prime and r equal r prime. Then, since absolute value of b in this case, with b negative, is negative b, we get A is QB plus R, 0 less than or equal to R, less than the absolute value of B. And that's this theorem. So we simply threw it back to the previous result. And with the general division theorem now established, we can formally give names to the two numbers Q and R. Okay, and officially we say the number Q is called the quotient of A by B, and R is called the remainder. And so we've now cycled right back to something that you learned in elementary school about dividing numbers, and that there were sometimes remainders, there were quotients and remainders. Okay, only now we've done it with some sophistication, and we've shown that everything is well defined. Oh, how about that? Well, now that we have the division theorem available, we can look at the important mathematical property of divisibility. If division of A by B produces a remainder R equal to 0, we say A is divisible by B. Hence, A is divisible by B if and only if there's an integer Q such that A equals BQ. For example, 45 is divisible by 9, but 44 is not divisible by 9. The notation that we use for divisibility is this: B vertical line A denotes A is divisible by B. And let me give you a warning at this point. B divides into A, or A is divisible by B, is not the same as B divided by A with a slanted line. This guy is a relationship. Between A and B. It's true or false. This guy denotes a rational number. The result of dividing B by A in the rational numbers. So we have a property, a relationship, which is either true or false, and we have a notation for a rational number. Now these are quite distinct concepts. This is something to do with two integers, tells you whether two integers are in a certain relationship. This is a notation for a specific number. The reason I'm issuing this as a warning is that beginners in particular often confuse these two things. They both, after all, do have to do with division. But in this case, it's a property, has nothing to do with fractions, with rational numbers. This, it's a specific number. It's a specific rational number that we're referring to. Now, there wouldn't be as much of a problem if the notation wasn't very similar. And it gets worse when people with sloppy handwriting, and you've probably noticed that I'm one of them, often don't distinguish clearly between a vertical line and a slanted line. In fact, this one is already almost vertical. Maybe it would have been better if I'd written it like that. Okay, that's better. But because the notation is similar, it's often very easy to get confused between these two things. The context does disambiguate. If you understand what's been discussed, you shouldn't have any problems. But bear in mind, especially when you're meeting this material for the first time, that there is an important distinction here. And in fact, I've got a quiz coming up in a moment, which I hope is going to help cement your understanding of this notion so that you'll be able to distinguish it from this one. Okay, and once we've got divisibility lined up, we can define the all-important notion of a prime number. A prime number is an integer p greater than 1 that is divisible only by 1 and p. Notice that we explicitly exclude 1 from the prime numbers. So the first prime is 2, the next one is 3, then 5, then 7, then 11, and so forth. Now for that quiz about divisibility. Okay, how did you do? Well, remember the condition we have to check is this one. B divides A if and only if there is a Q such that A equals BQ. Well, let's see what we have. The correct ones are B, D, F, G, and H. Why don't I have A? Well, remember, the whole definition of divisibility was under the assumption that B is non-zero. We can't consider divisibility by a zero number. So that one doesn't work. And likewise, that one doesn't work. And of course, the reason this one doesn't work is because 7 simply doesn't divide into 44. Okay? Do be careful about this though. Division by 0 is problematic under any circumstances, and so we rule it out. And in this case, it was ruled out in the very statement of the divisibility theorem. Okay, how about this one? Well, again, the condition we have to check is that B divides A if and only if there is a Q such that A equals BQ. And again, this is under the assumption B non-zero. Everything is an integer here. Well, the correct ones are that, and that. So why are the others false? Well, this one is false because that simply doesn't divide that. However, if you sort of got out a calculator and actually tried to divide it, then you were missing the obvious point. This is an even number, and that's an odd number. And we cannot have an even number dividing an odd number. So if you had to do any arithmetic for this, then you were making the mistake that I've been warning you against of acting as if you were in high school. This is a course about mathematical thinking, and what I hoped you would have done is to think about this mathematically and realize that you can't have an even number divided into an odd number. So this is a cautionary reminder that this is not about jumping into calculations and applying procedures. This is all about thinking about a problem. Okay, so that's false. But I would hope that you would recognize it's false without doing any work whatsoever other than a little bit of thinking. Okay? I occasionally like to slick things like that into quizzes just to keep people on their toes. Well, this one is false, of course, because that's simply not the case, that 2n divides n squared. The reason the others are false, well, this is false for various reasons. I mean, it's the same. I mean, 2n simply doesn't divide n squared for various reasons. The reason this is false is because if n can vary over z, then that will include n equals 0. And so we can't have this because we can get a 0 coming in. That includes n equals 0. Likewise for this one. Okay, same thing. So this one fails because 0 is included. If I excluded 0, it would be fine. I mean, the only difference between these two is that this is the positive integers, 1, 2 and 3 and so on and so forth. This one, because it's all of the integers, includes 0. Okay, well, let's move on now. I want to prove a theorem now that gives the basic properties of divisibility. So, theorem, let a, b, c and d be integers with a non-zero. Then the following all hold. 1, a divides 0, and a divides a. 2, a divides 1, if and only if a equals plus or minus 1. 3, if a divides b and c divides d, then AC divides BD. This is under the assumption C is non-zero, because we can't have divisibility by 0. The division theorem itself excludes the case of division by 0. 4, if A divides B and B divides C, then A divides C, and this is under the assumption B non-zero. Again, we have to exclude the possibility of division by 0. 5, A divides B and B divides A, those two hold if and only if A equals plus and minus B. 6, if A divides B and if B is non-zero, then absolute value of A less than or equal to absolute value of B. You can only divide smaller numbers into bigger numbers, or at least numbers that are no bigger than. You can't divide a number B by something that's bigger than it in absolute value. One more. 7. If A divides B and A divides C, then A divides bx plus cy for any integers xy. Okay, you prove all of these by going back to the definition of divisibility. Now, what I'm going to do is I'll prove 2 of them as examples. Let me just pick number 4. Let's prove 4, that's this one here. All the proofs are essentially the same idea. If A divides B and B divides C, then that means there are integers D and E such that B equals DA and C equals EB. That's the definition of divisibility, in which case C equals D times E times A, which again by the definition of divisibility means A divides C. Let me do one more. Let me do 6. Okay, so A divides B, so that means since A divides B, it means there is a D such that B equals DA, in which case, taking absolute values, absolute value B equals absolute value D times absolute value A. And since B is non-zero, we know that the absolute value of d will have to be greater than or equal to 1. So the absolute value of A is less than or equal to the absolute value of B. Okay. See, B is non-zero, so D can't be 0, so its absolute value is greater than or equal to 1, and if the absolute value of D is greater than or equal to 1, then A has to be less than or equal to B. The other statements in the theorem are proved similarly. You just take it back to the definition of divisibility, and when you know that, remember the definition is B divides A if and only if there is a Q such that A equals BQ. And in all cases you go back to the definition and then the thing drops out in a couple of lines. Okay, well that's the that lists all of the basic properties of divisibility. Okay, it's time to prove the fundamental theorem of arithmetic. Theorem: every natural number greater than 1 is either prime or can be expressed as a product of primes in a way that's unique except for the order in which they are written. For example, 4 is 2 times 2 or 2 squared, 6 is 2 times 3, 8 is 2 cubed, 9 is 3 squared, 10 is 2 times 5, 12 is 2 squared times 3, and so on and so on. 3,366 equals 2 times 3 squared times 11 times 17, and so forth. I worked that one out in advance, by the way. Okay, so 2 itself is prime, 3 is prime, 4 is a product of primes, 5 is prime, 6 is a product of primes, 7 is prime, 8 is a product of primes, 9 is a product of primes, 10 is a product of primes, 11 is a prime, 12 is a product of primes, and so on and so on and so forth. The expression of a number as a product of primes is called its prime decomposition. And when you know the prime decomposition of a number, you know an awful lot of information about that number and how it behaves with relation to other numbers. Well, we proved part of this a little while ago, proved the existence part. Though I'm going to give you another proof of existence in a moment, but the new part is to prove uniqueness. The uniqueness proof will require Euclid's lemma. That says if a prime P divides a product AB, then P divides at least one of AB. The proof of Euclid's lemma is not particularly difficult, but it would take me outside the scope of this course. Remember, the focus of this course isn't to teach you number theory and number theoretic techniques. It's to develop mathematical thinking, and it would be too much of a detour from that goal in order to prove Euclid's lemma. But if you just Google Euclid's lemma, you should be able to find some references that would lead you to a proof. Let me give you the existence proof. More precisely, let me give you a new proof of existence. Remember, this is the statement of the theorem. Any natural number greater than 1 is either prime or can be expressed as a product of primes in a way that's unique except for their order. And we're going to prove existence. The previous proof of existence that I gave you used the method of mathematical induction, and I gave it as an illustration of the method of induction. But I'll give you a different proof now. I'll prove it by contradiction. Suppose there were a composite number, that's a non-prime, that could not be written as a product of primes. Then there must be a smallest such number, call it n. Since n is not prime, there are numbers a, b, strictly between 1 and n, such that n equals ab. If a and b are primes, then n equals ab is a prime decomposition of n, and we have a contradiction. Because n was chosen so as not to have a prime decomposition. It was actually the smallest number that didn't have a prime decomposition. Well, if it's not the case that a and b are primes, then at least one of them must be composite. But if either of ab is composite, then because it's less than n, it must be a product of primes. So by replacing one or both of ab by its prime decomposition in n equals ab, we get a prime decomposition of n, and again we have a contradiction. That proves existence. That's the first part of the proof of the fundamental theorem of arithmetic. Now let me prove uniqueness. So what I have to prove is that the prime decomposition of any natural number n greater than 1 is unique up to the ordering of the primes. And I'll prove it by contradiction. So assume there is a number n greater than 1 that has two, or more in fact, different prime decompositions. Let n be the smallest such number. Let n equal p1 times p2 times times pr equals q1 times q2 times qs be two different prime decompositions of n. So we have n as a product of r primes, and we also have n as a product of s primes, some of the primes being different. Well, p1 is a prime factor of n, so p1 divides n, so p1 divides this product. Since p1 divides q1 times q2 through qs, and let me stop at this moment and see what I've done. I've said p1 divides n, so p1 divides this, and I'll split that into two that way, and notice that p1 divides q1 times that, and I've done that in order to apply Euclid's lemma. So now let me continue that sentence. By Euclid's lemma, either p1 divides q1 or p1 divides the product q2 through qs. Remember, Euclid's lemma says that if I have a prime number p, and if p divides a product a times b, then p divides at least one of ab. So Euclid's lemma was that if p divides a product ab, it divides at least one of those two numbers. So from here, p1 divides this product. I've now written that as a product of two numbers, and I can now apply Euclid's lemma and say that if p1 divides that times that number, it must divide at least one of them. Either p1 divides q1, or it divides the other part, or maybe both of them. Okay? Hence, either p1 equals q1, or else p1 equals qi for some I between 2 and s. Okay? If p1 divides q1, then they're both primes, so the only possibility is that p1 equals q1. Or else p1 divides this product of primes, which means that p1 actually is one of those primes. So first case, I know that p1 equals q1. Second case, I know that p1 equals qi for one of the i's between 2 and s. But then we can delete p1 and qi from the two decompositions in star, which gives us a number smaller than n that has two different prime decompositions. contrary to the choice of n as the smallest such. Okay, having established that P1 is equal to one of these Q's, we don't know which one, but it's going to be one of them, I can delete the P1 from here, I can delete the appropriate Q from there, and when I delete P1 from there and some Q from there, I still have equality, I still have a prime decomposition of a number, but having deleted that common prime, the number that I get is smaller than n. So I get a number smaller than n that has two different prime decompositions. The number smaller than n will be P2 times times PR, though, so that will be the number smaller than n. And I've deleted a number from here, and what's left is the prime decomposition here. So the proof involves simply identifying the fact that, or recognizing the fact, and this uses Euclid's lemma, that you're going to have the same prime on both sides. You can delete it and get two different decompositions of a smaller number. And that proves uniqueness. Okay, well, now we've proved the fundamental theorem of arithmetic. Cool, huh?
So, did that make sense? Chances are you're going to have to spend some time trying to come to grips with this. Though I know you're familiar with arithmetic, especially whole number arithmetic, this is probably the first time you've tried to really analyse numbers. See how you get on with assignment 9.
Well, as I stressed in the lecture, you've got to be careful in distinguishing between these two notions. You have a notation for a relationship, something that's true or false. A is divisible by B, or B divides A. And you've got another notation for a number, the result of dividing A by B. This makes sense when you're talking about the integers. This actually is not defined for the integers. I mean, for some integers you get an answer, but this is division, actual division as an operation, is an operation not on the integers, it's an operation on the rational numbers or the real numbers. In the integers, all you have is addition, subtraction and multiplication. You don't have division. What you can do is say whether you have divisibility. And divisibility is defined in terms of multiplication. Okay? So it's all about the distinction between the two. You've got a property, something that's true or false, and you've got a notation for a number. This is an actual number. Okay, so the actual answer I'm going to end up with is the thing here at the bottom to the question. As concisely and accurately as you can, the relationship. This is the relationship. B divides into A, or A is divisible by B, if and only if A divided by B happens to be an integer. And sort of summarising what I just said above there, that's a notation that denotes a rational number. Rational number. That's a different set of numbers. This denotes the relation B divides A, i.e. there is an integer Q such that A equals QB. And whenever you're dealing with divisibility with this notion and you're working with the integers, you have to reduce that abbreviation to this. There is an integer such that that. That's what that means. Okay, that means that. That nothing means that. Okay? And then to get down to here, in the case where you do have divisibility, then of course the Q that's here is the quotient. I mean, we use Q to denote the word, to stand for the word quotient anyway. But notice that this says nothing about division. Division doesn't arise here. It's all about the result of multiplying two numbers. So this makes perfect sense when you're talking about the integers. Okay? So we're not doing sort of arithmetic in the sense of calculating here. You know, obviously everything that's involved here about dividing one whole number by another, you know, you learnt it in elementary school, it is just division of whole numbers. The focus here, however, is on what you're doing within certain systems of numbers. We have two systems of numbers here. We have the integers, and we've got the rationals. They're just two separate systems of numbers. In the case of the integers, you can add, subtract, and multiply. in the case of the rationals, you can add, subtract, multiply and divide. But they're different systems of numbers. And so the focus here is on what you can do in the integers. That's what number theory is about. And then in the very last lecture, lecture 10, we'll be actually looking at the rationals and the reals. But that's a different system of numbers. You can do different things with it. So we're taking a more sophisticated look at elementary arithmetic, but it still is, after all, elementary arithmetic. Okay, let's look at numbers 2 and 3. Well, the issue with all problems like this is you have to express the divisibility property in terms of multiplication. Remember, divisibility is a property of pairs of integers. You can't divide integers. All you can do with integers is add, subtract, or multiply them. And divisibility arises when you take this definition, A divides B, if and only if there is a q, an integer, such that B equals Q times A. So the general strategy for dealing with divisibility, actually it's really the only strategy, is you replace issues like this, you replace a statement like that, with a statement about multiplication. Because the point is that there is no operation here. There's nothing that's not an operation to deal with. It's not an arithmetical operation on the integers. Remember, this is all about the integers. So you have to express it in the language of the integers. And the language of the integers allows you to talk about addition, subtraction, and multiplication, but not division. Okay, so how do you show that, how do you answer this one? What's the proof? Well, this one is sort of immediate because the very definition of divisibility explicitly excludes A not being in 0, A not equal to 0. It excludes A being 0. Okay? So it's false, and that's the reason. 9 divides 0, well, that's definitely true. And to show that it's true, you simply express the definition. You express it in terms of the definition. So you would have to show that there is a q. Look at the definition. You have to show there is a q such that 0 equals q times 9. Well, of course there is. 0 itself is one of those things. Okay, so it's false. It's true. This one's false for the same reason A was false. You're not allowed to have A equal to 0 in the notion. That includes that requirement. This one is definitely true, and the proof is just write it in terms of this. This is basically what you end up having to write. In each case, if you look at these, that's what I'm going to end up writing. I'm going to end up reformulating it in terms of the definition. That's really all it involves. Just reformulate the statement in terms of the definition. Show that the definition is true. Okay, well in this case it's true because q equals 1 makes it true. In this case, we know that there's no such q. You could argue it just by, since any possible q would have to be less than 7, say. You could actually explicitly, if you wanted to prove that even in more detail, you would just let q be all of the possibilities that have a chance of being that. Q equals 1, 2, 3, 4, 5, 6, 7, and 7 sevens is already 49, so you're out of it. So you actually only need to go to 6, of course. So you could explicitly list all of the possible q's if you wanted to. But that would be so trivial. I think you could just leave it like that. At this level, if we were talking to kids in the elementary school, we would ask them to maybe list all of the possible q's and make sure that none of them give you the answer 44. But at this level, you can just take that as being obvious. This one's certainly true. You exhibit the q, namely q equals -6, q equals -6. Ditto here. You exhibit the q, and again it's -7. Here you exhibit the q, and the q is 8. Here you need to show that for all n 1 divides n. Well, that's certainly true. And the reason is that for any n in z, n equals n times 1. Right? Kind of trivial, right? 1 divides everything. For all n in z, for all n in n, n divides 0. That's true because again, for any n in z, 0 equals 0 times n. And this one, this is what we've got to be careful with, because if we're quantifying over all of the integers, that includes 0 itself. And you're not allowed to have 0 dividing anything. Okay, that's excluded from the definition. So this is the one you have to be careful with, because it includes 0. It's the only case where it goes wrong, but you only need one counterexample to make a universally quantified statement false. And that one counterexample is all it takes to get rid of that one. Okay, so that one's false. Okay, and we've done them all. Notice it was just the same pattern. Express divisibility in terms of the definition of divisibility. And then in each case it just drops right out, because this is, after all, just elementary whole number arithmetic. You know, it's not that there's anything deep going on here. It's just that we're looking at it in a somewhat more sophisticated fashion than you did when you were in the elementary school. Everything you need to know to solve this, you learned in elementary school. It's just that we've now got a little bit more of a sophisticated gloss on it. Okay. Well, as with the previous example, what you have to do is reduce each of these to the definition of divisibility. Remember, divisibility is a property of pairs of integers. This isn't division. It's obviously related to division, but you don't have division in the integers. What you can do with the integers is you can add them, multiply them, and subtract them. I mean, subtraction just being the inverse of addition. But you can't divide them. Okay, but you can have a property of divisibility, but to discuss divisibility within the integers, you have to reduce it to a discussion of essentially of multiplication. Okay, so how would you show that A divides 0, that you've got divisibility of 0 by A? Well, you observe that actually, because of the properties of 0, 0 is equal to 0 times A, so in particular 0 satisfies the requirement for divisibility. Okay, there is a Q in Z such that 0 equals QA, namely Q equals 0. So by definition A divides 0. Okay. Similarly, in the case of A dividing A, because of the properties of 1, A equals 1 times A. So again, the definition of divisibility is satisfied, and it's satisfied in this case by letting Q be equal to 1. So by definition, A divides A. Okay, so that was that one. And the rest are essentially the same idea. A divides 1 if and only if A equals plus or minus 1. Okay, well, we've got two implications to prove. First of all, let's assume that A equals plus or minus 1. Then, again, all you have to do is show that there is something such that 1 equals Q times A. Well, if A equals plus or minus 1, there certainly is, right? Conversely, that should be if. Little typo there. Conversely, if A divides 1, then for some Q, 1 equals QA, by definition of divisibility. But if 1 equals Q times A, then the absolute value of 1 is the absolute value of QA, which is the absolute value of Q times the absolute value of A. And if 1 equals that, then the only possibility, because these are positive integers now, is that absolute value of Q is absolute value of A is 1. That's the only way you can get 1. And so if the absolute value of A equals 1, then A has to be plus or minus 1. Let me just do one more and then let you do all of the rest. If A divides B and C divides D, then AC divides BD. Okay, well, we know that there are Q and R, such that B is QA, definition of divisibility. D equals RC, definition of divisibility. Hence, multiplying the two together, you've got BD is QA times RC, which is, when you rearrange them, QR times AC. So by definition, AC divides into BD. And the others are essentially the same idea. In each case, you just reduce it to the question of multiplication through the definition of divisibility. So you never actually do any dividing. You express division in terms of multiplication. And you can do that because division is the inverse of multiplication. Okay, so the whole thing is going to work out. So these proofs are always typically just 1 or 2 lines. They really are just a matter of translating what it is you're having to prove into divisibility. So the first line of any of these arguments really is just is a matter of re-expressing what it is you're having to prove in terms of divisibility, in terms of multiplication via the definition of divisibility. Okay, well, that's it. Well, for number one, the first one is going to be true because 300 equals 15 times 20. Okay, so we've shown that 300 is a whole multiple of 20. The second one is false because if you apply the division theorem, then you find that 35 equals 2 times 17 plus 1. Okay. The third one is true because 0 is a multiple of 5. It's 0, times 5. Okay. The next one is false because 0 is excluded. This is explicitly excluded. You can't talk about divisibility by 0. And the last one is true because negative 21 equals negative 1 times 21. Now obviously here I'm giving overkill. I'm actually expressing these results in terms of the division theorem. In reality, because we're very familiar with divisibility, we can just recognize these facts. Okay, so this is definitely overkill. I'm doing this for pedagogic reasons, just to relate these issues with the division theorem. Okay, well, so much for number one. So question 2 asks us whether this proof of this theorem is correct or not. So let's just go through and see. We begin by, and I'm going to look at this both in terms of the logical correctness of the argument and whether it succeeds from a communicative point of view. Okay, so let's see what we've got. We begin by stating an initial assumption. There's no standard method being used here, so we're not sort of saying by induction or contradiction. We're just going to do some reasoning, but we state where we're starting from. We're starting with the division theorem, and then in particular, a consequence of the division theorem for when we are looking at divisibility by 4, the remainder is going to be either 0, 1, 2 or 3. So this is just an immediate consequence, a direct consequence of the division theorem. So we've stated the assumption, we've correctly derived an instance of that assumption, and we've stated an instance of that assumption. Let me see what we've got here. Therefore, any odd number has one of those two forms because the other two are even. So now I've particularized this fact. Okay, so I've got a starting fact, and then I've got a particular consequence or a particular case. Starting fact, then we specialize it in fact. Starting fact is a division theorem, then we specialize it to this case of divisibility by 4. Then we look at a particular case and say that odd numbers have that form. And then when I square, assuming the algebra is correct, so yes, yes, the algebra is correct. And in both cases, the result is 1 more than a multiple of 8. Okay, so that's correct, that's correct. I've made the observation that they're both 1 more than a multiple of 8. And then I sign off by stating that this in fact proves the theorem. So I've got a beginning, a middle, and an end. So it succeeds communicatively. I've given reasons for each thing. Notice I didn't just square these things. I didn't simply square them. I said I was squaring them, so that the reader's not left wondering what I'm doing. Now, the reader might be a little bit puzzled as to why I started in this way, and that's basically experienced mathematicians can fairly regularly and moderately quickly come up with this kind of thing. If you're a beginner, it can take you longer. Okay, And then when I've done that calculation, I make a specific conclusion, and this was a conclusion to the reasoning, not to the whole proof, because the conclusion of the whole proof is to observation that this proves the theorem. This is the drum roll. This is where the cymbals crash. This is where we take a bow. We've done it. We're out of there. Okay, so the answer is, yep, it's valid. And we've just checked that it's valid by going through all of these arguments. Okay, let's move on to number 3. Where this proof is in fact valid. Okay, let's just make sure that it works on all levels. We're arguing by contradiction. Okay, so this is the beginning, and this is the beginning step. Suppose the conclusion is false. Then there'll be a natural number n for which A is not true, so there'll be at least one. Now by the first condition, okay, at A1, we know that the m can't be equal to 1 because A does hold at 1, so m is bigger than 1. So m equals n plus 1 for some n. Since n is less than m, we know that an holds because m is the least one for which it doesn't. Then by the second condition, an plus 1 holds, i.e. am. That's a contradiction, and that proves a result. The only thing to notice is that here the n is being used in a quantified form. So this is a variable that's been quantified, right? Okay. In this case, what we're saying is if this fails, then there'll be one of these n's for which it fails. And at this stage, the n is sort of a variable. But at this point, when we put the m in, m is a specific number. We don't know what its value is. In fact, we're going to show that no such m exists. But on the basis of a false assumption, there will be a place where it fails. And m is going to be a specific number. So the m here is specific within the proof. Okay. When I get down to here, the n is also specific within the proof because it's equal to m minus 1. So in these cases, once I'm down here, I've got a specific m and a specific n. Up here, it's just a general n. Okay? So everything here is specific. Now, in fact, there never was such an m, and hence there never was such an n, because the conclusion as a result is valid. But within the context of this argument, these guys are specific. Okay. Here, this is a variable, it's quantified. All right? In any case, this is true. This is true. Well, number 4, we have to use the course rubric again. First of all, let's see what the theorem says. It says that if we take the Fibonacci numbers and we square them, and we take the first n of them and square them and add them, then the result is equal to the nth Fibonacci number, the last one in this sequence here, multiplied by the one after that. Now this is true, by the way. This is true. It's a valid theorem. It's one of many identities about Fibonacci numbers that show that they're connected in what at first are very surprising ways. They're very typical in that they're almost always proved by induction. And when you look at the induction proof, you realize that it's really the identity, which at first seems surprising, is actually just a disguised version of the definition of the Fibonacci numbers. What's behind all of these interesting identities is the fact that the n plus second Fibonacci number is the sum of the nth Fibonacci number and the n plus first Fibonacci number. So they all go back to the fact that it's defined in this iteratively additive way. Okay. Well, let's just see if this one, see how this one goes. Okay. First of all, we'll look at logical correctness, worrying about things like reasons and so forth later. Let's check that the first case is true. F1 is equal to 1, so F1 squared, and in the case n equals 1, there is no sum, it's just F1 squared, so the left-hand side is just 1. And the right-hand side is F1, which is 1. And of course, the second Fibonacci number is also 1. The Fibonacci sequence begins with a pair of 1s, so we have 2 1s on the right. So this is logically correct. Then there's the induction step. Let's just check the algebra here. Here it's just the taking a sum up to n plus 1 and pulling out the second one, the last term in the series. So we've got a sum of n plus 1 is the sum of the first n together with the last one. I'll look at the issue of reasons in a minute. This will be the induction hypothesis, nicely stated as a reason that this sum equals fn n plus 1. This is just fn plus 1 squared. I carried through. Take out fn plus 1 as a common factor. Okay. Let's see. This is definition of fn plus 2. Is the sum of that one plus that one. And then we've got the identity of n plus 1. Okay, so all of the logical steps are correct. This is a valid induction proof. So I'm going to give 4 marks for that. Is it clear? Yes, I think this is clear. Again, there's going to be some issues of reasons to explain things, but everything is clear. It's well laid out. It's easy to follow steps. Even when I had to figure out what the author meant, we'll talk in a minute as to whether I should have had to. It was easy to follow in that sense. So it was clear. There's an opening. It's well opened. It's a proof by induction as a standard method, and the good way to start, the correct way almost to start a proof using a standard method, is to state what the method is. So I'm going to give full marks for that. Conclusion. Well, the conclusion is stated. I'll look at whether it's properly stated in a minute, but there's certainly a statement that the proof is complete, and it's been laid out that it's going to be an induction proof. So I think we've got to give 4 for that. Reasons. A couple of quibbles. I think probably the author should have said separate out the final term. This is good. Stating the use of the induction hypothesis in an induction proof is always critical. I think this is such an important step. By algebra, yeah, you could say something like take out a common factor, but this level of mathematics when we're doing proofs in number theory, as I mentioned with the last problem set, we can assume that people can spot things like taking out common factors. This I think is important. This is critical, the fact that we're using the definition of the Fibonacci numbers. These kinds of as I mentioned a moment ago, these kind of identities actually only hold because of the way the Fibonacci sequence is defined, which establishes the identity for n plus 1. That's good. That's a local conclusion, which is good. The proof is complete. Here the person should have said by induction, or by the principle of induction. Let's put it out in full. Principle of induction, because there is a powerful fact about the natural numbers that's been used here. Okay, so what am I going to give for reasons? I'm going to give 2. I think I can't give 4. If this one, arguably, I would tend to lean on having this in, especially since it's an opening step in a proof. But if that was the only thing that was missing in this context, I might not have even deducted any marks at all. This one, however, I have to deduct at least 1, and I think I've already deducted. I think really I've deducted the 2 for this one. It was a bit of a judgment call. I have to allow for the fact that the author of a proof maybe made a slightly different judgment call. You have to try and judge how well you think a person's putting down a proof. And you can't really say, I always do it this way, therefore you always should do it this way, because people have they come on different sides of these issues. We're really looking to grade this as an overall thing. One of the problems with using a rubric is we're trying to take something that's holistic and is basically an overall judgment call and reduce it to a number of parameters. This is not how professionals grade. They look and they say, overall, is this a good proof? And then they assign a number. But that's based on years of expertise. Pulling it apart in this way is good for beginners because it allows you to focus one by one on the individual things But a professional looks at all of these things in one, and you have to sort of balance things out. And that's why we're going through all these videos, to try and give you some indication of how a professional, and in this case a professional is me, how we go about it, and how we tacitly, when we do this as part of our everyday work, when we're grading work, whether we're grading students' work or we're evaluating proofs of other mathematicians, this is all part of the tacit process of grading. And in writing out a proof, I've just tried to isolate the things that I implicitly and automatically look at in grading proofs, as indeed does any professional mathematician when they're grading a proof. Okay, and so and what I'm really saying is this is not really perfect in terms of giving reasons. Arguably, this one is more important than that one, for example. You know, it's just, overall, however, I'm going to give 4. Because these are sort of niggling. And the reason they're niggling is the person has laid out the fact that it's induction, has made it clear that they're assuming it for n, they've proved it for n plus 1. They've definitely stated the use of the induction hypothesis. As I say, this one would have been nice. I would have liked to see it, but this author presumably decided it really was patently obvious what's going on. This, I think, is an important one, because that's critical to the proof. This is not something that's typical. The fact that you can pull this in depends on the way the Fibonacci sequence is defined. And this is the only part in the proof where we make use of that fact. So you really should mention this one. So this one's important. And this one's important. And the reason is, until we've got to the last line, all we've really done is we've shown that the thing is true for n equals 1 and 2. Actually, for n equals 1, use the fact that F2 was what it was. So we've shown that we've proved it for the first case, or we've observed it for the first case. And then we've shown that if it holds at stage n, it follows that it holds at stage n plus 1. So we've proved 2 simple facts. One, a fact about the first one, or it's the first 2 Fibonacci numbers. And secondly, we've proved an implication from n to n plus 1. The conclusion is that this holds for infinitely many numbers, for all of the natural numbers. So somehow proving 2 statements, one simple observation and one implication, has proved that something is true for the infinitude of all natural numbers. Now, admittedly, induction has a natural, it's an obvious thing. There's a sort of a self-evident truth to the principle of induction. You know, you can think of it in terms of knocking rows of dominoes over or something. So, but the fact that the principle of induction, or that the method of induction has got a sort of intuitive obviousness to it, shouldn't obscure the fact that this is actually a deep result. Making a conclusion about an infinite set is non-trivial. You know, the Hilbert Hotel tells us that infinity is a very paradoxical domain. We've got to be very careful. So this actually holds. We can make the conclusion that it's true for all n because of the principle of mathematical induction. This, in other words, this is a big deal. This is a big, big deal. And when big deals are involved, you should mention them. You know, if there's a big guy in the room, it's polite, if not a matter of self-preservation, to observe that fact and make it clear. So you really do need to state the principle of induction here, to state that it's been used, or at least to say by induction. If I was feeling, if it wasn't for the fact that the rest of the proof was laid out so nicely, I might well have just deducted more here. But as it is, given everything else was laid out so well, and given that the proof is nice and elegant, and this is a slick proof, there's almost no superfluous lines in, then I think overall, simply deducting 2 marks is about right. So I've got 22 out of 24 for this one, and I feel reasonably good about this. There are a couple of small points. Well, it's one small point, one moderately big point, one really huge point. I think this is being generous, but I think this proof deserves generosity. Overall, I'm happy with that, and this is really how it splits up. Okay, let's go ahead and look at number 5. Well, number 5 is another of these Fibonacci sequence results. This one says that if we take the first n Fibonacci numbers add them together, the result is the next but one Fibonacci number. We skip over fn plus 1 and we go to fn plus 2 and we get the sum. Okay, so as is typical for these results, it's proved by induction. So let's see how the proof goes. For n equals 1, the left-hand side is f1. That's right, if n equals 1, there's no sum, it's just f1 itself. And the right-hand side is f... oh dear. If n equals 1, the right-hand side would be f3. And f3 equals 2. And 1 does not equal 2. So this isn't even true. It's not valid for n equals 1, which means the theorem's not valid. Oh, good grief. This is such an obvious mistake. It's a kind of mistake that anyone could make. It doesn't really reflect on their ability as a mathematician. It's just a human error. So common, this kind of thing. And yet, this is mathematics. Ultimately, in mathematics, things are right or wrong. I mean, if this was mathematics being used by an engineer to build a bridge, and the bridge falls down and people get killed, that engineer could be held liable, unjustifiably so. So, at the end of the day, we can't let things go through that are false. I'm going to have to give 0 for logical correctness before we go any further. I mean, it's just a plain false result. You could make the result correct. You could make the first result correct by subtracting 1. And in fact, it turns out, and I'll come back to this, that if you put a -1 in here, then the identity is true for all n. So there is a theorem here. And we get at the theorem by noticing what went wrong with this proof. Incidentally, this is very typical in mathematics. Often in mathematics, the statement of a theorem when it's proved isn't the one that the author originally tried to do. Very often in mathematics, we make a conjecture, we try to prove it, the proof has gone wrong, and so by analysing the proof, we kind of go back and change the statement. So it's often the case that statements of theorems actually come after the proof. Many proofs in mathematics began as proofs of something else that failed, but then the statement is changed to match what's being proved. So it's not always the case that the mathematicians sort of formulate theorems and then prove them. They often formulate a theorem, develop a proof, find out the proof is wrong, go back and restate the theorem so that the proof works for that restatement. Okay, that's just the way mathematics advances. It's part of the process of getting new knowledge. Okay, well, we're going to have to come back and sort of look at how the thing works as a proof, but it isn't a proof as it stands. Okay, but let's go through the mechanics of it and see if all of the other steps are okay. So, assuming the identity holds for n, then what's going on here? This is a case of separate. I'll give grades for reasons later, but let's just mention that what's going on here is separate out the last term. Okay, that's the reason here. Sum up to n plus 1 is the sum up to n together with the final term. This is the induction hypothesis. That guy equals that. Incidentally, and I'm jumping ahead to when I corrected this, at this point there should be a -1 in here. And if we do that, it carries through. So the proof as we're going through it will work validly, providing we state the theorem correctly. Okay, so I'm not going to give double jeopardy deduction for this. We've already knocked a ton off for that. Okay, so the rest of the thing is actually the logic is correct in of itself, except for this glaring mistake at step 1, but that topples the whole edifice. So I'm going to give 4 for clarity because it's absolutely clear, well laid out. It's proof by induction. It stated the method at the beginning, so 4 for the opening. The conclusion is certainly stated. I'm going to give 4 marks for that. What's the problem I have with this is that it's not mentioned that this is an induction proof. And as I elaborated on at great length with the previous question, with question 4, the fact that something is, the fact that an infinitary statement the statement about something being true for all n, the fact that that follows from a couple of little facts, like an observation and a simple implication, that's a big deal. That takes us into the realm of the infinite. And what takes us into the realm of the infinite is the fact that we have this thing called the principle of mathematical induction, which is difficult to prove if you try to prove it, or you have to assume it as an axiom or some kind of a principle. So this is not a trivial thing. It's intuitively clear, I know, but it's not. It's by no means easy to prove it. So we're pulling on something powerful here. We should state that we're pulling on something powerful. Okay. Now reasons. I mean, I was addressing those as I went through. This one's missing. That's in. That's good. The fact that the definition of this result holds. I mean, when modified to make it true, it holds by virtue of the way the Fibonacci sequence is defined. So you should stipulate the fact that you're using that. This is good, using the induction hypothesis. So I've got something good here. We've got something good here. That's a bit of a problem. That should have been in. This one, again, this is a judgment call. I would like to see that there, but that's just me. And all other things being equal, I would have ignored that. But all other things aren't equal because this person's already missed this out. So got a missing reason here, but a couple of good ones here. So I'm going to give 2. Okay. I think that's about right. Overall valuation, the thing is false. I mean, I can't possibly give 4 overall for a theorem that's plain false. Much as I'm sympathetic for the fact that it was a simple slip, the most I can give is 2. And I think I'm being generous there, quite frankly, because it is a false result. On the other hand, the course is focusing on mathematical thinking and mathematical communication, the ability to formulate and present a proof. And there's lots of aspects to that. It's not just about whether things are right or wrong. High school mathematics is largely focused on, K through 12 mathematics is largely focused on things being right or wrong. We've moved beyond that now. Right and wrong is still an important factor, which is why I give 0 for this part. But there are other things we're looking at. So I'm going to be giving 16 for this one. Okay, that's 8 marks lost out of 24. So this person's lost 1/3 of the marks for this. So I think one could say that this is generous for a false proof of a false result. On the other hand, there's a lot of good stuff here. It was simply a silly mistake right here at the beginning. Okay, that was very unfortunate. Okay. Life's like that at times. Let's go on and look at number 6. Well, this is another one about the Fibonacci sequence. What does it say? It says that the nth Fibonacci number is at least equal to the number 3/2 to the power n minus 2. Okay, let's see how this person does this. We have, interesting way to start, making a statement about f1, which is equal to 1, true. I mean, I'm going to look at logical correctness. I'll just follow it through and see what this person's doing. And 2/3 is equal to 3/2 to the negative 1. Okay, well, I guess they're showing that it's true for f equals for f1. So maybe this is an induction proof, although there's no way of knowing just by looking at it. Right? Well, this is interesting. The person now goes on and, we usually with an induction proof, you prove it for n equals 1 and then you stop. This person's now proving it for f2. Well, let's see what they're doing. So they're saying f2 equals 1, which it does. And 1 is indeed 3/2 to the power 0, which is true, because anything to the power 0 equals 1. So the inequality is valid for n equals 1 too. Right? Absolutely correct. Now assume the inequality holds for n, where n greater than or equal to 2. So we assume, but we're not told that this is going to be an induction proof. This person just jumped in, so this is already not a proof. This isn't telling a story. It's presenting us with a who done it, or what's done it, or what are they doing. So this is going to be a mystery, where n's greater than or equal to 2. Okay, then let's see. Fn plus 1 equals Fn plus Fn minus 1. True. That's the definition of the Fibonacci sequence, although there's no explanation of that fact. That's greater than or equal to... Well, where's this coming from? Well, looking ahead to the fact that this person's almost certainly doing an induction proof but hasn't written it down, what should have been said here was for holes, the inequality holes up to and including n. That, I think, is what's meant here, because we're assuming we're using it for two cases here. We're using it for the two previous cases, and we're saying that is greater than or equal to that one, that's greater than or equal to that one, and then we're taking out a common factor. This is interesting. There's almost no reasons given for anything else, and suddenly the person makes the obvious statement that this is by algebra, which indeed it is, taking out 3 over 2 to the n minus 3 as a common factor. There's one of them there, and there's just a 1 there. Then 3 over 2 plus 1 equals 5 over 2. Now we're spelling everything out in gory arithmetical detail. 5 over 2 is 10 over 4. Why you do that? Well, because then you can put a 9 over 4 here and make it smaller, and a 9 over 4 is a 3 over 2 squared, which gets you everything back to 3 over 2, which establishes the inequality for n plus 1. Okay, well, this person can certainly manipulate fractions. Well, that's already impressive, because a large percentage of the world's population has trouble dealing with fractions and inverting fractions and things. So this person has a lot of procedural skill with fractions. But is it a proof? Heavens, no. I mean, there's so much missing here. I'm going to give 4 for logical correctness, because the manipulations and the logic and everything was fine. As a professional mathematician able to figure out what's going on, I recognised fairly early on that this was an induction proof, but no thanks to the person writing it down, just because I've got a lot of experience. Nevertheless, I'm going to give 4 for the logical correctness. I'm also going to give 4 for the clarity, because it was sufficiently well laid out that once I realised that there's an induction proof going on here, I was able to follow the steps. So I didn't have to sort of bury myself in a morass of details to find out what was going on. It was clear. Opening. Well, there wasn't one. There absolutely wasn't one. This person just jumped straight in, and did so very obscurely, because even if looking at the first case indicates that we're doing induction, why look at the second case? We almost never do that in induction. And then we had to make a modification to even make sense of what was going on. So no opening. What about the conclusion? Well, no, there isn't a conclusion. What the person presumably should have said, or maybe meant to but didn't, hence, by induction, we could simply say the theorem is proved. That's fine. That's absolutely fine. The theorem is proved. Okay, that's all right. But it's missing. There's no conclusion stated. Going to be a 0 here. Reasons. There aren't any. There aren't any reasons. Simply no reasons. I mean, this one doesn't. I'm not going to give credit for that. That's just a. Here we should have said something like, well, by the induction. Well, actually, there's 2 things. By the definition of the Fibonacci sequence, is the first equality. Okay. And the second one is the induction hypothesis. This is by the definition of the Fibonacci sequence. It should be said. I mean, this is so self-evident the way it's written, because this is literally the definition. You could maybe let this person have some leeway if everything else was good, but nothing else is good. So I'm not inclined to give credit generously when there's so much lack of reasons given. This is the induction hypothesis. Applied twice, okay, once for that one and once for that one, and then the rest is algebra. Okay, overall, The only, I do, if I simply leave it at that and say that this is just terrible, because it is terrible as a proof, the person gets 8 out of 24, and yet this is quite sophisticated by most people's standards. I'm going to give 2 for the overall, and I'm going to give some sort of compensatory credit in here for the fact that this person's done some really intricate manipulations. There's some intricacy in here. This is not trivial. But it still just gives 10 out of 24. I mean, this is a low mark. Now, in terms of a grade for mathematical dexterity, that would be low. This person clearly has considerable mathematical dexterity. But proving things and communicating things in mathematics is much more than dexterity. It's about telling a story, it's giving reasons, it's establishing why something's true. I'm prepared to believe that this person convinced themselves that this is true and they understood why it was true. But what they haven't done is express that fact properly. This doesn't even come close to being a proof. As a proof, this one sucks. I mean, this is just not a proof at all. Okay. No mention of reasons. We've still got this mystery of why did this person do the first 2 cases? Well, that was actually a good observation. Mostly with induction proofs, you have to prove it's enough to prove the first case. But this one, you have to prove 2 of them, because if you look at the induction step, it uses it twice. You have to use it at the 2 previous cases. So in this case, the induction step depends on having it twice. You've got Fn greater than or equal to that, and you've got Fn minus 1 greater than or equal to that. So we've got 2 instances of the induction hypothesis here. Well, the induction hypothesis has to be pulled in twice. We use 2 inequalities. So you have to prove the first 2 cases, and you also have to, when you're making the assumption, you're not just assuming it for n, you're assuming it for n and n minus 1. Okay, you're assuming it for n and n minus 1. And the simple way to say that is you're assuming it up to and including n. So there's a lot in terms of missing reasons here. The fact that this person does what he or she does indicates to me that they almost certainly understand these issues. Simply observing you have to do it for 2 cases is significant. So I've got a lot of sympathy with this person. They've obviously thought deeply. I'm convinced actually that they know what they're doing and they know why they're doing it. Otherwise they wouldn't have done this. So the low mark here doesn't reflect that this person isn't good in terms of doing the mathematics for themselves. It reflects the fact that we're talking about the articulation and the expression of mathematical thinking and communication. So this would be a salutary lesson for the person to say, look, you're good. Make yourself like a professional. You've got the ability. Do the right thing, learn how to express things, learn how to communicate things to others. There's room in the world for a small number of brilliant mathematicians who are really bad at communicating. They often win prizes, we're glad they're there, but this is a course to sort of get everybody up to a nice level, a nice usable level of mathematics and mathematical thinking. And so I'm focusing on different things in this course. And in terms of what we're looking for in this course, 10 is actually about right. Even though in this, what I would do with it in a real, if I'd seen this in a real situation, I would have sat down and talked with the person and said, look, you've got a lot of ability. You really have got some talent. Let's work with that talent and let's develop the technique you need in order to become a functioning professional. If you're truly brilliant, we'll give you huge amounts of slack and we'll overlook the fact that you can't write a good proof if your life depended on it. But that's a small percentage of people. Most people have to make their living by collaborating with others, by working with others, and by being good communicators. And this course isn't really focused on the brilliant person. The brilliant person we take aside and we deal with them separately. This is focused on getting everybody up to an acceptable level. So low grade overall, but just this is not a good proof. It's simply not a good proof. It's not really a proof at all. Okay. And we've taken account of that appropriately. So a sad way to end a problem set. On the other hand, this person looks as though they can probably take care of themselves. Okay.
How did you get on with assignment 9? There was a lot there, so you might not have been able to finish it yet. Don't worry, you can finish that later. You won't need any of it for this final lecture, where we're going to apply our mathematical thinking to studying the real numbers. Incidentally, if you're not familiar with elementary set theory, you should look at the special course reader on the subject before you proceed with this lecture. Numbers arose from the formalization of two different human cognitive conceptions, counting and measurement. Based on fossil records, anthropologists believe that both concepts existed and were used many thousands of years before numbers were introduced. As early as 35,000 years ago, humans put notches into bones, and probably wooden sticks as well, but none of those have survived, or at least haven't survived and been found, to record things, possibly the cycles of the moon or the seasons. And it seems probable they used sticks or lengths of vine to measure lengths. Numbers themselves, however, abstractions that stand for the number of notches on a bone or the length of a measuring device, appear to have first appeared much later, around 10,000 years ago, in the case of counting collections. These activities resulted in two different kinds of number: the discrete counting numbers used for counting and the continuous real numbers used for measurement. The connection between these two kinds of numbers was not finally put onto a firm footing until the 19th century, with the construction of the modern real number system. The reason it took so long is that the issues that had to be overcome were pretty subtle. Though the construction of the real numbers is beyond the scope of this course, I can explain what some of the problems were. The connection between the two conceptions of numbers was made by showing how, starting with the integers, it's possible to define first the rationals and then use the rationals to define the real numbers. Starting with the integers, it's fairly straightforward to define the rational numbers. A rational number is, after all, simply a ratio of two integers. Well, it's actually not entirely trivial to construct the rational numbers from the integers. You want to define a larger system, the rationals, that extends the integers by having a quotient, a over b, for every pair ab of integers, where b is non-zero. But how would you go about defining such a system? In particular, how would you respond to the question, what is the quotient a over b? You can't answer in terms of actual quotients, since until the rationals have been defined, you don't have quotients. If you're interested, you can find an account of the construction of the rationals from the integers in many books and on the internet. But I'll mention once again that you should be cautious about mathematics found on the internet. The point is, constructing the rationals from the integers, while it has some subtleties, is fairly straightforward. Constructing the reals from the rationals, however, is a lot more difficult. In this final session, I'll look at some of the issues involved in constructing and using the real numbers. We'll start by looking at some properties of the rationals.
With the rationals, you've got a system of numbers that's adequate for all real-world measurement. This is captured by the following property of rational numbers, and I'll give it as a theorem. If r and s are rationals with r less than s, then there's a rational t such that r is less than t is less than s. Okay, before I prove that, let me give you a little note. This property is called density. The rational line is dense. So if we have the rational line, what density says is that whenever you have a rational number r and another rational number s, we can find a rational number t in between r and s. Okay, let's prove that. Well, why don't we just take t to be the mean of r and s? Well, clearly r is less than t is less than s. And the only question is t a rational number? Well, it obviously is, but let's prove it. Let r be equal to m over n, s equal to p over q, where m, n, p and q are integers. Then t is equal to a half m over n plus p over q, which equals mq plus np over 2nq. Of course, mq plus np and 2nq are integers, so that proves that t is in q. Which was pretty obvious anyway, but since we are focusing on how we prove things in mathematics, at this stage I thought it was a good idea to actually go through a formal proof that one could give. And density means that the rationals are good for doing measurements, because what density tells us is that we can get rational numbers as close as we wish to any particular length. You know, if this is slightly too small, if this is slightly smaller than a particular length, and if this is slightly larger, then we can always find another rational that's even closer. On the other hand, density does not mean that there are no holes in the rational line. Let me just emphasize that the proof finished here. So that was the end of the proof. And with this remark, we're on the edge of an abyss of understanding. At least it's an abyss if you haven't seen this before. This is there's some interesting stuff coming up. It's stuff that wasn't fully worked out until the late 19th and early 20th centuries. As an example of a hole in the rational line, there's root 2. And let me just make this a little bit more precise. Suppose I define A to be the set of all those rationals x which are either negative or non-positive, or x squared is less than 2. And let me define B to be the set of all those rationals such that x is positive and x squared is greater than or equal to 2. Let me draw a little diagram. Okay, we'll have 0 here. And A is a set that's going to go, out to infinity at the left. And it's going to go to some point here. That's going to be A. Let's delineate things here. So A is going to be a set here. B is going to be a set, also is going to go out to infinity. And we're going to have every element of A to the left of every element of B. And here is where root 2 would be if root 2 existed in the rational line. This is the rational line, Q. Okay. So we've got the rational numbers, and I've split the rational numbers into two sets. A, which is everything negative and anything whose square is strictly less than 2. And B is everything which is positive and whose square is greater than or equal to 2. And this splits the rational line into two pieces. Okay. So clearly, A union B is a rational line, but, and here's the kicker, A has no greatest member, and B has no smallest member. Now, it was by considering situations like this that mathematicians in the late 19th and early 20th century were finally able to figure out a rigorous construction of the real number system, a theory of real numbers. But it took a couple of thousand years to get to that stage from the time when the ancient Greeks discovered that the square root of 2 was irrational. What this tells us is that the rationals are inadequate. Can't even spell inadequate now. Inadequate to do mathematics. Why do I say that? Because in Q we cannot solve the equation x squared minus 2 equals 0. So the rationals are fine for measuring things. I mean, they're fine for doing carpentry and for doing various kinds of geometrical things and for building things and for tracking the stars and doing astronomy and so forth. That's fine, so long as we can get by with, say, the 10 decimal places of accuracy or whatever we need. But if we want an actual solution of equations, then the rationals aren't good enough, because even a simple quadratic like x squared minus 2 equals 0 cannot be solved. The way out of this problem, and this was the work that was done in the late 19th, early 20th centuries, was to say, well, we've got several different systems of numbers. We've got the natural numbers, then we've got the integers, where we add negative numbers, or we had negative versions of the natural numbers. Then we have the rationals, where we have quotients of integers. These are good for counting. These are good for doing arithmetic when we want to have negative values, like my bank account. These are good if we want to measure things. If we want to do mathematics, we have to go one step further to the rails. By the way, this was in many ways, it was a historical progression. Not quite, because Z sort of got in a different way. But going from the natural numbers to the integers to the rational numbers to the real numbers, that was largely a historical progression. And it was done in order to have greater expressivity. When arithmetic began about 10,000 years ago, it was exclusively the natural numbers, and it was introduced to provide a monetary system in some area, in what was known as the Fertile Crescent region, present-day Iraq essentially. And then as bankers came along and they wanted to keep track of people's negative bank accounts, I'm being a little bit flippant, but that was pretty close to what happened. Negatives were introduced, rationals were introduced to measure things in the world, and then the real numbers are required to do mathematics. And to get the real numbers from the rational numbers, what mathematicians in the late 19th century did was find a way to fill in the holes. There were these holes in the rational line, and the reals were constructed by filling in the holes. Okay. Fill in the holes in the rational line. Well, I'm going to give you a few more details about how this was done. But I should mention that there were some mind-blowing elements to this. There were some really interesting surprises in store for the mathematicians that made this step. One was the fact that, however you count it, there are more holes in the rational line than there are rational numbers. Now, there are infinitely many rational numbers. Nevertheless, the infinitude of the holes in the rational line vastly outweighs, on an infinite scale, the infinitude of the rational numbers themselves. It was a super infinity of holes. That meant that when those holes were filled in, the number system that was obtained, the real numbers, contained incomparably more numbers than the rational numbers. They're both infinite, but mathematicians had to develop systems for counting infinite collections in order to cope with this. And it turned out that the real numbers, as a set, has infinitely many more numbers than the rational numbers in an infinite sense. Now, making that precise is definitely beyond the scope of this course, but I will be able to get into the beginnings of the considerations that led to those surprising conclusions. Okay, Well, that's all coming up within the next few minutes. Well, before I give you any details of how the real numbers were constructed, I need to do a little bit of preliminary work. I need to introduce, or reintroduce if you've seen it before, the notion of intervals of the real line. Let A, B be real numbers with A less than B. The open interval AB, written with parentheses this way, is the set X in R such that A less than X less than B. So a simple diagram would be this. We've got a point A, we've got a point B. This is now the real line. And the open interval AB is a set of all the numbers strictly bigger than A and strictly less than B. But the interval excludes these two. So it's an interval of the line, it's a segment of the line, but it excludes the two endpoints. The closed interval AB, written with square brackets like this, is the set X in R, A less than or equal to X, less than or equal to B. So the diagram for this would be we've got A, and we've got B. And this interval actually includes the two endpoints. So the distinction between these two is that A and B are elements of the closed interval, but A and B are not elements of the open interval. Now, this may seem like splitting hairs. After all, this is a segment of the real line, so there are infinitely many numbers in here. In fact, as I just indicated a moment ago on that previous page, the infinitude of the real numbers in there is mind-bogglingly bigger than the infinitude of the rational numbers in there, and the rational numbers in there is already an infinite set. So we've got infinitely many numbers in here, infinitely many points in this line, and yet I'm splitting hairs between these 2 points at the end. That sounds like splitting hairs, but take it from me, this is a big, big, big difference or distinction. The distinction between these two turns out to be huge, and it's closely bound up with the reasons why the rationals are inadequate to do mathematics and the reals are actually good for doing mathematics. Well, we're going to use this notation in order to talk about what had to be done to go from the rational numbers to the real numbers. I'm not going to do the construction, it's way too deep for a course like this. It's first and second year university level mathematics, and it takes most of us a long time to understand it. But I will open the door to such a study. There are some variations on the notation. Let me give you those. I'm not doing any mathematics here, I'm just giving you some notation. Okay. One of them is what's known as a half open or half closed intervals. So we have half open intervals or half closed, they're the same thing really. Such as AB, where that's closed and that's open, square brackets, parenthesis. That's a set of all X in R such that A less than or equal to X less than B. And the other way would be A, B this way is a set of all X in R such that A less than X less than or equal to B. And this one is called left closed, right open, and this one is called left open, right closed. So the word closed means you include the endpoint, and open means you exclude the endpoint. So if it's left closed, the left endpoint is included. If it's right open, the right endpoint is excluded. And one more bit of notation we sometimes include intervals that stretch all the way to infinity, and we write things like negative infinity a is the set of all x in R, well, such that x is straight left than a. It's everything to the left of a. Or I might write something like negative infinity a with a closed bracket here, with a square bracket to denote a closed part of the interval. That would be the set of all x in R, such that x less than or equal to a. Similarly, I could have a going out to plus infinity, would be the set of all x in R, such that x strictly greater than a. Or I could have closed a infinity, which is the set of all x in R, such that x greater than or equal to a. And with one final remark, I'm done with this summary of notation. We don't have something together with infinity closed, and we don't have infinity closed together with something. You can't have infinity next to a square bracket, because infinity is not a real number. So there's no possibility of this guy, whatever it is, being an element of the interval. Notice that when I defined these, there was no mention of infinity. I just said all those x's to the left of a. Ditto, ditto, ditto. Okay, with this notation available, we can now move ahead and look at how we go from the rational numbers to the real numbers. We can look at what goes wrong with the rational numbers in a deep, precise sense, and I can give you some indication of how we would go about rectifying the deficiencies of the rational line. Okay, coming up next. Well, the key property that the real numbers have that the rationals don't have is what's known as the completeness property. In a nutshell, the completeness property is what makes the real numbers great for doing mathematics, and the absence of which makes the rationals inadequate for doing mathematics. So it was a formulation of a system of numbers that satisfied the completeness property, and indeed a formulation of the completeness property itself, that was one of the crowning glories of late 19th century mathematics, that set up the 20th century mathematics upon which most of modern science and technology depends. So this is a big deal, folks. Given a set A of reals, a number b such that for all a in a is less than or equal to b is said to be an upper bound of a. We say b is a least upper bound of a if, in addition, for any upper bound c of a, we have b less than or equal to c. Well, duh. What else would a least upper bound be? It's the least one. It's an upper bound and it's the least one. Why am I making such a big deal of this? Because it was by making a big deal of this that mathematicians were able to formulate this, and it was by formulating this that mathematicians were able to construct the real number system, which meant that after 2,000 years of effort, mathematicians finally had a system of numbers that was adequate for doing modern science, physics, technology, etc., etc., etc. In mathematics, it's often the case that something that seems trivial turns out to be fundamental and have enormous consequences. And this is one of those moments. Okay, so I'm being very precise about the definition because mathematicians found that it was only by being precise that they were able to figure out how to proceed. The notation we use for least upper bounds is this, least upper bound of A. So the notation for the least upper bound of a set A is lub A. Let me make a note. We can make the same definitions for n, for Z and for Q. The completeness property of the real number system says that every non-empty set of rails that has an upper bound has a least upper bound. And let me stress that that least upper bound is in the set of real numbers. This one simple, elegant statement is the key to the real number system and to most of modern mathematics. Before I go any further, you really ought to take a look at assignment 10.1. I say you should at least look at it. Ideally, you should try to do it, or at least try to do as many of the exercises as you can. You need to be familiar with the background material about upper bounds and least upper bounds before we progress. We're about to meet material that most beginners at university level mathematics find incredibly difficult. You know, to go back to my favourite example about riding a bike, it's one of those transitions in life where it seems impossibly difficult until you get the hang of it, and then it suddenly seems remarkably straightforward and you wonder why it took you so long. So it's not that we're facing something terribly difficult, it's just that we need to go through some kind of a shift, going from thinking it's impossible to thinking, well, okay, that seems straightforward. It's one of those difficult transitions that when you look back are actually, with retrospect, don't seem so difficult at all. We're facing one of those, and I strongly recommend that you take a look at that assignment before you go any further. Otherwise, you might very rapidly find yourself lost in the next few minutes of lecture. Okay? Having said that, I'm going to take a pause now, and then I'll come back in the second video connected with lecture 10. And I'll see you then. Welcome back, as they say in the media. Where the correct answers are number 2 and number 3. 5 is not the maximum element of this interval. In fact, 5 is not an element of this interval at all. This, remember, is a set of all x in the rails such that 0 strictly less than x strictly less than 5. So 5 itself is not a member of there. So not only is it not the maximum element, it's not an element at all. 7 is actually not a member of this interval, for the same reason as 5 wasn't an element of this interval. But nevertheless, 7 is still the least upper bound. There is no smaller upper bound of that interval than 7. So it is a least upper bound. So least upper bounds are not the same as maximums. And in this case, 0 is a member of that set. That interval is defined, remember, as a set of rails such that 0 less than or equal to x less than or equal to 1. And in this case, the end point 0 and 1 are elements of the interval. So 0 is in there, and it's clearly the minimum element of that interval. Where the answer is the first one is correct. This is what it means to say that the rational line is dense. Between any two rationals, you can find a third one. The second one is actually true, but it doesn't express density. It doesn't express density because whether or not there is an irrational number between two rationals is sort of irrelevant. The question is about the rational line being dense. This is actually making a statement about the real line. So it's true, but actually irrelevant to the notion of density of the rational line. So that one's not true. I mean, that one's true, but it's not the answer to the question. And this one, that's actually expressing the notion of completeness. Now, if by least upper bound we mean least upper bound in the rationals, in the rational line Q, then that would say that the rational line is complete, which is false. If, however, we interpreted this to mean every set of rationals that is bounded above has a least upper bound in the real numbers, then that would be an instance of the completeness of the real line. And this issue about the existence of least upper bounds is what distinguishes the reals from the rationals, and it's what makes the reals a very powerful system for doing advanced mathematics and calculus in particular, and demonstrate, and the fact that the rationals is not complete is what demonstrates the impoverished nature of the rationals in terms of mathematics and doing things like calculus. Okay, how did you get on? What I want to do now is, well, actually really what I want to do is introduce the beginnings of the subject known as real analysis. Now, this isn't real analysis as opposed to fake analysis. Real here is essentially short for real numbers, or for the real number system, if you like. It's the analysis of the real numbers. And I'm going to begin with a theorem. The rational line is not complete. Now, if you've done that assignment 10.1 that I asked you to do, you should be familiar with what that means, but let me remind you, in case you decided to play it risky and go ahead without doing that assignment. Well, let me just remind you that completeness means if a subset of reals has an upper bound, then it has a least upper bound in the set of reals, that is. That was completeness as applied to reals. But as I mentioned at the time, these notions also apply to any set. So in terms of the rationals, completeness would mean if A is a set of rationals having an upper bound, then it has a least upper bound in the rationals. What this theorem says is that this property does not hold for the rational numbers. Remember, R stands for real numbers here, but if I replaced R by Q and talked about the rational numbers, then this property would not hold. It does, however, hold for the real numbers. That is the completeness property for the real line. We won't be able to prove that, but I'll be able to indicate how it's possible to construct the reals in order to make it possible to prove that. Okay, here's the proof of the theorem. Let A be the set of all rationals R such that R is non-negative and R squared is less than 2. Now already you can probably sense what's going on. This is going to hinge around that property that the square root of 2 is irrational. So let me draw a picture. Here's 0. Here's 2. A is going to be a set where everything is going to be greater than or equal to 0. And A is going to go up to some point less than 2. Well, A only contains rationals less than 2, whose square is less than 2, so those rationals themselves are less than 2. So it's going to be something like this. And we all know that lurking in there somewhere is the square root of 2. I should stress that throughout this argument, the argument I'm about to give, we're talking purely about the rationals. So I'm not going to be talking about any reals. This is why I sort of put this down here somewhat faintly. This is to help guide our intuition. This is to sort of motivate what's going to go on. But the entire argument I give is going to be in terms of rational numbers, not real numbers. I deliberately did not write R less than the square root of 2 because there is no such thing as a square root of 2 in the rationals. I'm using sets of rationals in this argument. It's an argument about the rational numbers, not about the real numbers. Okay, well, A is bounded above. For example, 2 is an upper bound. We only need to find 1, and 2 will do just fine. I will show that A has no least upper bound. That would mean that A is a set of rationals which has an upper bound but no least upper bound, and hence the rational line is not complete, because completeness would say that any set of rationals with an upper bound in the rationals has a least upper bound in the rationals. Well, how would I show that there's no least upper bound? Well, let x in Q be any upper bound of A and show there's a smaller one. Again, let me stress smaller one in the rationals. Remember, we use the letter Q to denote rationals because Q stands for quotient, and rational numbers are numbers that are quotients of integers. We can't use the letter R for rational because R is used for real numbers. Unfortunate, I know, but there we are. Well, since we're talking about the rationals, that upper bound x is going to be of the form P over Q, where P and Q are integers. In fact, they can be natural numbers, because this set A is positive integers, or at least non-negative numbers. This set A is non-negative rationals. It's everything's to the right of the origin, so everything's positive. So I don't have to worry about negative numbers here. So these two integers can be chosen positive. And I want to show that there's a smaller upper bound. Well, let's suppose x squared is less than 2. It's either less than 2 or it's greater than or equal to 2. It's one of the two. Let's just see what happens if x is less than 2. In that case, looking at this equation, 2q squared is bigger than p squared. Now, as n gets larger, n squared divided by 2n plus 1 increases without bound. So we can pick an n in n so large that n squared over 2n plus 1 is bigger than p squared divided by 2q squared minus p squared. Now, you might not see where I'm going with this, but hopefully you can believe everything I've said. Okay, we're assuming x squared is less than 2. We'll actually, in a moment, we'll arrive at a contradiction. So the conclusion I'm going to get out of this is that x squared is in fact not less than 2. But this is where we're starting. If x squared is less than 2, then because of that definition, 2q squared is greater than p squared. Okay, so 2q squared minus p squared is positive. That means this number is a positive number. And what I'm saying is that because we've got an n squared here and a linear term involving n here, the bigger n gets, this gets increasingly large. It gets as large as you want it to be. So I can pick an n big enough so that this number is bigger than that one. And if you rearrange that, you'll find that 2n squared q squared is bigger than n plus 1 squared p squared. Okay, I'll leave you to do the algebra for getting from there to there. Hence, n plus 1 over n squared times p squared over q squared is less than 2. Just rearranging that, taking those terms to the other side. Now let y be n plus 1 over n times p over q. Well, notice that y is a rational number. It's a quotient of integers. And y squared is less than 2, because this says that y squared is less than 2. By the way, this, by now you should have begun to smell why I started looking at this term. I was trying to get this number y. Remember, I started with an x as an upper bound, and I wanted to show that there's a smaller one, and I'm going to work towards that. And now I've introduced this y. Okay. So y is in Q and y squared less than 2. So y is an element of that set A. But wait a minute, y is equal to a number slightly bigger than 1 times x. So that means that y is actually bigger than x. So the number y that I've constructed is in the set A and yet is bigger than x. Well, that's a contradiction. Since x is an upper bound of A. That supposition must be false. So x squared has to be greater than or equal to 2. Okay, so what I've done is I've taken an upper bound of A. I'm going to show there's a smaller one, and as a first step towards doing that, I've shown by contradiction that that upper bound has to have its square greater than or equal to 2. Now I'm going to go ahead using this extra information to show that there's a smaller upper bound, and hence there's no chance of any x being a least upper bound. Let me recap where we've got to. We let A be the set of all rationals that are non-zero and for which r squared is less than 2. We let x be an upper bound of A, and we had x in the form p over q, where p and q are integers. Okay, so we have that, and our goal is to show that A has an upper bound smaller than x. Hence there cannot be a least upper bound, which would show that the rationals are not complete. And we just showed that x squared is greater than or equal to 2. Hence, since the square root of 2 is irrational, x squared is strictly bigger than 2. X is irrational, x squared can't be equal to 2, so it's strictly greater than 2. Thus, since x equals p over q, p squared is bigger than 2q squared. I'm going to use this fact to find an upper bound of A smaller than x. To do that, I'm going to pick n, an integer, so large that the following is true. N squared divided by 2n plus 1 is bigger than 2q squared over p squared minus 2q squared. i.e., rearranging that, p squared n squared greater than 2q squared times n plus 1 squared. So you just rearrange this, do a little bit of algebra, and you get this. i.e., p squared over q squared times n over n plus 1 squared is greater than 2. Again, you just rearrange that and do a little bit of algebra to get that. Let y be n over n plus 1 times p over q. Then y is an element of q, y is a rational number. It's a quotient of integers, so it's in q. And moreover, y squared is bigger than 2. Moreover, since n divided by n plus 1 is less than 1, y is less than x. Because p over q is x, and y is just this guy times x. So it's less than x. But for any a in A, A squared is less than 2 is less than y squared, so a is less than y. Hence y is an upper bound of a, which is smaller than x. Thus a does not have a least upper bound. And this proves the theorem. I guess my mathematics is better than my handwriting. This proves the theorem. Okay. Final remark, the construction of R from Q can be done in several different ways, but in all cases the aim is to prevent an argument like the above going through for R. And with that, you're at the very gateway to modern real analysis. For our final topic in this course, I'd like to say a little bit about real number sequences. These are connected with one of the ways of constructing the real numbers from the rationals, and they also give us a technique or a concept for doing an awful lot of work in real analysis. To put it another way, sequences of real numbers are a big deal in modern real analysis, which means they're a big deal in calculus. And anything that's a big deal in calculus is a big deal in science and engineering and technology. So, whichever way you cut it, sequences are a big deal. Now, what is a sequence? Well, in everyday terms, it's a list. 1, 2, 3, let's put some commas in here, of numbers. So we have a number, a number, a number, going on to infinity. The way we normally express this and try to capture this infinite extent here is by writing it an, where n goes from 1 to infinity. And this is what's called an infinite sequence. If you look in textbooks, you'll find a more formal definition that a sequence is a function from the set of natural numbers into the real numbers, but for the purposes of one of the kind of things I want to talk about here, it's enough to think of it simply as an infinite list of real numbers. For example, the sequence of natural numbers, 1, 2, 3, and so forth. That's an infinite sequence. In terms of our notation, I would just write that as n, for n goes from 1 to infinity. Or I could have the sequence that consists simply of an infinite sequence of sevens. 7 going on forever. That would be expressed in this way. Or I could have the following sequence: 3, 1, 4, 1, 5, 9, etc. Enumerating the decimal digits of pi. Well, there's no simple formula like this to capture this one. I have to use some expression like this. Or let me give you another example. I could have the sequence consisting of -1 to the n plus 1 from n equals 1 to infinity. That's a sequence that consists of +1, -1, +1, -1, +1, -1, etc. That's an example of what's known as an alternating sequence, meaning that the sign alternates as you go through the sequence. Okay, so that's what sequences are, just infinite lists of numbers. Now let's look at the following example. Look at the sequence consisting of the numbers 1 over n from n equals 1 to infinity. Okay, that's the sequence 1, a half, a third, a quarter, and so on. And the thing to notice about this is that the numbers get closer and closer to 0. In fact, they get arbitrarily close to 0. Or this one. 1 plus 1 over 2 to the n, from n equals 1 to infinity. That consists of the numbers 1 and a half, 1 and a quarter, 1 and an eighth, 1 and a 16th, etc. And these numbers get arbitrarily close to 1. And going back to this example here, the sequence 3, 3.1, 3.14, 3.141, 3.1415, 3.14159, 3.1415992, 3.1415926. That sequence gets arbitrarily close to pi. That's as far as I know the decimal expansion, by the way. So these sequences have the property that as you go along them, they get arbitrarily close to a fixed number. 0 in the first case, 1 in the second case, and pi in the third case. And there's a general property here that we're going to capture by way of a definition. If the numbers in a sequence n from 1 to infinity, get arbitrarily closer to some fixed number a, we say that sequence tends to the limit a, and write n arrows a as n arrows infinity. An alternative notation is we sometimes write it this way: limit as n goes to infinity of a sub n equals a. Not all sequences tend to a limit. Look at this one, for example, this alternating sequence. +1, -1, +1, -1. That doesn't approach any particular number. It bounces back and forth between +1 and -1. This one, in a trivial sense, does tend to a limit. This one tends to the limit 7. It doesn't just tend to it never gets away from it. This one doesn't tend to a limit at all. These numbers get bigger and bigger and bigger. We would sometimes say that the sequence tends to infinity, but that's beyond the scope of the limited amount I want to talk about sequences in this course. The point is, some sequences don't tend to a limit. Other sequences do tend to a limit. Okay, let's move on. Well, so far everything's been very intuitive. Let's get a little bit more formal now. We've got a sequence an, n from 1 to infinity. The intuitive explanation, or the intuitive description I gave of this, that the sequence, or the members of the sequence, tend to a limit a as n tends to infinity, that sort of corresponds fairly roughly to the fact that the absolute value of an minus a becomes arbitrarily close to 0. Boy, my writing really is a problem, isn't it? Close. Now let me give you the formal definition. And the formal definition involves being precise about what that means. an tends to a as n tends to infinity if and only if, for all real numbers epsilon greater than 0, there is a natural number n such that for all m greater than or equal to n, absolute value of am minus a is less than epsilon. And now, perhaps for the first time, you see why we spent so much effort understanding quantifiers and being particular about the order in which quantifiers appeared. This definition is absolutely crucial in real analysis. It's absolutely crucial to our definition and our understanding of the real numbers. And that means it's absolutely crucial to calculus. And hence it's absolutely crucial to physics, science, engineering, technology, etc., etc., etc. This is the real stuff, folks. Okay, let's try and understand how that captures this intuition. The geometric intuition we have, I think, is fairly clear that you're going along a sequence and the numbers get closer and closer and closer to some fixed number. How does this somewhat complicated looking expression capture that in a precise formal way? Well, let's peel away this part for a minute. By the way, it's traditional in mathematics to use epsilon in this context. And at the back of your mind, you should think that epsilon is not just positive, but it's very small and positive, like a tenth or a hundredth or a millionth or a zillionth or whatever. As you'll see when I go through this, it's when epsilon becomes small but remains positive that this thing kicks into power. Okay, so let's forget that bit. Let's look at the other part. Exists an n such that for all m greater than or equal to n, absolute value am minus a is less than epsilon. And I've avoided mentioning explicitly the set n now. Notice that in the first place I didn't mention that m was also a natural number because the context makes that clear. N is a natural number and we're talking about all m's greater than or equal to n. And when we discussed quantifiers earlier on, I pointed out that mathematicians do this kind of simplification all the time. So it makes it easier to read, that's all. Okay, what does this part mean? So we've been given an epsilon, we'll assume. We're given some positive number epsilon, and at the back of your mind, think of it as a small positive number. What this means is that from some point onwards, so from some point n onwards, all the members of the sequence are within a distance epsilon of a. So all the numbers in the sequence an, n equals 1 to infinity, are within a distance of epsilon from a. You still with me? Now let's see what this thing means when we have the whole expression. This says that for any epsilon greater than 0, this thing holds. So for any epsilon 0, there is a point such that from that point onwards, all the numbers are within a distance epsilon from a. As I mentioned a moment ago, the intuition here is that we can take epsilon greater than 0 as small as we want. So let me draw a picture now. We've got some number a, and there's a sequence bouncing around here somewhere. Maybe it's coming in from the left, from the right, or maybe it's bouncing around. But there are these numbers a1, a2, scattered along this line here. Now we're given an epsilon greater than 0, so let's suppose it's down here. So here's, let's say negative, here's a minus epsilon, and here is a plus epsilon. Okay. I've just got a distance epsilon to the left and a distance epsilon to the right. And the argument I'm about to give will hold for any epsilon. At least that's what this says. So I'm given an epsilon and I look at this interval. And what the rest of this formula says is that from some point on, all the elements of the sequence are in here. If I take a smaller epsilon, let's do it, say, here and here. Let's call it epsilon prime. So that would be a minus epsilon prime. And here would be a plus epsilon prime. So I take a smaller epsilon, still positive, so the formula will hold for the epsilon prime. There will be some point from which all the elements of the sequence beyond that point are within this region. And then I could take an even smaller one, and an even smaller one. Notice that the n depends on the epsilon. Remember that example about the American Melanoma Foundation? Wasn't a problem for them getting the quantifiers the wrong way around. If we got the quantifiers the wrong way around here, we'd be in big trouble. This wouldn't work. The point is, given an epsilon, you could find an n. For each epsilon, you may have to go further out in the sequence until you come to a point where all the elements are within that distance. But what this says is that you can always, by going sufficiently far out in the sequence, reach a stage where all of the numbers in the sequence from then onwards are within a given distance of A. And you can do that for smaller and smaller and smaller A. And that's capturing this intuition. And it does it beautifully and elegantly and with enormous power. Okay? Let me give you a couple of examples. First example. Let's look at the sequence 1 over n. N goes from 1 to infinity. Now we know that 1 over n tends to 0 as n tends to infinity. Let's prove this rigorously in terms of the definition of limits that I just gave. Okay, so I'm going to prove that fact. What I have to show is that for all epsilon greater than 0, all real numbers epsilon greater than 0, there's an n in the natural numbers such that for all natural numbers m greater than or equal to n, absolute value 1 over m minus 0 is less than epsilon. Well, let's simplify that. For all real numbers epsilon greater than 0, there is an n, and let me just drop that explicit mention of the natural numbers. For all m greater than or equal to n, that just says absolute value of 1 over m less than epsilon, which actually just means 1 over m less than epsilon, because m is a positive integer. Okay, so I have to verify this in order to prove that. Okay, so how do I verify that? Well, let epsilon greater than 0 be given. Another way of saying it would be to say let epsilon greater than 0 be arbitrary. Different way of saying the same thing essentially, at least in this circumstance. What I need to do is find an n such that for all m greater than or equal to n, 1 over m is less than epsilon. Well, pick any n such that n is bigger than 1 over epsilon. Epsilon, if epsilon is a very small number, this will be a very large number, so I might have to pick a large n. But pick such an n. Now, intuitively, you know that since the natural numbers go on forever, as it were, getting bigger and bigger, that's always possible. That actually uses a principle of mathematics called the Archimedean property, so named after Archimedes. See assignment 10.2 for a little bit more about that. So pick an n big enough so that n greater than 1 over epsilon. Then, if m greater than or equal to n, 1 over m is less than or equal to 1 over n is less than epsilon. And we're done. Notice that the choice of n depended on epsilon. Given an epsilon, I picked my n in terms of the epsilon. Please note American Melanoma Foundation. At least when you apply quantifiers in mathematics, it's a big deal if you get them in the wrong order. The n depends upon the epsilon. The smaller the epsilon is, the bigger the n has to be. Intuitively, for this sequence, the smaller the tolerance you impose on the number being close to 0, the further out in the sequence you have to go, the bigger the n is, before you're within that tolerance. So quantifier order matters. The choice of n depended on epsilon. Different epsilon, different n. Okay, let me give you one more example. And let me look at this sequence. N over n plus 1 from n equals 1 to infinity. That's the sequence 1/2, 2/3, 3/4, 4/5, and so on. And let me prove, in terms of the definition, that n over n plus 1 tends to 1 as n tends to infinity. Now, intuitively, it obviously does. These numbers get closer and closer and closer to 1. But to prove that, what I have to show is the following. For all epsilon greater than 0, there is a natural number n, such that for all natural numbers m greater than or equal to n, absolute value of m over m plus 1 minus 1 is less than epsilon. Okay, I'm going to prove it the same way as before. I'm going to assume I'm given an epsilon, then I'm going to find an n dependent on epsilon that makes this thing true. Let epsilon greater than 0 be given. We need to find an n such that for all m greater than or equal to n, m over m plus 1 minus 1 in absolute value is less than epsilon. Well, I'm going to pick n so large that n is bigger than 1 over epsilon. That's actually the same choice as in the previous example. It just works out that way because I'm using very simple examples. In more complicated examples, the choice is perhaps not quite so simple as straightforward as this. Okay, but let's see why that one works in this case. Then for any m greater than or equal to n, I've got the following. M over m plus 1 minus 1 in absolute value equals minus 1 over m plus 1 in absolute value. Just work that out as a single fraction, which is just 1 over m plus 1, which is less than 1 over m, which is less than or equal to 1 over n, because m is greater than or equal to n, which is less than epsilon. And we're done. Okay, you should now be in a position to attempt the questions on assignment 10.2. Bear in mind that the two examples I've given were particularly simple ones, where the choice of the n was very simple. You won't always be so lucky. You might have to work a little bit harder to find the n. But my focus here, as it's been throughout the course, wasn't so much on the details and on the procedures. If you graduated from high school, I assume you can do mathematical procedures, you can do the algebra. The focus is on the reasoning. In particular, in the context of sequences, the key thing is how, given an epsilon, you have to choose an n that depends upon it. It's this quantifier switch that's really crucial. For all epsilon, there is an n. If you go on to further studies in mathematics, in particular in real analysis, you're going to see variants of this kind of definition, not just for limits of sequences, but for the definition of continuity, and then when you come to look at the formal definitions of integration and so forth. So you're going to come across this kind of a definition a lot. Coming up with this formulation was one of the jewels in the crown of late 19th century mathematics. Absolutely brilliant piece of work, and it gave rise to pretty well all of modern mathematics, at least all of modern mathematics that's to do with real numbers. Okay, well, good luck with assignment 10.2.
Well, you made it. All you have to do now is complete the final assignment and you should be well set for taking college-level mathematics courses, or for simply reasoning more effectively in your job or in your everyday life. Since you got this far, I'm sure you'll complete these last steps, so let me offer you my congratulations now. These massive online courses are still hugely experimental, so simply sticking with us and finishing the course is an accomplishment all by itself. Future generations of students will surely have it easier in some ways. What they won't find easier, however, is the material itself. Learning facts is relatively easy. Learning to think a whole new way is extremely difficult. However well you think you've mastered the material, you should feel pleased with completing the entire process under your own motivation. As a lifelong teacher, much of my motivation and reward has been getting to know each generation of students and working with them, helping them overcome difficulties, and then seeing them succeed. With a MOOC, that regular close contact's absent, and I miss it. On the other hand, being able to reach tens of thousands of students, as opposed to 25, brings its own reward.
The next 2 weeks are devoted to the test flight process. See the website for details. Okay, well, we're at the end of the course now, so in keeping with my basic philosophy behind the course, I'm only going to answer one or two of the questions from assignment 10. Since there's no more lectures to come, no more material to come in this course, there's nothing that's going to depend upon on anything now. You'll only need this stuff for future courses or for using it in the real world. So I'm going to leave most of the questions on assignment 10 for you to do in your own time and to resolve them with colleagues and so forth. But I'll just do one or two just to sort of set the ball rolling and show a good faith, if you like. Okay, so this one, I'll do assignment 10.1 number 1. The intersection of two intervals is again an interval. It's sort of easy if you think in terms of diagrams. I mean, what are the possibilities? You could have two intervals, they could sort of overlap, or one could be inside one of another. They could overlap the other way around. They could be disjoint, completely separate. And I guess that's it, isn't it? They could have overlap one way, they could overlap another way. One could be completely inside another one, or they could be completely disjoint. But let's just do it in a symbolic fashion. Let's be, well, I'll take the case for open intervals. An analogous argument will work for closed intervals. So let's let A be AB and let C be the interval CD. then by definition A intersection C is the set of all x such that A is less than x is less than B, intersected with the set of all x, this is x in the rails, such that C is less than x is less than D already. And because of the way conjunction works, that's the set of x such that the maximum of A and C is less than x is less than the minimum of B and D. Okay, I think I've used the right letters there. Yeah, that's correct. Okay, which is an interval. It's in fact the interval, open interval, maximum of A and C to the minimum of B and D. And that's an interval. It may be empty. You know, if it's disjoint, it's empty. The empty set is an interval. It's the it's still a set of numbers between 2 points. Okay, so that I think is we'll deal with that one. And let me just say, similarly, for closed intervals and for half open intervals, half open, half closed. Okay, so that's really it. And in the case of unions, it's false for unions. For example, if I take the open interval 0, 1 and I form the union with the open interval 3, 4, then that's not an interval. Okay, and that's that one. Okay, which one shall I do next? Let me do, what shall I do next? Let's do question 5 in 10.1. As a question 5 asks us to verify this alternative definition of least upper bound. Okay, so let's see. Well, first of all, A just says that B is an upper bound. Okay, so let me write that. A says B is an upper bound. So the issue is, does condition B say that it's a least one? Okay, well, let's see what that amounts to. B is a least upper bound if and only if no C less than B is an upper bound. Okay, that's what the word least means, right? There isn't a smaller one. So that's the original concept. There's nothing small that's a lower bound, an upper bound. Okay. Well, that's true if and only if for any C less than B, C is not an upper bound. That's just another way of saying the same thing. If and only if for any C less than B, if it's not an upper bound, that means there is an A in A such that it's not the case that A is less than or equal to C. Okay. You can find an A for which C is not bigger than it, is not an upper bound. If and only if, and I'm really laying this one on with incredible detail here, for any C less than B, there is an A in A such that A, if it's not less than or equal to C, is bigger than C. Now, arguably, I could have deleted one of these lines. I'm really being very pedantic about writing everything down. But in my experience, both when I was a student and from teaching this kind of material for many years, even though these are very simple ideas, it's very confusing at first dealing with the different variations of definitions of greatest lower bounds, least upper bounds. There's something about the way the human brain works that even though we recognise on one level that this has got to be really, really trivial, it causes us problems. So it's just something to do with the way the brain works that makes this a challenge, at least for most of us. Okay, well, that's that one. Let's see what we're going to do next. Well, I think I'll do just one more, and I'll pick one of those limit questions in number 4. Okay, this is from assignment 10.2. And I'll pick this one, show that the limit of n over n plus 1 all squared tends to 1 as n goes to infinity. And these all follow a standard pattern. You start by with a given epsilon greater than 0. And what we need to do is we need to find an integer n such that for any natural number n bigger than or equal to n, it is the case that the absolute value of n over n plus 1 all squared minus 1 is less than epsilon. From some point on in the sequence, the difference between that term and 1 is less than epsilon. Okay, so now let's just pull this apart and see what this really wants us to find. We need to find an integer n such that n greater than or equal to n implies, let me write everything over n plus 1 all squared, and I've got n squared minus n squared minus 2n minus 1, that is less than epsilon, i.e. I need to find an n such that n bigger than or equal to n implies the n squareds disappear. I've got a 2n plus 1 over n plus 1 squared less than epsilon. Okay, so the n squareds disappear. I'm left with minus 2n minus 1 over n plus 1 squared in an absolute value, and taking the absolute value. And so when I do take the absolute value, the minus 2n minus 1 just becomes 2n plus 1, and the n plus 1 squared is positive, of course. So that just reduces to that. Okay, now we can see what to do. What we need to do, and remember we're looking for a big N. So let's pick N so big that n plus 1 squared over 2n plus 1 is bigger than 1 over epsilon. We can always do that. Epsilon's given, it's a small number, we'll assume. I mean, these really, we use a symbol epsilon to sort of emphasize the fact that that in reality epsilon's very small. That's not a logical restriction, it's just our intuitions behind what the proof's doing. Okay, so this is going to be a very large number, but in this term, in this quotient, the numerator is squared and the denominator is linear in n, so eventually the numerator dominates the denominator, so we can make this as big as we want, and we can certainly make it bigger than 1 over epsilon. And when we do that, we find, of course, that if n is bigger or equal to n, then 2n plus 1 over n plus 1 squared is certainly less than or equal to 2 big N plus 1 over big N plus 1 squared, which is less than epsilon, because we picked big N to make that happen. Okay, and that's it. Okay, we just worked backwards. We looked at the goal, and we worked backwards, and indeed we can always find an n with this property, because the numerator grows faster than the denominator without bound. It's squared over linear, and so we get this expression. This is very typical of limit verifications. I wouldn't say they were all like this, but the vast majority of them follow this pattern. You work backwards, and then you just ask yourself where you have to look, how big you have to go, how far you have to go out in order to make something happen. And you very often end up saying, well, pick something so big that it's bigger than 1 over epsilon. And very, very common for limits that involve quotients. Okay, well, I think that's all I'm going to do. As I say, I'm not going to do many on assignment 10. I'll leave it with those. There are plenty more to work with, and I hope you'll enjoy working through those. I remember when I learnt this stuff for the first time as a student, I actually enjoyed it. I thought it was a lot of fun. First of all, it's dealing with infinity in a rigorous way, and that's pretty cool anyway. Right, infinity, dealing with infinity, holding infinity in the palm of your hand, that's really pretty cool, and it's just an intellectual challenge. It's a fun game to play. Okay, so enjoy it, have fun with these things, and I hope you do okay in the final exam. Okay, bye for now. Okay, well, this whole issue of least upper bounds is one of these things that, when you're learning it, is notoriously difficult to get your mind around. Once you've mastered it, it's really pretty straightforward. But there's something about the way the human mind works that makes it difficult for most of us, if not all of us, to master this and to get our minds around it when we first encounter it. I remember when I first encountered this as an undergraduate, I just found it completely baffling. I just really didn't know what was going on. Now I understand it. I realise that there's actually nothing deep here. But I still have to be careful, because you have to use language in a very careful, precise and somewhat intricate way. And it's very easy to sort of go off track. So I don't think this ever gets easy in a sense of being able to just rattle it off without thinking about it. But once you've mastered it, providing you think about it and you keep your clear head and drink enough coffee in advance, then it's usually fairly easy to do these things. So they're not terribly difficult. You just have to be a little bit careful. But as I said, and let me stress it again, if you're meeting this for the first time, you're going to have trouble with this. We all do. Okay, let's see what we've got. This one is definitely true. Okay, and here's the reason. Let's say if A and B are two least upper bounds, then to say that A is the least upper bound means that A is less than or equal to any other upper bound. Okay, that's another way of saying A has to be, A cannot be bigger than B. If A is the least upper bound, then it cannot be bigger than any other upper bound. That's what least means. Least means it's not big. You can't find a smaller one. Well, if B was less than A, B would be a smaller one. So if A is the least upper bound, you cannot find an upper bound B which is less than A, which means that if there's another upper bound B, it's greater than or equal to B. And similarly, because B is the least upper bound, B is going to be less than or equal to A. If B is the least upper bound, A cannot be less than B, because if A was less than B, B would not be the least one. Okay? It's I realise as I speak this that when you meet this for the first time, what I just said is not going to make any sense. It sounds almost as if I'm saying the sky is blue because the sky is blue because the sky is blue. I'm not. There's actually more substance to this, but you have to think very carefully. If these are both least upper bounds, you cannot find an upper bound less than A, so B cannot be less than A. And if B is the least upper bound, you cannot find an upper bound less than B, so A cannot be less than B. So they're equal. Okay? Well, as I said, this makes sense to me. You may well have to work pretty hard to follow that. That's just the way it is. You're not being stupid. You've just got a human mind. And the human mind just does not like this. Okay, this one's also true. This one's actually less difficult, because if A is a lower bound, any lower bound of the set A, then so is any B less than A. If little a is to the left of everything in this set, then so is anything to the left of A. So providing there is a lower bound, then anything to the left of that lower bound is still a lower bound. We're not talking about least upper bounds or greatest lower bounds. We're talking about just plain old lower bounds. And once you've got a lower bound, anything to the left of the lower bound is a lower bound. Okay, this one's false. This is the third one. If a set of rails has a lower bound and an upper bound, it's finite. And I'm going to do that by giving an example. And the most obvious one, I think, is to take the unit interval 0, 1. Then it has a lower bound, namely 0. It has an upper bound, namely 1. In fact, the lower bound is a minimum element, and the upper bound is, the least upper bound, at least the one we mentioned, is 1. So this set actually has a least element and a maximum element. So it's saying it has a lower bound and an upper bound. Anything to the left of 0 is also a lower bound. Anything to the right of 0, anything to the right of 1 is an upper bound. So this thing is bounded below and bounded above, but this is an infinite set. It's got all of the real numbers between 0 and 1. So having lower and upper bounds does not mean that the set is infinite. The set is finite. Indeed, if it's an interval, it could be infinite. Incidentally, this is not the same. There is a phrase, finite interval. That's got a different meaning. That basically means that the interval does not stretch to minus infinity or plus infinity, that it is an interval between 2 points. But this is a special use of the word finite. It doesn't mean it's a finite set. It just means it's got finite lower and upper bounds. It's got endpoints, if you like. So having said that, I'm going to get rid of that because I don't want to confuse the issue. As a set, this is an infinite set. Okay. And finally, let's look at the last one. This is also false. Let's just look at what the set is. Let's write it out. The set starts down here, a long way down here actually. Then we've got -4, -3, -2, -1, or -4, -3, -2, and -1 if you're pedantic on those issues. And then this one actually has a maximum element. That's also a least upper bound. Okay, if there is a maximum element, it has to be the least upper bound. So there is a least upper bound. It's the maximum element, and it's -1. It's not 0. 0 is well to the right of this thing. So the least upper bound is -1, and 0 is not the least upper bound. Okay, well, how did you do on that one? You know, if on reading it through now you throw your fist to your forehead and say, "Oh golly, how could I be so stupid?" Well, you weren't being stupid; you were being human. This is just tricky when you first meet it. You know, and if it looks simple now, then good. And if it still looks complicated, then you're going to have to work for it a bit more. But you're not at all unique. If having seen this, you're still confused. We all are when we first meet this. Okay. Well, let's go to number 2 now. Well, as with the previous question, the approach is to move slowly and painstakingly and be careful about what things say. Just to sort of parse it apart so that we know exactly what it says. So let's do that one step at a time. B less than or equal to A for all A in A. That says B is a lower bound of the set A. If C is less, so that says C is a lower bound of the set A. So B is given as a lower bound of the set A, and if C is another lower bound of the set A, then B is greater than or equal to C. In other words, B is the biggest one. B is bigger than any other one, or at least it's greater than or equal to any other one. So B is a lower bound, and moreover, B is at least as big as any other lower bound. So the answer is yes. That one does say it's the greatest lower bound. What about the second one? That says B less than, so this says, again, it's the same thing. B is a lower bound. And this says, if C is any other lower bound, then B is bigger than C. There's a problem here. Because B itself satisfies that. That would mean B is bigger than B. This statement would imply B is bigger than B. Which is impossible, of course, right? No number can be strictly bigger than itself. So this thing is just, it's not only is this, does it not say that, so this is in fact a false statement. It doesn't say anything sensible. I mean, it implies that B is bigger than itself for some B. So certainly this does not say it's a greatest lower bound. It doesn't say anything meaningful at all. Let me say a little bit more. What's going on in here and in here is we've got implicit quantification over C. Implicit quantification over C. This is really saying for all C, if C less than or equal to, this is a quantification in this situation. It's implicit quantification over C. And whenever you've got universal quantification, implicit universal quantification, whenever you've got universal quantification, you can hit every possible target. So whenever there's something like this going on with the universal quantifier, among the possible C's is the B itself. I mean, the B isn't really been quantified within this. B is just some number that we're trying to classify. So the B is just a number. It's a fixed number, if you like. The A's are being quantified over for all A's, and the C here is being quantified over. Now, we haven't used the traditional language of for alls here, but it is a universal quantifier, and there, because it just says any C less than or equal to A. And so the C can be anything, and in particular, the C can be the original B. In the first case, it was no problem, because B is greater than or equal to B. This case, it's a big problem. It makes it false, in fact, because a number can't be bigger than itself. Okay. Let's look at the next one. Well, let's see. Why don't we take A to be the closed unit interval 0, 1. Okay. The greatest lower bound of A is 0, the minimum element, right? Why did I do that? Well, because 0 is not strictly less than everything in A. In the case of this set, you would have to have 0 strictly less than 0, which is impossible. Okay? So it cannot be the case. I mean, this can't, it just can't be, I mean, it's just not true. This thing's not true, because to be a greatest lower bound, you would have to, this tells you you'd have to be strictly less than everything in the set. And in the case of a closed set, it doesn't have to be the unit interval 0, 1. Any set with a minimal element will do this. All we need is a minimum element. And if the set has a minimum element, then the greatest lower bound cannot be strictly less than everything in the set, because if there's a minimum element, it is the greatest lower bound. So that rules out this one. Okay. What about this one? Well, essentially the same reasoning. You can't classify a greatest lower bound by including the requirement that it's strictly less than everything in the set. If there's a minimum element, it is the greatest lower bound, and it's not strictly less than it, so that doesn't capture it. Okay. And let's look at this one. This says B is a lower bound of the set A. And what this one says, by the way, there is a reason why it's expressed in terms of these epsilons. A lot of the theory of the real numbers that was developed in the late 19th, very early 20th century, it turned out that doing this stuff with epsilons was very powerful. But if you look at what it says, it's going to turn out to actually say the same as the one right at the top. That says, if you combine that with that, this says, forget that bit for a minute, this says any number slightly bigger than B, bigger than A. Yep. Any number bigger than B. Good grief. Okay. You're going to add an epsilon to B. So you're going to go slightly to the right of B. And what it says is if you go slightly to the right of B, you can find an A to the left of that. So let me just draw a little picture. Okay. We've got this set A here. Okay, so A is somewhere in here. Okay. And I've got a B that's to the left of everything in A, or at least not to the right of everything in A. It's less than or equal to everything in A. And then what I'm saying is, if I go slightly to the right to a number b plus epsilon, which we'll put in here, then already I've gone to the right of some element a of the set here. So b is certainly to the left of everything in A, but if I go slightly to the right by adding an epsilon onto b, then I will be able to find an element in the set to the left of it. So this can't be a lower bound. So b is a lower bound, but if I pick anything to the right of b, and this is saying, I really shouldn't have underlined that maybe, this is saying everything to the right, anything to the right of b, anything to the right of b already dominates something in the set A. So anything to the right of A will fail to be a lower bound. So B is the greatest lower bound. Okay, so you just have to parse apart that combined with that. For any epsilon greater than 0, B plus epsilon has a property. So these two together is basically saying for any number bigger than b. That's really what that's saying. For any number bigger than b, there is an A such that, in other words, it's saying this thing. It's exactly the same as this, expressed differently. Okay. Well, you probably have to think a little bit about this. As I've mentioned a couple of times already now, the human mind just seems to find it's very difficult when it first meets it. And as I've demonstrated by a couple of misspoken remarks I've made, even when you're familiar with the material, it's tricky to say these things precisely unless you really sort of rehearsed it out. And that's just the way the mind works. Okay, let's move ahead to the next question. Well, question 3 deals with the delightfully named sandwich theorem. Incidentally, this is not to be confused with the ham sandwich theorem, which is a very different theorem altogether. I'm not kidding you, there is a thing called the ham sandwich theorem. You can look it up on the web and find out what it is. This is something quite different. And what it says is that if you have two sequences, one always less than another one, and you've got another sequence in between them, then when one sequence and another sequence, when they send to the same limit, the thing in between them gets forced to the same limit. It's called a sandwich theorem because the A sequence and the C sequence are slices of bread, and the B sequence is in between the slices of bread. And what this says is if you make a sandwich with two slices of bread and some meat in between them, or some filling, and you squeeze the two slices of bread together, then the filling will get squeezed between them. Actually, of course, what happens is that mayonnaise runs out all over your lap, or ketchup and things, so it's kind of messy in real life. But in principle, what we're saying is if we squeeze the two slices of bread together, then the filling must get squeezed in between them to the same thing. Okay, now in question 4, we're going to have to prove the sandwich theorem. Here we're just going to apply it. And it's a very useful theorem. It's a simple theorem. It's intuitively obvious. And we're going to give a very simple example here. And here's the theorem we're going to prove using the sandwich theorem. That the limit as n goes to infinity of sine squared of n divided by 3 to the n equals 0. Okay, and the proof is rather straightforward. What we do is we observe that for any n, 0 is less than or equal to this term because we've got the square, which is always positive, of course, and we've got the positive number on the bottom. So this is always, it's non-negative. And it's clearly less than or equal to 1 over 3 to the n because the sine, the maximum value of the sine of any number is 1. So this is less than or equal to 1 over n. And so we've got a sandwich. Incidentally, there's nothing to stop the sequence an being a constant sequence. So in this case, a0 equals a1 equals a2. I mean, all of the a's are 0. Okay, actually we start at 1 usually. So a1, a2, a3, etc. 0. So we've got the ANs are the zeros, the CNs, the top slice of the sandwich, if you like, this top piece of bread, is 1 over 3 to the n, and this is sandwiched in between. Well, clearly, well, we know that this sequence is a constant sequence of 0, so the AN sequence tends to 0. So the CN sequence tends to 0 as well. Okay, because it's quite clear that the denominator it grows without bound, and so this gets bigger and bigger and bigger, and it tends to infinity, if you like, and so the quotient tends to 0. So these terms are squeezed between 0, the constant sequence, and 1 over 3 to the n, a sequence which tends to 0. So by the sandwich theorem, this tends to the limit 0 as required. That's all there is to it. It's logically correct. Everything's there. It's clear. There's an opening. Really, there's not much of an opening to do, in a sense. Arguably one should have said, one could have said at the beginning, we're going to use the sandwich theorem, but that was actually given to us in the question. And so as long as we cite it when we use it, that's fine. Okay, so the opening, in a sense, was provided to us by the context for this one. There was certainly a conclusion. There's the conclusion, clearly stated. The reason, there's a couple of reasons. This is part of the reasoning, but this is the key one that we're going to cite the sandwich theorem. That's the main reason. And overall, absolutely correct. 24. It's not. The complexity, the depth is actually in this statement here, in the sandwich theorem. The sandwich theorem does all the work for us. This is really just a corollary of the sandwich theorem. But proofs don't have to be long. So long as everything's there, so long as it's clear, it's a proof. Now, I didn't prove this. I said it was clear, because in the context of applying the sandwich theorem, you're entitled to say that this is clear. Okay, one could give an epsilon proof of this. Given an epsilon, there's an n, and you could use a definition of limits, but it's unnecessary. You don't normally prove that 7 plus 5 is 12 when you're doing some arithmetic. You just assume that. It could be proved. You can prove it from first principles. You can do various things if you want to, but in the context of applying the sandwich theorem, you're entitled to assume something like this. It is important to say if it's clear. If you said because that we can apply the sandwich theorem, then it's a little more mysterious. But saying something is clear is a valid reason. So that's an okay method of saying that something's a reason. Say it's clear. If it's clear, simply saying it's clear is adequate to give a reason. You don't need to have length and depth in these proofs, so long. Well, you need to have the depth, but it doesn't need to be unnecessarily long. This is a good proof. 24 marks. Let's go on now and prove the sandwich theorem itself. So here we are. Let's again look at what it says. It says you've got 3 sequences, and that from some point onwards, the A sequence is less than everything in the B sequence. The corresponding member of the B sequence is less than the corresponding member of the C sequence. This happens on a term-by-term basis. From some point onwards, the nth term of this is less than the nth term of that, is less than the nth term of that. So from some point onwards, you've got a sandwich where the B is the filling in between the 2 slices of bread. Okay, and then the outer sequences, the lower sequence and the upper sequence, tend to the same limit. They converge and tend to the same limit. Then the conclusion is that the sequence that's in between is convergent and moreover converges to that self-same limit. Now, intuitively, it's obvious, and the obviousness is actually captured by the name of the theorem. That's why people call it the sandwich theorem, also known as the squeeze theorem, which I think was actually mentioned in the original statement of the problem. Obviously, when I'm doing these abbreviated forms for the demonstrations, I cut things down because I want to get everything on a single slide. Okay, and we're going to prove it by going to the definition of convergence, which is one of these epsilon arguments. And oh dear, already I'm very unhappy, because this guy needs to begin with a statement, let epsilon greater than 0 be given. Without that, we do not have a proof. We simply don't have a proof. This epsilon appears here somewhere, suddenly comes in, but what is the epsilon? It's not in the statement, it's something we introduce in the proof. And what makes this a proof is the fact that the argument we carry out here can be carried out whatever epsilon we're given in the beginning. It's the arbitrariness of the epsilon which makes this a proof. This is a big deal, and it's going to affect the grade I give. Okay. Come back to that. Let's just follow the steps. Since the limit of that is L, we can find an integer such that from some point onwards an minus L is within a distance. So an is within a distance epsilon of L. Ditto, since the Cn sequence tends to L, we can find an integer n2 such that from that point onwards the Cn numbers are within a distance epsilon of L. And now I can take n to be the maximum of the n0, the point from which we get a sandwich. We get a sandwich from n0 onwards. And n1, the point from which we get this happening. And n2, the point from which we get that happening. So beyond the point m, all of these three conditions are going to be satisfied. So for any n beyond there, I'm going to have this, which is the first condition, except I've got rid of the absolute value terms and I've written it with a minus and a plus. Okay. Ditto here. I've got it between minus and plus epsilon for the Cn's. So that implies, and what I'm going to do now is I'm going to combine these together with the fact that we've got a sandwich. This is good. I'm going to give credit for this because this reminds us that we've got an extra piece of information. So what I'm doing is combining it. I'm saying I've got a minus epsilon is less than this guy. This guy is less than this guy because an is less than bn. So an minus L is less than bn minus L. So that gives me that one. This inequality is also going to come from there because bn is less than or equal to Cn. And so I can subtract L from both sides of there. And then finally this one is going to give me Cn minus L is less than epsilon. So what I'm doing is for the first inequality here, I'm taking this and that feeds into that inequality. Then this here is going to feed into the second inequality. This here is going to feed into the third inequality, and this here is going to feed into the last inequality. So that inequality here gives me the first one, this gives me the second, that gives me the third, and that one gives me the fourth. So it's all concatenated and sort of pressed in, but the reasons are all given. This is there, and that's there. Those are the three reasons. They all combine to give me that. Then I can say that minus epsilon is less than bn minus L is in the middle, and plus epsilon is on the outside. And now I can put absolute values back in and say that means bn minus L in absolute value is less than epsilon. So by the definition of a limit, this proves that this thing is convergent, and moreover that it converges to L. Well, it does that providing this argument is carried out for an arbitrary epsilon. So now let's give some numerical grades. Logical correctness, I'm going to say 4 for that. The logic was absolutely brilliantly laid down. I mean, this is very succinct, nicely done, very impressive. Clarity, absolutely clear. Absolutely clear. Opening, there wasn't an opening. The opening has to be let epsilon greater than 0 be given. That's how the story slides. This is the equivalent of once upon a time in a fairy story. Yeah, I mean, you have to start somehow. You have to open the story. This is the opening for this kind of argument. It's equivalent to saying we're going to use induction for an induction proof. An epsilon proof has to begin by stating that the epsilon is epsilon, that the epsilon is an arbitrary positive number. This is crucial. First of all, it tells you it's positive. You've got to make that explicit, and you've got to say that it's arbitrary. So there's no opening here. State the conclusion. Oh yeah, the conclusion is beautifully stated. 4 marks for the conclusion. What about reasons? I'm going to give 4 marks for reasons. In particular, I love this one here. This is really nice that this has been written here. Let's put a little smiley stick here. Say we really appreciate the fact that this has been done here. That's nice to put that in here, rather than sort of expect people to sort of pull it back out of the hypothesis. Yeah. In fact, without that, I think I would have deducted marks for reasons. This is there, that's there, and that's there. arguably one could have put a bit more detail in the way I explained it when I went through it. But in terms of expressing what needs to be expressed, this does it very well. Overall valuation, in all conscience as a mathematician, I can't go any higher than 0 for overall. Without that, the whole thing falls apart. This is not a triviality. This is what makes the thing work. It hinges on the fact that it works for epsilon greater than 0 be given. Okay, and you can't simply say, well, we all know that. Well, we don't know that. This is a proof. And this is part of a proof. It's not just part of a proof. It's an absolutely critical part of a proof. So can't go beyond that. Not only is it an arbitrary, not only is it an incredibly important part of the proof, but this approach, this way of dealing with things, came after the result of hundreds of years of research in mathematics. It was only late in the 19th century when people figured out how to do this kind of thing and make sense of limits. So this is not just important within this proof. This was a major advance in mathematics in the late 19th century. Incredibly powerful. So I've got 4 lots of 4. I've got 16 for this one. And I don't think that's unduly harsh. Even though I feel sorry for the person, because this is very clever, manipulating inequalities and getting them right, and that's tricky, and people have difficulty with that. But I've given credit for that. Okay, that was in the correctness and the clarity, and given the reasons. Where this falls down is it's not a proof. It is simply not a proof, and without that, there's no way it's going to be a proof. So that's a big deal. And the fact that we can make this into a routine little opener is by the by. Yes, it may look routine when we write it down, but it's a huge part of the logic. Okay, one more question to go on this problem sheet. Question 5, we have to prove this theorem, and that means proving it from the definition of a limit. Okay, so we're proving that this particular sequence, n plus 1 over 2n plus 1, tends to the limit 1/2. Okay, I will tell you that this is actually my proof, and the reason I'm doing that rather than taking a proof that I've had from a student or composite from students is that these proofs tend to be sort of longish because you're manipulating inequalities and fractions and things, and they wouldn't fit neatly onto a single slide. So in order to fit it onto a slide, I actually gave my own proof, and so this is a very succinct proof. Okay, and I'll tell you up front that I'm going to give myself full marks. I'm entitled to do that, aren't I? But in fact, this is a correct proof. So let's take away all of the suspense by saying I'm going to give myself full marks on this one. Instructors can do that, right? But in fact, this is fine, but this is not the kind of proof I would expect to see from a student. And certainly not a beginning student. I'd expect to see quite a bit more. But let's just see what's going on. Okay, so we begin by saying let epsilon greater than 0 be given. So I start off well. Okay, I give the opener. So that's the opener nicely taken care of. Choose n large enough so that n greater than or equal to 2 epsilon. Well, if epsilon is small, and the intuition, of course, is that what makes the proof work is that the epsilon can be arbitrarily small, which means 1 over 2 epsilon will be arbitrarily large. But of course, I can always pick an n bigger than that. That actually is a mathematical principle known as the Archimedean principle, but we won't go into that now. Okay, intuitively, it's clear that you can always pick an integer bigger than any real number. Okay, so why am I picking that? Well, because I'm looking ahead to what I want at the end. And after doing this kind of thing for years, I can look ahead and see what I've got. In practice, what you've probably got to do is just work through without saying what the n is, and then see what you have to do at the end. So I could write this down in the beginning because I can see ahead, but typically you might have to go through the logic first before you can decide on this step. So this sentence, for most people, comes at the end of the manipulation. Okay. Then for n greater than or equal to n, I'll come back to that point in a minute. For n greater than or equal to n, we've got the following. Okay. We need to show that this is within epsilon. Okay, so we're going to show that this guy is less than epsilon. Well, let's just work it out. Write it as a single fraction. Common denominator is 2 into 2n plus 1. So then I've got 2n plus 1 minus a 2n plus 1. Do the algebra, that just becomes 1 over 2n plus 1. Everything's positive now, so I don't need the absolute value symbol. And I can get rid of the half now by saying it's less than that over that. Just simplifying things. And I can say that that's less than 1 over 2n, because the denominator is bigger here, so it makes it smaller. And now you should be able to see why I picked n that way, because what I wanted to say was that 1 over 2n is less than epsilon, and I can do that by picking that n, because if the little n is bigger than the big N, then this one is less than that one, and that one is less than epsilon. So this last step is where that came from. Why did I do that? Because having manipulated this through, at the end I realised that in order to get this guy less than epsilon, because the whole point is to show that this is less than epsilon. That's what we've got to show. Show that that's less than epsilon. How do we do that? We do that by picking n's big enough so that 1 over 2n is less than epsilon, because this is actually bounded by 1 over 2n. So it was doing this manipulation that gives me the choice of the big N. And as I say, I've been doing this for so long that I can see ahead to see what's going on. But even if you can't, you can just start with what you're trying to prove. You're trying to prove that this is less than epsilon, see what it is you have to prove, and make simplifications. Get rid of the 2. You don't need it, because that makes it bigger. Get rid of the plus 1. You don't need it. And then you get to something simple, and you can pick your n that way. Okay, and then by definition of limits. So let's just see why I gave this. The logical correctness, well, it has the start in there, the opener, okay, so let's take them one by one. The logical correctness, these are just manipulations. This is just inequalities. Okay, it's pretty slick. I did it in a few steps. You might make a few more steps, but it's logically correct. It's absolutely clear. There is an opening. There is a strong conclusion by the definition of a limit. Reasons, yeah, well, there's a reason there, and there's sort of reasons embedded in here in what I'm doing. I didn't write reasons down here. I didn't write explanations, because this is just straightforward manipulation. You know, you could say what I've just articulated. You could give explanations and reasons, but you don't need to. This is transparently clear. It's just basic algebraic manipulation of inequalities. So reasons are okay. I mean, this is an important reason, I think. It's definitely worth saying that. And if you go back to previous question 4, I didn't make a big deal about it, but if you look at question 4, it also ended by citing the fact that we're using the definition of a limit. And then overall, yeah, you give 4 for this, because there's absolutely nothing missing. It's a clear, concise, rigorous, logical, complete proof. Okay, these take a while to get used to, though, because you are working backwards. You have to sort of play with the thing until you get it into a form where you know how to pick the n. But it comes down to picking an n so big that everything happens that you want to happen. Okay, well, that's the end of problem set 8, which is the last problem set of this course. How about that?
The idea behind TestFlight is to give you a brief experience of 2 of the main things that professional mathematicians do: prove results and evaluate proofs created by others.
Well, we're looking at the first sample problem set solution, and in this one, the student's answer is wrong because the statement's false. The problem is that this answer clearly assumes that 0 is a natural number, and by definition, the natural numbers are 1, 2, 3 onwards. That's historically correct as well. So this is actually a false assumption. So I'm not going to give full marks for logical correctness. On the other hand, you will find some mathematicians who do include 0 in the natural numbers, so I'm not going to be too strong on the penalisation here. But we're in a community, and mathematics takes place in a community. When we're writing proofs, we do so using the norms and practices of that community. We design our proofs to match the audience that they're intended for. So writing a proof has to take account of which community you're in and who you're writing for. I mean, when I write proofs for other mathematicians, I do them very differently from the kind of proofs that I write for students. When I write proofs for graduate students, they're different. We have to adjust the kind of arguments we're giving depending on the community we're in and the people we're writing for. So there's a community aspect to writing proofs. It's not a matter of right or wrong always, it's a matter of who we're trying to communicate to. So what I'm going to do is I'm going to put 2 for logical correctness. I'm going to give some credit for saying, well, if you do assume 0 is a natural number, then this is a solution. But in fact, we're in a community and we've got some accepted practices now. We've established a convention that 0 is not a natural number. And in fact, that is the standard convention within mathematics. So I think I've been pretty generous here in giving 2, but I think that's fair. It's clear. It's absolutely clear. I mean, there really isn't an opening in this case. It's just, you're just doing it. It's so short and simple. So I'll have to give 4 for that. Conclusion is stated. Reasons are given. I mean, insofar as there are reasons to give. Overall, I think I'm going to have to give 0. Because this is just from the point of view of what we're doing in this class and the audience we're trying to communicate to when we write proofs, this is just not good. It really doesn't answer the question within the framework that we're working. Okay, so that means I'm going to give a total of 18. I think that's a pretty good result. In fact, I think that's generous, given that the students made what is a sort of fundamental mistake within the context of this course. Let's move on to question 2. Well, for number 2, the student gives the right answer, but the proof is completely wrong. There's a fundamental misunderstanding here. The student has assumed that this is an existential quantifier, that there are 5 consecutive integers whose sum is divisible by 5. In fact, this is a universal quantifier. What it means is that take any 5 consecutive integers, then their sum is divisible by 5. So this is just not a proof. Student really doesn't understand universal quantification. So we're going to have to give 0 for everything here. This is just a basic misunderstanding. There's nothing we can give any credit for. We have to give a 0. When you really misunderstand something fundamental, like what it means to have a universal quantifier as opposed to an existential quantifier, we can't possibly give partial credit or anything like that. This is just plain wrong. The student has no understanding of what we're trying to do. Pity, but there we are. Okay, number 3 now. Well, first of all, the student doesn't actually say whether it's true or false, not strictly speaking. On the other hand, the student does start out and say, I'm going to prove it, so it's obvious that this person believes it's true, which it is. So I'm not going to deduct any marks for not saying whether it's true or false. That's just a slip, and it's got nothing to do with sort of mathematical thinking ability. They just missed out saying it. Okay, so there's something missing here, but we're not going to worry about that. Okay, going to prove it by induction. Okay, let's see. For n equals 1, true. Okay. Suppose this is the induction hypothesis. Then, following this through, this is all okay. This is all okay. Beginning to look a bit suspicious, this one, because this argument doesn't actually use the induction hypothesis, which means it's not an induction. It's not an induction proof, right? Let's see. But 1 of n plus 1 is. This is good. This is good. We'll come back to talk about that in a minute. That's good. So that's even. Well, it certainly this appears to prove the result, but it's not by induction because there was no use of the induction hypothesis. That was never used. And there's another problem here. This actually says for any integer. That includes the negative integers. Induction only works for the positive integers. You can actually extend induction to work for the positive and negative integers. We haven't done it in this course, but you can do that. But if you do that, then you're going to have to sort of take account for the fact that it's a little bit different for the positive and the negative integers. So as we've set things up, induction, and this is pretty standard, induction is usually taken to just mean for the positive integers, for the natural numbers. And the fact that you can use it for positive and negative is an extension of it. That's not what we're talking about. So there's a problem here. Induction, as we've got it, standard induction, standard mathematical induction, doesn't prove things for all integers. So this is already wrong. It hasn't proved it. It's only proved it for the positive integers. And moreover, it hasn't done it by using induction. So there are certainly problems with this. This is actually going to be tricky to grade this one, because there is, as I said, I'll come back to this one, there's something good going on here. Okay. Logical correctness. I'm going to give 1 because there is a logical flow to this. It's not an induction proof, except in some strictly formal, vacuous sense. But I'll give 1. Okay. Clarity. I'm going to give 2. In of itself, it's clear. But as a demonstration of the truth of this guy, it's not clear. This doesn't add clarity to knowing why this thing is true. Opening. Again, I'm going to give 2 because it sort of begins fine. It's just that it's not relevant. It's not totally irrelevant. This is not completely off the wall, but it's not really addressing the issue. So I'm going to give 2 for that one. State the conclusion. That was well done. I'll be full on that one. The conclusion was stated. Reasons. Boy, this is not an easy one. I'm going to give 2 for that. I'm on the fence here. Reasons were given, but they just weren't always the right reasons. On the other hand, this guy really is this is remarkable, because if you go back to here, the real key to proving this is to take that guy and factor it as n times n plus 1 plus 1, and then observe that one of these is even and the other one is odd, hence their product is even, so when you add 1 it's odd. So the proof of the result really just amounts to factoring this as n times n plus 1 plus 1, and observing that that product is even, and then when you add 1 it's odd. That is the proof. Now the person has spotted that here. This is the key idea. And that was why I was generous here. On all of these I erred on the side of generosity, and I did it because the student had the key idea. This was it. This was the key to the result. And I wanted to give credit for that. But everything else was just off the wall, almost off the wall. Okay. Overall, I'm going to have to give 0 because this simply doesn't get at the issue. The student had sort of seen it, but wasn't aware that he or she had seen it. So I can't give more than that. Okay, so I've got a total of what? Let's say 11. Okay, just somewhat less than half marks. Okay. But I think that's about right. I mean, I couldn't even give 50% for this one. I think that's as good as I could give, because I'm really just giving credit for this one particular observation. Incidentally, with these exam sample solutions, what I've done is I've compiled them from many solutions I've seen over the years giving this course, and I've sort of simplified them so they fit neatly onto a single slide, and that means we can use them as examples to look at. But if this had been an actual student paper, if these questions were all answered by the same students, then at this point I'd actually get rather suspicious, because questions 1 and 2 were answered very badly. I mean, really badly. And then suddenly a student comes up with a key idea. At this point I'd begin to suspect that the student had actually copied something from another student, either copied it wrongly or copied something that had been done wrongly by the other student, because making this observation just seems so strange given what we've seen in questions 1 and 2. Now, as I said, this is not an exam solution from a single student. It's a compilation to illustrate points of grading and evaluation. But in reality, if I was grading a paper, I'd be suspicious. I mean, I would still give the grades the same way. You grade what's in front of you, but your suspicions are often aroused. And sometimes, of course, with a real course where there's actual credit being given for a certification and for a degree, say, college credit, then you often end up calling the student into the office and going through it and double checking if the student really knows what they're doing. Okay, we've given 11 for that. I think that's the student shouldn't have any grounds to complain. They've actually got as good a grade as they're likely to get for this one. Okay, number 4. We prove it by induction. What's going on? It looks as though this student is trying to prove some sort of a converse, namely that every number of one of these forms is odd, namely that 4n plus 1 is odd and 4n plus 3 is odd. Well, that's trivial, right? 4n is even, so you add 1, it's odd. You add 3, it's odd. And yet that's what the student seems to be proving, in which case they've missed the fact that it's obvious. So what am I going to give for this? All I can give is 0 for this. It's just off the wall. There's nothing I can really give credit for. The student's trying to do something that's not asked for. What you're trying to show is that if you take a number which is odd, then it has to be of one of these two forms. You're not showing that any number of one of these forms is odd. So the student's not even answering the question. They're answering the complete converse of the question, which is in fact trivial. So no way I can give any credit for that one. Okay. Whether or not this is. Let's just check and see if this is a valid argument. If it was induction, let's just see. That's okay. If it's true for n, then well, okay. But since it's got nothing to do with what's been asked for, I'm not going to even look for giving partial credit for that. I mean, in a different context, and I may well have looked for partial credit, if this had something to do with what was been asked for, but it's not. This is just completely irrelevant to what's been asked for. And as I've indicated when we set up the rubric, you can give partial credit so long as it's relevant to the question. But a valid argument that doesn't address the question at all just can't receive partial credit. And that's what's going on here. Well, number 5, I have no idea what the student's trying to do here. It looks as though he or she has used that technique you often develop at high school of sort of trying to match to a template, looked at the question, looked through his or her notes to see something where this kind of thing is dealt with, and then throwing down expressions that seemed relevant at that time. In other words, using the template method, try to match the question to a template and then apply the template. But as I've said many times in this course, in the lectures already, templates tend not to work for this kind of material. You've got to think of the actual question. So forget trying to match a template and apply a method that you've seen and that you've got in your notes. Think about the actual question. And this has nothing to do with the actual question here. These might seem like relevant statements, but they're not. This simply doesn't really address that at all. There's nothing I can give here except zeros throughout. Again, as in the previous question, you can't look for partial credit when what's written bears no real relationship to what's required. If there's some relevance, then you can give partial credit, but not in a situation like this. Clutching at straws, hoping that by scattering some sentences down that were copied from notes or somebody else's notes, you're going to get some grade. No, isn't going to work. Well, this is very much like the last one. It's a clutching at straws argument, putting things down that look as though they might be relevant on the hope that that they'll get some partial credit. But it really just doesn't address the, wait a minute, there's something I kind of like about this. Suppose because of let's look at this first bit. This is the opening part. No, there's a period missing. I'm not going to deduct any marks from missing punctuation, but let's put a period in. This actually shows some mathematical sophistication. There's something clever going on here. This makes sense as an attempt to start to prove something. Take a pair of twin primes and then show, with p greater than 5, and show that you can't extend them. So in terms of establishing a method whereby you're going to try and prove something, this actually is kind of impressive. Surprisingly so, given the other answers we've seen from the student. And remember, this is actually a compilation, it's not a single paper. But if it was from a single student's paper, then this would make me, it'd make me, I'd want to talk to the student, because a student who starts off by saying this actually indicates some mathematical ability. So I'd want to determine if it was that student's own work, because if it was, I would work with him or her in order to try and improve their overall performance, because this actually shows some ingenuity. In fact, what I'm going to do is I'm going to give marks. I'm going to give full marks for the opening, because this is impressive. I will give credit for a very good opening as a way of starting a proof. Now, it turns out that the student's done nothing with this. It makes no sense. And so it's not logically correct. It's not clear at all what's going on. I have no idea what's going on here. Okay, I mean, I can't give credit for stating the conclusion because it's not addressing the question. I can't give credit for that either. And I'm certainly not going to give credit for that. I'm just going to acknowledge the fact that this indicates some good mathematical sense, some ingenuity, and I want to give credit for that. But it's got nothing to do with what's being done. Okay, so, you know, it sounds as though I'm contradicting what I've said earlier. I'm actually not. I'm trying to make a fine distinction, because this is not totally irrelevant to proving this kind of thing. It's the kind of thing you might want to do. It makes sense to start that, but then it's not delivered. It doesn't convert into anything sensible. So it's not an irrelevant thing to say, but it certainly doesn't establish a result. So I'm just giving the credit as an opening, because it's possible that would have been an opening of a correct answer. Well, the student's obviously using induction to prove this result. Doesn't tell us that fact, so we're going to be deducting marks for a whole variety of things here. Let's just see if it is a correct induction. Begins with n equals 1. That's okay. Assume it holds for n. Adding. Now this is nice, explaining what's going on. So I'm certainly going to be giving partial credit for this one. And that's 2n plus 1. That's 2n plus 1. Brings them together. Simplifies that way. That's the advantage. Okay, so there's some really nice stuff here. On the other hand, there are some glaring holes in what's supposed to be a proof. Okay, logically correct. It's absolutely logically correct. No problems there. It was clear. There were it states this part. It tells what's going on here. It observes that that's the identity for n plus 1. Completes the proof. So it was absolutely clear. No statement of the fact that this was a method of induction, and that's a big deal. So the opening simply isn't there. Part of the opening, and large part of the opening, is to say we're going to prove this by mathematical induction, and that's completely missing. Okay, this assumption here is part of the actual mechanics of induction. Okay, stating conclusion. You know, I'm going to go for 0 there. I mean, maybe I've been a little bit harsh, but there's no. First of all, there was no statement of induction at the beginning, and the conclusion, in any case, should have said by the principle of mathematical induction or by induction, the result follows. Simply going straight from the identity at n plus 1, which is proved on the assumption of the identity at n, that it completes the proof. Well, it doesn't. That on of itself doesn't complete the proof. That completes the proof that if it's true for n, then it's true for n plus 1. It doesn't complete the proof of this guy at all. That requires a principle of mathematical induction added to what you've just done. So this is just not a good conclusion. There is no conclusion. I can't give credit for the conclusion to the overall proof. Okay. I mean, I was, on the other hand, I've been generous elsewhere, so I'm okay with that one. Reasons, I'm certainly going to give 2 marks, because locally reasons were given. The big thing that was missing was induction, and that's a big reason that's involved in the argument. But within here, reasons were nicely given, so I'm going to give 2 for that. And that means overall I'm going to give 2. So I'm going to give a total of 12 for this one. And I think that's pretty good, actually. Half marks for something like this. That's pretty good. The trouble is, though, the things that are missing are big things. and so you're going to lose a lot of marks for that. Induction proofs draw upon a very important principle, and you really have to state that you're using induction, and you have to mention when you're using it. Okay. Incidentally, there was no mention of the of where the induction proof used the induction hypothesis, but I agree that's okay because you're beginning with the identity and you're seeing what you're doing with it. So even though there was no statement in here that says by the induction hypothesis, that sort of doesn't make sense in this particular argument. Alrighty, let's go on and look at number 8 now. Well, the answer to number 8 in many ways is quite similar to the answer to number 7. There's some good technical manipulations going on, but it doesn't have the right structure of a proof. First of all, what's key here is the initial opening assumption that epsilon greater than 0 be given. That's just not there. And I'm really going to ding that. In fact, I'll put this down now. The opening is missing. Okay. What about logical correctness? But this is good. This is good. We can find an n such that by the assumption, the given assumption, then whenever that's scarce, that all follows. That works fine, which shows that I'd be inclined to here want a student to put something like by the definition of limits. At this level, when you're talking about introductory material, introduction to real analysis, introduction to the concepts of limits and so forth, I think this really would need to be there. I mean, for a professional mathematician you wouldn't, because you can assume that they know what's going on. Okay, so in any case, for logical correctness, I'm going to give a 4, because logically it's correct. Clarity, I'm going to have to give 2, I think. Quite frankly, I don't think this is clear. It needs a little bit more explanation. At this level, one would expect more explanation. A few reasons, a few hints. Okay, a professional mathematician can look at this and fill in the missing blanks and know what's going on. But my guess is most of you, the students in this class, would have to struggle to follow the student at this stage and to see what they're doing. I mean, especially given the fact that there's nothing by way of an opener to the thing, and there's no reasons given. Stating the conclusion. I'm going to be general. I mean, the conclusion is stated. I'll worry about that when I talk about giving marks for reasons, I think. But absolutely, the conclusion is stated. Arguably, this is part of the conclusion. And so when I look at reasons, then I'm just going to give 2, because there's no reasons given anywhere in here, and in particular it's not explained why it shows it. Which shows that? Well, at this level, a student is reasonably entitled to say, how come it shows that? Why does it show that? What's going on? There's something missing. So some reason would begin. But at the very least, you need to alert people that this is simply the definition of a limit that's been applied here. So overall, I'm going to go 3. I could have gone 2, but I'm going 3 because this is actually correct. This is very slick. It's written very briefly and simply. There's explanations missing that could help a beginner, but this is actually pretty slick. And again, if this was an actual paper from a student, I'd really suspect that student had help or had copied the material. In doing so, they'd missed bits out and they hadn't fully understood it. So this is a situation where in a physical class I'd want to sort of chat with the student and try and find out what he or she knew. Because if they were producing this themselves and making lots of silly mistakes, then I would want to work with them quite intensively, actually, to try and bring out their mathematical ability. So what have I got now? I've got a total of 15 for this one. Okay. Let's go and look at number 9. Well, the first thing I want to do here is get a picture of the student's answer. So let's see. A1 is going to be 1 over 2 to 1. A2 is going to be 1/3 to 1/2. A3 is going to be 1/4 to a third, etc. So let me get a picture here. Let me draw the unit interval from 0 to 1. A1 is a half to 1, so this guy here is A1, okay. A2 is a third to a half, so let's put a third in, and there's A2. A3 is a quarter to a third, so let's put a quarter in. Well, the scale is off here, but never mind, we're just going conceptually. A3. Already now we see that the student's example doesn't work because it doesn't satisfy the condition that AN plus 1 is a subset of AN. In fact, these are completely disjoint. So the example is plain wrong. Oh dear, what a shame. Okay, so it's going to have to be 0 here. The example's wrong. It doesn't satisfy the requirements. Well, remember, we are trying to be helpful to a student. The point of evaluation is to provide feedback, to give credit for relevant work that is appropriate. So having seen that there's some stuff here that looks good, I'll see if I can give credit, because what's going on here is the students carrying out the kind of argument that would be required to prove this result. Now, admittedly, they've made a mistake here, and we've dinged them for that quite significantly. They've got 0 for that. The example's incorrect, but the rest of this is a kind of argument you would need to give, or you could give, if the example was correct. If the student had given intervals that satisfy this requirement, then this is the kind of argument that you would need to do. So if these ANs satisfied that requirement, if there'd been different definitions, this is the kind of argument you'd want to do. So this is not irrelevant work here. There's a fundamental mistake. But in terms of what's done, this is actually clear. Since it's not relevant, I can't give full marks for clarity, but I can give 2 marks, I think, for that one. It's clear in of itself, it's just not clear within an example that works. The opening, once you've got the example down, the opening first of all consists of defining the AN and then of carrying out some little argument, and that's done well. So again, I'm going to give 2 for that. State the conclusion. The conclusion is absolutely stated. Again, this doesn't work for this example, so I'm just going to give 2. Ditto for reasons. Overall, all I can give is 0 because the example is plain wrong. The example does not satisfy the requirements. So I'm giving it 8, which 33%. It's a shame, given that the student has done some decent stuff here. But the fact of the matter is, if you're asked to prove an example, if you're asked to give an example to show something, and if your example doesn't satisfy the requirements, then it doesn't show it. So a third, I think, is probably as good as you could reasonably expect, given what we're asked to do. Well, this answer to number 10 is perfectly correct. One could argue that the student should have said clearly A to the n plus 1 is a subset of AN for all n. But the argument itself is absolutely logical. It's rock solid. So given the quality of the argument, I certainly wouldn't penalise for doing that. I mean, you may differ on that one, but as it's pretty clear by now, I'm sure, grading, even when you've got a rubric, grading is pretty subjective. Now, it is the case that professionals, by their subjective grading, actually achieve an objective result because professionals end up remarkably similar in the grades they give. Not exactly, but pretty close. So there is this. It's a mixture of art and science going on here. But this is absolutely correct. I'm going to give. I'll put the marks down first of all. I'm going to give 4 for everything. Again, if this was a single student submission, I would be very suspicious and want to talk to that student, because to have gone from some really bizarrely wrong answers that suggest the student's got no understanding to produce something of this level of sophistication that defies credibility has been a legitimate piece of work by one student. But let's just look at what this thing does. For any n, so we observe that zeros in all of these sets, so zeros in the intersection. Also observe that anything other than 0 is eventually going to get missed out, and so anything other than 0 won't be in the intersection, so the intersection consists purely of 0. This is slick. It's slick, and it's as brief and succinct but correct as it's possible to be. So grading what's in front of me, for me it's straight 4s all the way through, because given the slick nature of this proof, I would be forgiving for having missed that. Yeah, that should be in. I mean, you should make that statement, especially given the audience that this is intended for, which is an introductory class. So you should really observe things like that. But this is straight across the board correct. Okay, well, that's the first sample exam solution done. What have we given for this one? Let's see, we gave the totals we've given for this one. For the whole sheet, we gave 18, we gave a 0. Looking back on our list now, we've got an 11. We gave a 0, we gave a 0, we gave a 4, a 12, a 15, an 8, and a 24. Those are what we gave. So altogether, we've given 92 out of a possible 240. So overall for this paper, we've given 38%, slightly more than 1/3. Okay? Which actually would be a passing grade. For material like this, anything of the order of 35% or more would definitely be a passing grade for an introductory course. Remember that the grades are meant to indicate how close you are to being able to produce at the level of a professional, and no one expects someone in an introductory course to produce the kind of results that a professional does. So for this kind of course, at this kind of level, anything over the sort of 30-35% mark is actually acceptable. And it would be unusual for a student to score sort of 70 or 80% if they were really genuinely a beginner. You do find students like that. You sometimes find students who score 90 and 100% at the beginning. They tend to end up becoming professors of mathematics. Okay. That's the first problem set solution done with. Well, looking at the second sample problem set solution, the answer to question 1 that this person gives is perfectly okay. Observes that you, first of all, makes the note that this thing is false, which is correct. Then says you have to look at these values of m for that reason, look at those values of n from that reason, and then says if you calculate the values for all of those 6 possible pairs, you'll find that the answer is never 12, and this proves the result. So it's logically correct, 4, it's perfectly clear, there's a great opening, conclusion is certainly stated, reasons are given, overall, full marks. So this is a 24. Incidentally, there's no need to actually carry out these calculations. For this audience, or at least for any audience, for someone who's able to read a proof of a result like this, you can assume that they are able to carry out simple whole number calculations like this. So there's no need to actually carry out those calculations. That's now, you can simply assume it. So no need to do the calculations. It's enough to state that the calculations can be done. Saying that you're doing the calculations is different from doing the calculations. If you hadn't said that, then you're leaving the reader in the lurch. But simply by saying that it follows by calculation, the reader can fill in the details. Perfectly okay. Well, let's look at number 2 now. Oh, this person thinks it's false. Well, something's gone wrong because this is actually true. Okay. Let's see what's gone wrong. This is okay. That's a good representation of an arbitrary sequence of 5 consecutive integers. Then you add them all together. That's fine. You've got 5n plus 1 plus 2 plus 3 plus 4. That's fine. You've got 5 n's and you've got a 1 and a 2 and a 3 and a 4. So you've got 5n plus... Aha! There's the problem. 4 plus 3 plus 2 plus 1
is actually 10. Oh dear, that is a shame. How do we deal with this? Because this is clearly an utterly trivial mistake. The person has simply made a little arithmetical slip. So I'm not going to take too many marks off that, because clearly anyone who can produce an argument like this, which is fine, is capable of adding 4 numbers together and getting the right answer. They've just made a slip. And the experts make slips like that all the time. I make slips like that all the time. And the world doesn't come to an end. Of course, if you're an engineer building a bridge or something, then the consequences of a simple arithmetical slip can be quite severe. But at the moment, we're looking at people's ability to do mathematical thinking, and I'm not going to take an awful lot out of their result because they've made a simple arithmetical slip. I'm going to give 2 for logical correctness, because it's actually not logically correct, because adding those 4 together is part of the logical argument. So the argument is not correct. So I'm going to take that down to 2. It is, however, clear. There's a nice clean opening, a clear statement of a conclusion. Reasons are given. Okay. Even talking about the division theorem. Overall, though, I'm going to have to drop down to 2 for that, because it's wrong. The result is wrong. Okay. And there's an arithmetical mislip. Yes, it's tiny little slip, simple arithmetical slip. We know that this person could add those together and get the right answer if they were fully awake at the time. But end of the day, it's wrong. So this person only gets 20. I say only. 20 out of 24 is actually this kind of material is a good result. So we're just making note of the fact that there is an arithmetical mislip, and we otherwise we'll congratulate the person on a nice, elegant little proof. Well, in question 3, what does this person do? First of all, they don't say whether it's going to be true or false. And we can't immediately infer that without reading through the thing. So I'm going to be a little bit hard on this one. So this person is claiming that it's true. Okay. Well, they're not claiming it, but they're assuming it's true. That was their conclusion. They simply didn't make a claim. And I think on this occasion, given that you have to sort of read through to the end to find out whether they think it's true or false, I think that's not a good start. Okay, let me see. This is good. This is really the key to this thing. It's the observation that a pair of successive integers multiplied together is always even, because one's even and the other one's odd. And here there's a typo, because that's meant to say +1. So there's some carelessness in writing this one down. A good idea, but there's some carelessness. In fact, it's even worse, because that's really not what was claimed. What was claimed is that n squared plus n plus 1 is odd. So what you would have to say is that this guy equals that guy plus 1. So you might have to say, hence, cross that out there, is odd as claimed. Okay, now we've sorted this guy out. Okay, this is a particular proof. So there were some problems with this. The person sort of obviously made the key insight, knew what the answer was. So the issue with this person isn't that he or she isn't able to do the mathematics. They're not able to communicate it well. This is not a proof. We are looking for a proof, and this isn't one, for a whole variety of reasons. So what am I going to do? Well, it's logically correct. I'm going to give 4 for that. I'm only going to give 3 for clarity, because once we got into it, things were fairly clear. There were some typos and so forth, but I think it's sufficiently clear. Opening. Well, in terms of the proof, there's a good opening. I'm going to give 4 for the opening. I'm going to sort of separate and say, stating it's true is not really the opening. It's just sort of announcing the answer. And then for the opening, saying that for any n this is true, that's fine. Stating the conclusion, I'm going to give 3, because they really didn't state this part of the conclusion. They left it in that other form. Giving reasons, that I think is fine. Reasons are given. Overall,
going to go down to 2 on that one, I think. So I've got a total of 20. There's nothing really wrong, it's just niggling little bits. Okay, and in fact, you know, if I was grading this while I had a headache, I might have even knocked it down a little bit more, because I think this is a lot of carelessness here. The person just needs to, you know, they know what they're doing in a sense, but they just need to figure out or to learn or to acquire the ability in order to do. They know what they're doing. What they need to do is learn how to express what they've done in a way that makes it a good argument, a good proof. Well, if I was grading an actual paper from a student, when that student had got marks into the 20s for the first 3 questions, I would not have expected to see an answer like this. And in fact, this is a consequence of the fact that I've put these solution sheets together from the kind of answers I've seen over the years. And so this would have been produced by a student very different from the kinds of students who would have produced the answers to questions 1, 2 and 3 that we've just looked at. Because this is just totally wrong. It's a sort of trying to prove some kind of a converse. The person is presumably trying to show that if you start with an integer, then you get an odd natural number. You start with an integer by doing this, and then they've said it's not true because under those circumstances you get negative numbers which are not natural numbers. So it's just a total failure to understand what's required here, and when you've got that degree of failure, the grading sort of becomes easy in terms of giving a numerical grade. You put zeros all the way through. Now, if you're faced with a physical student and your job is to help that student do as best they can, which is what we do with our students on the campus, then you're going to have to spend some time with that student, because this is just totally confused. And it certainly seems to be based on misunderstanding the implication. You're supposed to start with any odd natural number and deduce that it's of one of these forms, not take an integer and look at the way these numbers follow from that integer, and by taking a negative integer results in get the result that these things are not natural numbers at all. So in a sense, this is an easy one to grade numerically. It's just zeros across the board. Well, in number 5, what's going on here? There's a bold statement here. N can be expressed in one of the forms. Can it? Well, indeed it can. But the reason we know that is because there's a very important theorem called the division theorem. And without stating that, we're just making a bold statement and leaving it up to the reader to figure out why. Okay? So already we've got problems with this one. We suppose a proof is meant to be an explanation. It's meant to be a story, right, with a beginning, a middle and an end. This doesn't have a beginning, and so that's we're just jumping straight in. So it's not a proof. It's not an argument to convince someone. It's a challenge to someone. It's a puzzle to someone to figure out what's going on, and that's not what proofs are about. Okay, we'll address that when I give the marks, but let's read on through. It's certainly the case that by the division theorem you do get that. The remainder is either 0, 1 or 2 when you've got 3 as the divisor. In the first case it's divisible by 3. In the second case n plus 2 is divisible by 3. And in the third case n plus 1 is divisible by 3. Okay. So logical correctness. Yeah, it's logically correct. Okay, everything this person does is what's required in the terms of the logical structure. Clarity, I'm going to knock that down 1 in terms of clarity, because that makes it somewhat unclear. I'm going to take more account of that in a minute. And I don't want to sort of double penalise someone. So this is an issue of reasons here and openings. But nevertheless, having that missing means it's unclear. It's also, there's a bit of unclarity, because there's no sort of conclusion at the end saying, you might need to say something like this, what can we say? This takes care of all 3 possibilities. Something like that, just to sort of say that there are 3 possibilities and we've taken care of them. namely possibility 1, possibility 2. That alone, I mean, this is the end of the story, if you like. And so maybe we could say, and proves the result. We could be totally open about that. But I'm not too worried about that one, because if this was a long argument, if there were 10 cases, the reader could have forgotten where they were. But there are only 3 cases, they're in 3 lines, they're right in front of the reader. So the reader who's read through this, having had it established that there are 3 cases, the reader would instantly, I think, recognise that that's the end of the proof. So I'm not too worried about this one. But coupled with the fact that it didn't have an opening, we've now got a story that's just got a middle, no beginning and no end. So I'm going to knock it down for clarity here. I'm also going to knock it down for opening, because it doesn't have a good opening. In fact, there really is no opening. This is just an in-your-face statement. Ditto, stating the conclusion, was left a little bit vague. Reasons, I'm going to put a 0 there. I mean, this is a huge reason. And this is the key to the whole result. This is a consequence of the division theorem. So if you don't mention the division theorem, you haven't really said what's going on. You haven't said why this thing's true. So this is huge. I mean, there's no way I could give more than 0 for that. And of course, I couldn't give less than 0. So overall, I'm going to put a 2 here. And I don't think I'm double penalising here, because there's no beginning and there's no end. And arguments are supposed to have beginnings, middles and ends. It's at this level in mathematics, when we're talking about proofs, it's not enough to be able to do the algebra. It's to be able to use the algebra in the course of giving an argument to establish a result. Okay, so I've got looks like 15, I think, right? Yeah, so this person lost quite a few marks, but I think in terms of proofs, these are big errors. Yep, I think that's a fair mark. 15. Okay, number 6 proves that the only prime triple is 3, 5, 7. So we want to take 3 successive integers and show that they're not all primes. Okay, where n is bigger than 3. I show that 3 divides 1. This is a very good start. Very good start, very clear. Look at 3 numbers, well, except this person clearly meant to say odd, because it's about odd numbers and they've picked them 2 apart. So there's a little bit of carelessness here. Okay, well, I'm inclined to let that go. I mean, it's clearly, I think it's clear, given the way this starts, that that's a typo. If these are then by the division, this is good. N equals 3 plus 1, 3q plus 1 or 3q plus 2 for some q. Well, again, the person maybe should have said integer q here for some integer q. That would have been nice, but it's really not required, because we are doing number theory, and in number theory you can assume, unless otherwise stated, that everything is an integer, because that's what number theory is about. Well, at least this kind of number theory. There's something else called analytic number theory, but that's sort of different. But in this kind of number theory, basic number theory, if it's not stated, you can assume something's an integer. If it's a positive integer, you really need to say so. But integers are what it's about. So let's see. In the first case, n plus 2 equals 3q plus 1, and I think the person really wanted to put in here and missed it out, 3 times q plus 1. Okay, because they want to say that. Oh, good Lord, this is another typo. Has to be a typo, right? The person surely meant to write n plus 2 there, because they've shown that n plus 2 equals 3 times something. And indeed, they want to show that 3, the whole point is you want to show that one of these things is divisible by something like 3, and so it's not a prime. So, and 3 is what's going to stop it being a prime, by the way. So this was wrong. I mean, it's given the kind of argument that's going on, I'm sure this is a typo, but this is getting to be a bit of a habit, okay? In the second case, n plus 4 equals, and again, I think we should have put in here 3 into q plus 2. So, oh, dearie me, because then you've got n plus 4 is a multiple of 3. So that should now say n plus 4. Okay, thus 3 must divide one of the 3 numbers. That's right, this person was absolutely doing the right thing, which means they cannot all be prime. Okay, so the logic is really good. But boy, this person is careless. So let's see how I'm going to grade that. Logically correct, yes. Clarity, 4 because I think these were so transparently typos. So transparently typos. All of them. In fact, if I was grading a pile of papers and I wasn't thinking about recording myself going through the grading, I might well have just read through these and not even noticed these things. I would have probably read what I thought I was reading because the structure is so good. So I think I'm only noticing these because I'm recording it for posterity. Okay. The opening is wonderful. Start with 3. They've absolutely stated the way they're going to prove it. Okay. The conclusion is stated correctly. The only key reason to state it really is the division theorem. And that's stated. So I'm going to give 4 for that. On the other hand, this thing is littered with typos. You know, now I'll overlook 1 typo and maybe 2, but there are typos everywhere here. Now that just is way too careless. I'm going to go right down to 0 here. You know, you can't get by if you're constantly making typos. Incidentally, you know, you might have thought that I should have been a bit harsher here. The reason I was very tolerant of typos is that those of us who are doing mathematics, and you know, when we're proving things, we do make typos all the time. We miswrite, we mistype, and the reason is we're concentrating on the hard stuff. We're concentrating on the logical flow. I mean, I do the same thing when I'm speaking. You know, if you play some of these tapes over again, you'll realise that I often don't say quite what I'm writing, or I misspeak, and that's because I'm focusing on the depth of the things. I'm focusing on the concepts, not on what I'm saying. And after all, this is a course about mathematical thinking and communication. But in the case of communicating, if you wanted to see, you know, my attempts at writing things down correctly with all the typos eliminated, then you read my book. You know, the book that goes with the course, there are maybe still 1 or 2 typos, but I worked hard and I took feedback from other people to eliminate the typos. So when we're producing papers and books, those of us in the business do take care to get rid of the typos. But when we're actually generating a proof, when we're thinking, when we're doing something, then typos crop up all the time. And yes, we'll deduct marks because they do detract from being a proof. But in and of themselves, typos are secondary at this stage in the game. And so I just took the marks off right at the end. Okay, now that knocks it down to 20. Still a remarkably good result. Because this person clearly knew what to do, and it's actually a very good proof. It's a good proof that's spoilt because of total carelessness resulting in a lot of typos. And so I don't think I could have given more than 0 there. It was just too many of them. Okay, let's take a look at number 7. So number 7, prove that for any natural number n, this guy equals this guy. Obviously, I think it's fairly obvious that you were going to do this by induction, but in any case, this person is doing it by induction and begins very appropriately by stating that. Let's check that the proof is correct. For n equals 1, the left-hand side reduces to just 2 to the 1, which is 2. The right-hand side is 2 to the 2 minus 2, which is this, which is also 2, so that's true. Assume it holds for n, then... Oh, well, now we've got a puzzle on our hands. Where did this come from? What is the person doing? Where's the induction hypothesis being applied? Well, if we stare at it for a few minutes, we realise that the induction hypothesis is what lies behind what's going on here. Because what this person is doing is saying, this is the left-hand side of the identity we're trying to prove, and this is the right-hand side of the identity. So we're taking the original identity, which is that this equals this, and we're adding 2 to the n plus 1 to both sides. So we're taking an assumed equation and adding the same thing to both sides. And then we're doing a little bit of algebraic simplification, and we're going to come down to this, which is the identity for n plus 1, and the result follows by induction. Okay, so that's all fine. But we had to puzzle that out, because what this person should have said was something like, then adding 2 to the n plus 1 to both sides of the assumed identity. If we do that, then it's clear what's going on. We're taking the assumed identity and we're adding the same thing to both sides.
We don't really need to explain this. It's fairly obvious that this is just algebra. You could say by algebraic manipulation, by elementary algebra, say what you like, but this is the key thing, because this relates to the structure of the whole argument, and that's the identity at n plus 1. And the result follows by induction. Okay, so this is the problem, and I'm not going to be able to let this. I'm not going to be able to overlook this because it was a big miss. Question is, what am I going to say in terms of the grade? Well, it's certainly logically correct. It wasn't clear. I had to work. I had to sort of figure it out, what was going on. So it's not a clear proof. It certainly had a good opening. Prove it by induction. That was good. Okay. The conclusion was there. In fact, you know, the inner conclusion, the conclusion of the induction step was there, and then the result follows by induction. That's wonderful. I really like that. This is where the person steps to the front of the stage and takes a bow, takes the applause of the audience. This is the end of the thing. It's the grand finale. I've got to give 4 for that. Wonderful. Reasons. Ooh. Well, yeah, I mean, the big one was there. Okay, the one that's stating it's by induction. But this one is really important, and I'm going to take it down to 2 for that. Yeah, I think 2 is about right. You might want it to. You may want to go a little bit lower than that. You may say this is really, really significant. I'm inclined to think 2 is okay. I've sort of taken some account of it here, but it is a major hole. And as a result, I'm only going to give 2, because this didn't read that smoothly as a result of that. So the total is 18. And I think that's just that's a good mark in a sense. I mean, that's the mark it should be, because this was just left it too difficult. Okay, let's see if number 8 brings any more joy. This is interesting. This expression is one that you'll see professional mathematicians use, especially when they're sort of working among themselves. Most of us, I think, when we're teaching this kind of material to an undergraduate audience, we would avoid saying that, because that could be interpreted by a beginner as meaning just pick one that you like, or pull one off the shelf or something, and that's not really what it means, unless you're saying pull it off the shelf randomly. It's much better to say let epsilon greater than 0 be given. In other words, you have no choice whatsoever in that epsilon. It's literally given to you arbitrarily. Now, mathematicians use this, and when they do that, they're using this elliptically to represent pick epsilon greater than 0 arbitrarily. They don't articulate the word arbitrarily. It's understood to mean pick it arbitrarily. But as I say, for a beginner, it could be confusing. And since proofs are meant to be devices that convey reasoning, convey the truth of something to a particular audience, what classifies as an acceptable proof in one group of people doesn't necessarily classify as an acceptable proof in another. We're not talking here about rigid proofs in mathematical logic that can be read by computers or any of that. We're talking about one human talking to another. The focus of the course is both humans reasoning mathematically, not just about mathematics, but about things in the world, and communicating their reasons. That's what we're looking at. That's why the course is called mathematical thinking. It's not called mathematics or mathematical logic. And so we have to be always conscious of who it is we're trying to convince and to convey some meaning to. And this, I think, is not a good idea. And I'm going to deduct a little bit for that, even though mathematicians would do that. Okay. Since that tends to mean there is an n such that that's true. You see, this is actually fine. In fact, if this was a graduate course in real analysis, I would give full marks for this. Absolutely. Because I would know that by that stage in their development, everyone in the class would know what that meant, and they would be able to read this. This is actually, I think, difficult for a beginner to read, partly because we're using lots of words rather than symbols. This is one of those occasions where I think some absolute value symbols and some minus signs and some less than signs would make it clearer. To the outsider to mathematics, mathematical symbols seem to make things more obscure. But once you're in mathematics, the symbols, I think we all found that the symbols are much clearer to read. Okay, and if you don't believe that, you should get hold of a medieval manuscript in mathematics where they used almost no symbols and it was all written in words, and they're almost impossible to make sense of. In fact, when I do that, when I look at ancient manuscripts, and I do from time to time, I translate them into modern symbols in order to understand them. Okay, how am I going to assign points to this? Well, it's logically correct. Absolutely, it's logically correct. So 4 for that one. I'm going to say 3 for clarity. A couple of reasons. One is that I don't think is clear. I think that just makes it obscure. The student might well think, well, what if I just randomly picked a number for which the proof worked, but it didn't always work? That would not be at all unjustifiable for a beginner to say that. So I think there's some level of unclarity here. And I also think this hence would need some kind of an explanation, like by definition of limits. Just a pointer to the student as to what's going on. Hence. Well, why hence? Well, because it's by definition of limits. The stuff in the middle, if it was written out with absolute value symbols, minus signs, less than signs everywhere, as inequalities in the standard way, I think this would be relatively easy to follow the logic for a class at this level of development, sort of undergraduate level of development. So I think the confusion, if there is any, is probably caused by the fact that it's written in words. So I think I'll just take the 1 down here. The opening, I'm going to take 1 off there as well, because although this is something that professionals do, they do it knowingly, and I think in this group, with this audience, that actually is not a good opening. State the conclusion, I think I'll give 4. I'll worry about that part. The conclusion was absolutely stated. Now arguably this is part of the conclusion, but I'm going to take care of that when I talk about not all the good reasons there. I can't take this down by too many marks because this is technically all correct. I'm just sort of nudging it because of audience design issues, really. And likewise, I'm going to take that down to 3. I think it's just a little bit too brief, succinct, too crisp in an advanced mathematical sense to function well as a proof in the community we're now working. So altogether, I've got I've lost, which is 20. I've taken 4 marks off altogether. So it's a good mark. And all of the deductions were based on the fact that this is not a good argument for the audience for which it's intended. And in some sense, the audience for which it's intended, other students in this class who will be grading each other on the final exam. So one has to sort of provide a good example, a good illustration to a typical student of the class. Well, maybe not a typical student, a student who's still here at the end of the class. And as we all know, that's usually between 5 and 10% of the students who start. In MOOCs, that is. So with that intended audience, I think I'm justified in taking 4 marks off. Okay, well, this is interesting. The answer is a lot shorter than the question, but because the question contains a definition of this thing. Okay, what does this person do? Well, they obviously begin by, well, typo there, I guess, should be a comma. This person begins by sort of writing some explicit intervals. They're taking the unit interval, open unit of interval, then the first half of that, then the first half of that, then the first half of that. So they're taking, open interval between 0 and 1, then they're taking the one between a half, then they're going down to a quarter, and they're going down, 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 and they're going to squeeze in on the origin there. Okay, and then they write down a general definition of the nth interval. That's good. Since that is okay, right. Well, I did my PhD in set theory. I worked solidly in research in set theory for 10, 15 years or so. So when I read this, I have no trouble with it. I know exactly what's going on. This works as a brilliant proof for me. So if I'm the intended reader, yep, full marks. But the intended reader for this proof, this particular one in this course, isn't me. It's other students in the course. And for that audience, this is just not good. It's just too obscure. So I'm going to start taking some marks off for the person making it just too difficult to follow. I can't take marks off for logical correctness because this is absolutely logically correct. I saw that the instant I looked at it. I'm going to take a mark off for clarity because it's really not clear. It's obscure. Opening, insofar as there is an opening, that's fine. I mean, this person actually sort of even motivates it by looking at the sequence that we're taking the definition for. So I think that's a good opening. What about the conclusion? Well, the conclusion was stated absolutely crisply. So the conclusion would definitely state it. We have no doubt that this person claims at this point to have proved the result. Okay. What about reasons? Boy, I could only give 2 for that. As I say, if I'm the intended reader, there's all the reasons I need there. But for students in this class, I think we need a little bit more than that. You need some assistance as to why that tending to 0 implies that. Maybe I'm even been too generous with 2, but I'm inclined to sort of go with 2 here. And overall, I'm going to take it down by 1 because I just think it's just too obscure for the intended audience. So I'm down to 20. Still a good mark, but I think just way too brief for this audience. As I say, for a graduate course in set theory, absolutely fine. For an undergraduate introductory course like this, where set theory is just an example at the end, not fine. Unfair on the reader. And we've taken account of that. Okay, and finally, we've got this one, very similar, sort of variant of the previous one, if you like. And in this case, the person has taken the closed interval from 0 to 1 over 2n. By the same argument as in question. That's fine. If you've got an argument that you've already used and you've established, you don't have to repeat the argument. You can simply refer back to it. It's a bit like calling a subroutine in a computer program, pulling up a module or something like that. You're entitled to do that. That's a perfectly valid thing to do, providing the material is accessible and within the context of the same exam. That's fine. And then it follows that equals that. Okay, so it's essentially the same argument as before, with a closed interval, and you get a slightly different outcome. So I'm going to approach this. I should mention one thing I've just noticed. Neither in the last case nor in the present case did the person prove that. Well, you could say they should have proved that because you are supposed to show that it has a stated property, and arguably that is part of the stated property. I think most of us probably read it as part of the setup, but it really has to be verified. On the other hand, when you're looking at these kind of intervals, it's obvious that they're nested. If you start drawing the intervals. So I'm not going to ding any marks for that. I'm not going to go back to the question 9 and take a mark off. I think given that there's a degree of complexity in the reasoning here, that just pales into insignificance. Okay, so in other circumstances, maybe we'd need to take more account of that. But for here, I think we can just focus on the heart of the thing. Since it's essentially the same argument as before, I'm going to approach the grading as before. It's logically correct, yes. I'll take 1 off for clarity because it's not clear to the intended reader of this argument. There's a good opening. There's a good clear statement of the conclusion. Some missing reasons, and overall, we need to take a point off because it was just too slick and short and brief for the intended audience. So that takes me down to 20 in that one. So altogether on this paper, I gave a total of 24 for the first one, 20 the second, then another 20. Then there was that 0, that disastrous question, that disastrous fourth question. Then there was 15. Then there was a 20. There was an 18. Then there was a 20, another 20, and another 20. There were 20s all the way through at the end, right? Okay, so I've got a total of 177 out of 240, which is 74%. So, although this wasn't the work of a single student, it was an aggregate, by and large, most of the questions were done pretty well. We got lots of results in the 20s and the 18s. So, if this had been a single student, and it's possible that it was even a single student and there was an aberration, who knows what would happen then. But that would have been a pretty good result. 74% for a beginner in this kind of material is really a very strong result. We're turning to the third sample problem set solution. Let me tell you up front that all 10 answers are going to end up getting 24 marks. This is, if you like, a model solution sheet. I mean, I don't give
model solutions, because you can't grade this kind of mathematics by comparing someone's work with a model solution. You have to look at the work they've done and evaluate it on its own terms. Just as you can't do this kind of work by looking for templates, you can't grade it by templates either. You have to evaluate it in its own terms. So I don't give out model solution sheets. On the other hand, this particular video that you're watching will show you a good solution for each one, and in most cases, actually in all cases, a very slick solution. So before we begin, we know that we're going to be able to congratulate whoever it is that did this solution. Now wait a minute, that was me. I did this solution, and I can't really congratulate me because I'm the one putting the course together. Okay, let's just make some, what I'll do is I'll go through and I'll just make some comments. So the grading is going to be fairly straightforward. It's going to be 4, 4, 4, 4, 4, 4, 24, and it's going to look the same throughout. This is a very short proof. It's certainly false. We observe that for any m, if n is bigger than or equal to 2, then this thing's bigger than or equal to 13. So we only need to show that there's no m for which that's the case, i.e. no m for which that's the case, and that's immediate. Okay? Very short, very sweet. That's all you need. Full marks. So I can just go straight in and put the numbers 4 in everywhere, and a total of 24 for this one. And this is very much like the solution we saw in sample exam solution 2, except in that case the answer had an elementary mathematical mistake here, an arithmetical mistake, where the student put 8 rather than 10. But other than that, this is essentially the same argument. It's written extremely slickly, and everything's there that you need to be there. I wouldn't normally expect a typical student in the class to produce something quite as short and succinct as this, but it's absolutely perfect proof. All of the reasoning's there, everything you need there. So, very nice little proof. Right, looking at number 3 now, I'm not going to put in all of the 4s anymore. I'll just jump straight in and put the 24. Beautiful proof. Consider the two cases, even and odd separately. Very elegant. If it's even, then that guy works out as being odd, and I've actually stated that it's odd. I admit that I was the one that wrote this out. If n is odd, same thing, you follow it through and you show that this guy is odd, and then you wrap the thing up by concluding that in both cases n squared plus n plus 1 is odd. And the danger with this particular video is that it's going to go by too quickly for you to sort of take it in. So what I suggest you do is, as we get to each one, you freeze the video and you just take a look at it, and you see why it works. Incidentally, some of the early research that was done at Stanford onto students doing MOOCs showed that there was a very strong correlation between the number of times the students used the pause and rewind button and the success they had in the course in the long run. And that's for a whole variety of reasons. One is, of course, if it shows that the student's engaged. If you have to keep stopping and rewinding, it shows you're engaged, it shows you're reflecting on the work, it shows you understand when you don't understand what's going on, you know when you don't understand, and you're taking control of your own learning. So the correlation between using the pause and rewind button and success in the course is actually quite high. And indeed, one of the advantages that MOOCs have over classroom lectures is that you can do that. It's very hard when I'm lecturing in the class to freeze me and rewind me. In fact, I wouldn't recommend you try to do that. Okay, I certainly hope you wouldn't try anyway. Okay, let's go on to number 4. Okay, so for question 4, we know we're going to give 24. Let's just go through it. M is a natural number by the division theorem. So stating the reason for why this is going to be the case. There are unique numbers n and r such that. So actually giving a statement of the division theorem. So m has got to be one of these 4 guys. 2 of them are even, so that if the number m is odd, the only possibilities are the other 2. And that's the proof. Very slick argument. Again, you might want to freeze the video at this point and look at this, but absolutely perfect little proof. Everything's there that you need to be there. Number 5, again, put down 24. I think the only comment to make here is the fact that this solution doesn't state explicitly that q is an integer. As I've mentioned before in the grading, when you're doing number theory, you can assume that any variable that's not explained or defined denotes an integer. Integers are the default case. So simply by looking at the context, you can get by without saying it's an integer. It's not wrong to say it's an integer. You might want to do that just to play extra safe. but in this context, that's going to be an integer. If we were trying to make a claim where we were saying something about there being a positive integer, then we'd need to say it. But the default case when you're doing number theory is that anything that's not specified can be taken to be an integer. So there's no need to say that it's an integer. This is fine. Okay, 24, we know that. I think the only remark I want to make here is that, and I've made this remark before, it's perfectly okay to cite previously established results, just as it's okay to cite standard results. So it's okay in the context of putting together a piece of work to say by the answer to the previous question. You can refer back. It's like using a lemma when you're proving a theorem. So perfectly good. Very short, very slick, definitely worth full marks. Well, the way most people prove this is by induction. This person's done it a different way, and this is very nice. Look what they do. They say let S be the sum we're interested in, then double S, and you multiply through by 2, so you get a 2 squared there, and that last one becomes a 2n plus 1. Then you subtract the first one from the second one, and everything drops out, except you've got the 2n plus 1 at the beginning, from the end, and you've got the minus 2 from there. So you've got 2n plus 1 minus 2. But 2s minus s is just s. So you've got s equals that guy, s, this is s, remember, equals 2n plus 1 minus 2. Isn't that nice? That is beautiful. In fact, this is so nice, this is so elegant, no need for the power of induction. I'm going to put a smiley sticker on that. That's a very, very nice proof, very clever. It's pleasing to see things like that. Okay, so let me put the 24 down and let's see how it works. Let epsilon greater than 0 be given. Very nice, starting as one should. By the assumption we can find an n such that this. Why are we picking an n with this? Well, because the whole thing is about multiplying by m. And so in order to make it work out at the end, we're going to start by dividing by m. Because we're looking ahead, we're going to say we're going to end up with an m times something. And we want to end up with an epsilon. Well, how can you take m times something and end up with an epsilon? Well, the something you multiply it by is going to be epsilon over m. So that's where that came from. We get this by looking ahead to this last step. When you first meet this kind of structure, these kind of proofs are hard to do, but when you've seen a few of them, you get pretty good at looking ahead and saying, yeah, I'm going to have to divide by m, or I'm going to have to take epsilon by 2, or whatever it is. And that gives you the limit. So if you almost certainly are having difficulty with this at this stage in the game, but if you spent a few more weeks looking at this kind of argument, you'd get very good at looking ahead. It's not guesswork. It's literally looking ahead to see what you want to do. And if you can't look ahead, just work with anything you want and then go back and adjust it. You can just go back and change things. Okay? This is about as slick as you can get. Incidentally, in the last sample exam solution, this one was written out in words. I think you'd agree with me, given that you're still in this course, that it's much clearer to write it like this in symbols than to write it in terms of words with saying things like an is a distance less than epsilon over m of l and so forth. To the modern reader, symbols are much cleaner and easier to understand than a lot of words. Oh, this is a particularly nice proof. Admittedly, the person doesn't prove this part. We've talked about that with a previous sample exam solution. I think it's okay not to do that. It would sort of be nice to have it there, but it's okay given that this is so good. And let's just, because it's obvious. I mean, you just these intervals. Arguably you should state that. Okay, but it's we're pushing the limit of where that's really necessary now when we get to this kind of sophistication. And this is sophisticated. It's very slick. You let those with the intervals. You observe that, and this is sort of almost, it's getting very close to saying that, but it's a little bit beyond that. You're saying everything's within 0, 1, so everything in the intersection is going to be in there. And then this is very nice. If x is anything in there, we can find a number such that it's going to be excluded from that interval. This is very nice because that just nails the fact that nothing can possibly be in the intersection, so the intersection is empty. So very, very nice, economical, elegant proof. This is what mathematicians mean when they talk about a proof being beautiful or elegant. It's just perfect. Okay, let me put the 24 down. So this is almost exactly the same as the previous example, except that this is now left closed, so 0 is an element of all of these things observed here. But now it's okay to refer to the previous argument, the one for question 9, because that shows that no element x strictly between 0 and 1 can be in the intersection, so the intersection consists only of the point 0. It really is the same argument as before at that point. We've just included the initial point in there. So again, very elegant, very slick, and that really completes the 3 sample solutions. The first one was really a bit of a low end one. There were all sorts of things wrong with that. You often get papers like that. In fact, you may get a fellow student's paper like that. It's the kind of thing that you often get when students are really beginning and struggling. The second sample solution, that was the kind of thing that you'd tend to get from pretty good students in a class, where we got sort of 74, 75%. That's probably as good as you'd get. This solution set, the third one, where everything was perfect, that's something that only a professional's like to produce. I mean, it really was a pro's job. And you would be I would be very surprised to see that coming from a student. It would be most unusual. But there we are. So, having done the 3 sample solutions, your next task will be to grade 3 papers from your fellow students, or at least 3 papers from your fellow students. Chances are they're not going to look as slick and as elegant as this. They're probably going to be a bit longer. These are all compressed to fit on a slide, carefully chosen and edited to make it look neat. The real world is never as neat as that, so you're probably going to find it challenging in different ways. But I hope, having gone through these 3 sample solutions, you've got some degree of confidence as to the kind of things to look for. It's clear that this is not an exact science. By having a rubric, we can sort of we can get some level of precision. As I say, the professionals tend to agree by and large, but you're going to get variations of 1 or 2 points, absolutely, and sometimes even more than that. This is qualitative stuff. It's not quantitative, and assigning numbers to something that's essentially based on judgments is not an easy thing to do. Okay. Well, good luck on grading your fellow students' work.